Welcome to the Microsoft Full Stack Developer Professional Certificate. In this program, you'll master the skills needed to build dynamic, full-scale applications from the ground up. You'll start with coding foundations, learn C# programming, and create engaging user interfaces with Blazor and web technologies. You'll also gain expertise in managing databases, handling server-side programming with .NET, and securing your applications using best practices in authentication and security. With Microsoft Copilot integrated throughout, you'll streamline coding, debugging, and optimization. Along the way, you'll enhance performance, ensure scalability, and explore cloud-based deployment using DevOps tools. By the end of these 12 courses, including a capstone project, you'll have the practical experience and technical knowledge to become a proficient, full-stack developer. Let's explore the courses in this program. We will begin with the foundations of coding full stack, where you'll learn to plan and structure projects, think logically, and solve problems. You'll design algorithms, implement control structures, and develop modular, reusable code. Microsoft Copilot will assist in coding and debugging throughout the course. In Introduction to Programming with C#, you'll set up .NET projects in Visual Studio Code and learn key programming concepts like variables, loops, methods, and object-oriented principles. You'll also work with asynchronous programming and use Copilot to write and optimize your C# code. Next, in Introduction to Web Development, you'll learn the basics of building web pages using HTML, CSS, and JavaScript, making them responsive and accessible. You'll also collaborate using GitHub and develop a small interactive website with Copilot's assistance. Then, in Blazor Pages for Front-End Development, you'll use Blazor to create dynamic websites, working with components and data binding. You'll build a Blazor project, manage app data, and use Copilot to enhance your website's efficiency and user experience. Moving on to back-end development with .NET, you'll work with the .NET framework, creating web APIs using ASP.NET Core and integrating OpenAPI for documentation. You'll apply C# and use Copilot to implement and optimize API code for seamless back-end development. You'll work with relational databases in database integration and management using Entity Framework Core or EF Core. You'll set up databases, model data, and use SQL for queries and data manipulation, while Copilot helps you optimize SQL queries for performance and security. In full stack integration, you'll combine your front-end and back-end skills, setting up a full stack environment, connecting APIs, and managing data flow. To ensure smooth integration, you'll also explore Blazor API handling and build a full-stack project with Copilot. Next is security and authentication, where you'll learn to secure applications using ASP.NET Identity and role-based access. You'll cover user registration, token-based authentication, encryption, and JSON Web Tokens, or JWT. You'll use Copilot to write secure code and protect user data. In performance optimization and scalability, you'll focus on improving application performance through caching, query optimization, and load balancing. Copilot will help you fine-tune your code and database queries to handle increased traffic and efficiency. Then in data structures and algorithms, you'll explore the most efficient ways to handle and organize data. You'll implement arrays, linked lists, trees, and algorithms like sorting and searching to solve back-end problems, all while optimizing performance with Copilot. Next, in deployment and DevOps, you'll learn how to deploy and manage your applications using Azure Cloud Services. You'll set up a CI/CD pipeline, automate tasks, and monitor performance with Copilot, helping you streamline your deployment activities. Finally, you'll bring everything together in the capstone project by building a comprehensive full-stack application. You'll integrate front-end and back-end components, optimize performance, and demonstrate your ability to manage real-world development workflows. By the end of this program, you'll have mastered key full-stack development skills, from front-end technologies like HTML, CSS, and Blazor, to back-end frameworks, databases, and API integration. You'll be able to build scalable, secure web applications and optimize their performance, with Copilot helping you streamline and enhance your development process. We're excited to guide you on this journey towards becoming a full-stack developer. Welcome to the Foundations of Coding Full Stack course. Here you'll master building and managing every web application layer, from dynamic front-end interfaces to powerful back-end systems. We'll dive into API integration, version control, and security best practices, giving you the tools to create robust, scalable applications. By the end, you'll have the skills and confidence to bring full-stack projects to life and thrive in today's tech-driven world. We'll start by examining full-stack development, uncovering how it combines front-end and back-end expertise to create seamless applications. We'll explore the unique role of full-stack developers and the key tools and technologies that make them invaluable in the industry. Next, we'll strengthen your problem-solving skills, learning to tackle challenges with clear logic and strategic thinking. We'll explore powerful techniques to break down complex tasks and write efficient code ready for real-world use. Next, we'll explore client-server architecture, the differences between HTTP and HTTPS, and the principles of RESTful APIs and GraphQL. We'll also examine how to use WebSockets for real-time communication, enhancing dynamic application interactions. Then we'll explore the basics of databases, exploring relational and non-relational structures. You'll learn to design and manage database schemas effectively, and then focus on strategies to optimize database performance for maximum efficiency. Next, we'll cover the essentials of version control, exploring Git and GitHub for collaboration, and dive into advanced Git techniques. You will apply best practices to create a conceptual design for a full-stack application. Finally, you will apply coding concepts and problem-solving techniques, creating algorithms and flowcharts, use control structures and loops, and develop modular code, leading to a comprehensive coding project. Throughout this course, you'll master full-stack development, from building front-end interfaces to managing back-end systems. You'll learn to integrate APIs, optimize databases, and use version control, equipping you to create dynamic, scalable applications. We're excited to guide you in becoming a skilled full-stack developer. My name is Paul Party, and I'm your instructor for this course. I've been programming computers since I was in my teens. I love programming because it's like solving puzzles while designing and creating something amazing. My graduate degree is in philosophy, where I learned how to become a better thinker. When I program computers, I can apply many of the logic skills I learned in philosophy. Computer programming not only enables you to build cool software, but I believe it can help make you a better thinker. I started my software development career at Microsoft when the internet was just getting started, and I participated in the internet revolution firsthand. I managed software engineering teams that worked on desktop and web-based software. The internet gave software developers, particularly those working on user interface, incredible new opportunities. From mobile interfaces to websites, software developers are not only creating software that's functional, but also works of art. In my career, I managed and worked with teams at both Microsoft and PayPal that focused on customer-facing interfaces and learned how to make them great. I also spent part of my 20 years at Microsoft in training organizations, where I learned how to communicate challenging ideas to new learners. I also was fortunate enough to have spent 15 years teaching non-majors philosophy at a university in Seattle. This reinforced my ability to teach learners difficult concepts using ideas they can relate to. There's nothing more satisfying than to witness a learner having an aha moment where they understand something new. I'm really excited about this program. I believe Microsoft has some of the most powerful and exciting software development tools available, and I can't wait for you to learn about them. I'm confident you'll have many of the aha moments as you gain new skills and reinforce existing ones. The learning experience in this course is designed to give you a comprehensive understanding of key concepts through various learning methods. You'll be guided through interactive, engaging materials that help you build practical and theoretical knowledge. Whether you're interested in front-end, back-end, or full-stack development, this program has the tools to support your growth every step of the way. Throughout the course, you'll be introduced to core concepts and key ideas in videos. These videos are designed to help you understand definitions, processes, and essential steps clearly and concisely. You'll get to absorb foundational knowledge, setting the stage for deeper exploration as you move forward. And when you need step-by-step guidance, screencasts will provide you with a detailed practical view. These screencasts will show you exactly what's on the screen and how to work through specific coding tasks. The course also includes readings that reinforce the key ideas presented in the videos. These readings are more than just supplementary material, they're job aids. You can print them out and use them as a reference while working on assignments or activities, helping to apply what you've learned in real-world situations more easily. Small activities are included to help you check your understanding of key ideas. These activities provide quick, interactive opportunities to practice what you've just learned. After completing each activity, you can compare your work with a fully explained example and answer key. This ensures that you always know if your answer is correct. Practical experience doing tasks you would in a job within this field is essential, and that's where guided labs come in. These labs take you through the implementation of different concepts step by step. As you work, you'll receive feedback and helpful hints, ensuring you can get the help you need when you need it. It's the perfect opportunity to practice in a controlled environment while learning by doing. After completing the guided labs, you'll move on to independent projects, or you try it. This is where you'll put your skills to the test, applying what you've learned in the labs. You'll work through real-world problems, cementing your understanding of the course material. The course will culminate in a practical project leveraging Microsoft Copilot that you can use as a portfolio artifact when you begin your job search in this field. As you progress through the program, the portfolio pieces will become stronger and better representations of the authentic experience you've gained. They'll showcase your understanding of code and the ability to implement different concepts from the developer program. This course guides you step by step from understanding concepts through videos and readings to apply them in activities, screencasts, and labs. Each part of the course builds on the last, helping you gain knowledge and authentic experience. By the end, you'll have completed real projects that not only showcase your skills, but can also be included in your portfolio as you start your career. Everything you do here will prepare you for success as a developer. Let's get started.
Throughout this course, you'll complete several guided labs. These labs are meant to give you an opportunity to practice your newly learned skills in an environment where you can get help and feedback as you complete coding challenges. This video will describe how to complete the guided labs in this course. We will explore a guided lab together so that you'll know what to expect when you come to one later in the course. First, let's check the content leading up to a guided lab. This structured content ensures that you have exactly the skills you need to complete the task. In this instance, there is a practical application video that describes in detail how this concept is used in real-world situations. Following this practical application video, you can review a reading that explains the concept in detail so you can go through this content at your own pace. Next, you'll find a video that works through the guided lab itself. This video won't give you all the answers to the guided lab, but it will provide an overview of the upcoming questions and challenges. Lastly, we come to the guided lab itself. The guided lab is a simulated code environment where you can experiment with code and receive hints and feedback in a realistic coding situation. To start, I'll click Start. In this lab, step 1 is an introduction to if-else statements, so I'll click Begin. Below the simulated code environment, I can find the specific instructions for this lab. Declare the variable age as type int. Place your cursor into line 2, type your answer, and select Enter to check your work. Alright, I think I know this one. I'm going to type in INT and hit Enter. Great, I got that correct, and I got a bit of feedback about my correct answer. To move on, I click Continue. And these instructions say, prompt the user to enter their age, place your cursor into line 4, type your answer, and select Enter to check your work. This one is a little trickier. Let me try type your age. Got it. This feedback for my wrong answer points me in the right direction. Let's try that again. I'm going to erase what I had here and then enter your age. Perfect. I'll click continue. Let's try one more. Convert the input to an integer using int.parse and store it in the age variable. Place your cursor into line 6, type your answer, and select enter to check your work. I'm not totally sure here, so I'm going to click on hint and get some help. And the hint says use console.readline and then an open and close parentheses, display a message asking their user for their age. Great, that helps. I'm going to click continue and type in console.readline. And I've got it. That's how you work through a guided lab. Some questions will require more complex code to complete, so make sure you're using the hint function when you need it and reviewing the feedback provided for your right and wrong answers. Have fun completing these coding challenges that put your new skills to work.
In today's rapidly evolving tech landscape, artificial intelligence plays a key role in making development more efficient and intelligent. That's where Microsoft Copilot comes in. Microsoft Copilot is a powerful AI-driven tool that can assist developers in writing, optimizing, and debugging code. In this course, you'll leverage Copilot as a thought partner and a code-generating assistant, helping you solve problems, generate code snippets, and enhance your projects. The goal is to provide you with hands-on experience using a tool that real-world developers use to improve their workflow. In the last module of this course, you'll engage in videos, screencasts, guided labs, and independent projects that integrate Copilot. These labs will take you through how to use specific prompts to generate code, optimize solutions, and solve problems. You'll be shown step-by-step how to leverage Copilot's capabilities to strategically approach the final project. During the guided labs, you'll get hands-on experience working with Copilot. These labs are structured to show you how to craft effective prompts and work with Copilot's code generation features. You'll use it to assist in writing code, refining your solutions, and debugging. This practice will prepare you for the independent work you'll do in the final project. After the videos, screencasts, or guided labs, you'll move on to independent activities where you'll take control. Here you'll use Copilot to assist with various aspects of the project. You'll be making strategic decisions, but Copilot will support you by generating code, suggesting optimizations, and helping you troubleshoot. This prepares you to work more independently while still having the power of AI to assist. The final project will combine everything you've learned in the course, and you'll have Copilot as a key tool in your development toolkit. You'll use Copilot to help you generate and refine code as you combine the concepts from earlier lessons. The project is a portfolio-ready artifact showcasing your coding skills and your ability to leverage AI in modern development workflows. To succeed in the final module, actively engage with the guided labs and practice using Microsoft Copilot effectively. The videos and prompts will take you through Copilot and equip you to apply it strategically and independently. By the end of the course, you'll be fully prepared to complete the final project and demonstrate your skills using traditional coding and AI-assisted workflows. Welcome to the course. In this video, we will discuss how you can make the most of each part of the course to set yourself up for success. Whether you watch the videos, complete activities, or work through hands-on labs, each element has been designed to help you master the skills you need to become a confident and capable developer. The first step in every lesson is the videos. You'll be introduced to new concepts, definitions, and key ideas. Watch these carefully and take notes on the important points. The videos provide the foundational knowledge you'll need to build on, so don't skip them. They'll give you the context to understand everything that comes next. After each video, complete the readings. These readings reinforce the key ideas you've just learned and can serve as job aids. I recommend printing out the readings or saving them for quick reference. They'll be extremely helpful when completing activities, working on projects, or just needing a refresher. They're not just supplementary, they help you apply what you've learned to real-world tasks. Throughout the course, you'll find small but impactful activities. These quick exercises allow you to check your understanding of key ideas. Don't rush through them. Take the time to work through these activities thoughtfully. After each, compare answers with the answer key to check how well you understand the material. This is your chance to practice without pressure. At the end of each lesson, you'll encounter practice quizzes. These quizzes are a great way to ensure you fully grasp the concepts from the videos and the readings. Use these as a checkpoint to assess how well you retain the information. If you find yourself struggling, review the videos and readings again. The goal is to build confidence and solidify your understanding before moving forward. When you need to see the material in action, screencasts guide you. These videos show you exactly how to work through certain tasks step by step. If you ever feel stuck or unsure about applying a concept, watch the screencasts and follow along. This hands-on guidance is invaluable for understanding how the code works in real time and applying what you've learned. At the end of each module, there will be graded quizzes. These are an important part of your success as they allow you to demonstrate mastery of the material. These quizzes build on the practice quizzes, and they're a great way to ensure you're ready to move on to more advanced concepts. Treat these quizzes as milestones. Passing them means you're fully prepared for the next challenge. The guided labs are where you'll take the concepts from the lessons and apply them in a controlled, hands-on environment. These labs will take you step by step through tasks, including helpful feedback and hints. The more effort you put into the labs, the more you'll get out of them. It's all about learning by doing, so take your time and ensure you understand each step before moving on. After you've completed the guided labs, it's time to test your skills with independent projects or U-try-its. This is where you'll apply everything you've learned without step-by-step instructions. These projects are a great way to gauge how far you've come and to put your knowledge to the test. Don't worry if you feel challenged, that's part of the learning process. By completing these projects, you'll reinforce your skills and build confidence. Finally, at the end of the course, you'll complete a culminating hands-on project that you can use as a portfolio artifact. This project will showcase the skills you've gained throughout the course and give you something tangible to present to potential employers. As you progress through the program, these portfolio pieces will become stronger representations of your hands-on experience and understanding of key concepts. Success in this course comes down to using all the tools available. Watch the videos carefully, engage with the readings, complete the activities and quizzes thoughtfully, and take full advantage of the screencasts, labs, and projects. Each element of this course is designed to help you master the material step by step. By the end, you'll have a solid understanding of the concepts and real projects to prove your skills. Remember to persist, take your time, and you'll be ready for a successful career in development. Every successful coding project starts with a solid plan. By carefully organizing and outlining your project, you'll ensure all the parts come together smoothly. This process may seem like extra work, but it lays the foundation for success. With this plan in place, a developer can then write, debug, and optimize code to build dynamic, responsive applications. In this video, we will explain the end-of-course project. This project simulates real-world software development. You'll start by designing and planning an application, then building the basics, debugging, and refining your code as it grows more complex. By the end, you'll integrate everything into a polished, final product. The goal is to experience the full coding process, writing, fixing, and improving your code. Before writing any code, you'll plan and design an application. This will involve defining project requirements and objectives and creating a design outline. With a plan in place, you'll then write the core features of your application. This step establishes basic functionality that will be expanded later. Once the core features are in place, errors will naturally appear.
You should then focus on debugging, identifying issues, and ensuring everything works correctly. Refining your code at this stage is critical for smooth performance. As your system grows, debugging manually becomes time-consuming. Here we'll use Microsoft Copilot to help find and fix errors quickly. Copilot offers AI suggestions that streamline the debugging process and improves system performance. By the end of the project, the final product will be a polished system ready for use. In this project, you will go from planning to building, debugging, and refining your code. Following a structured process, you will create a functional system that mirrors the real-world development cycle. This experience will teach you the value of careful planning, problem solving, and using tools like AI to optimize your work.
Welcome to Introduction to Full Stack Development. In this module, you'll learn how full stack developers bridge front-end and back-end work, mastering key tools and technologies to become versatile and highly valued in the tech world. We will begin by defining full stack development and its scope within the software lifecycle. We'll identify the key roles of full stack developers, comparing their work with front-end and back-end development, and explore the essential tools and technologies they use. Next, we'll explore full stack developers' key roles and responsibilities and understand their importance in the industry. We'll also examine the growing demand for these versatile professionals and the exciting career opportunities they offer. Then we'll compare full stack development with front-end and back-end roles, exploring how each contributes uniquely to software projects and how full stack developers integrate these skills to create cohesive solutions. Next, we'll dive into the essential technologies and tools that full stack developers use, covering both front-end and back-end technologies critical for building complete and dynamic applications. By the end of this module, you will have the knowledge and skills to excel as a full stack developer, seamlessly integrating front-end and back-end technologies to build dynamic applications. Let's get started. Imagine you're building a website that could shape the future of online learning. As a full stack developer, you're not just crafting the user interface that students interact with. You're also engineering the back-end process that powers it. Full stack developers hold the unique ability to understand every aspect of an application, from what the user experiences to how data is managed behind the scenes. In this video, we'll define full stack development. And we'll further explore full stack development by examining the principles it follows. But before we explore full stack development and its principles, let's take a moment to understand the foundation, front-end and back-end development. These are the core areas where full stack developers spend most of their time, so let's break them down. The front end is the part of the application that runs directly on the user's device, whether it's a browser, mobile app, or desktop app. It's where the user interacts with the application. This interaction includes everything they experience and click on: the layout, text, images, buttons, and forms. On the other hand, the backend is the part of the application that runs on the server. It's where the magic happens behind the scenes, managing databases, processing requests, and ensuring that everything functions smoothly. For instance, when you submit a form on a website, the backend processes your input and retrieves the necessary data from the server to display it on the front end. Now that we've laid the groundwork by defining front-end and back-end, we can explore how full-stack developers integrate these areas. This integration allows full-stack developers to supervise and optimize the entire application, ensuring that the user-facing elements and the underlying processes work in harmony. Full-stack development is the development of both the front-end and the back-end of a web application. The role demands a broad understanding of the technologies involved and how they will work together to deliver a seamless user experience. For example, a full-stack developer might design a website's interface while also writing the server-side code that powers its functionality. By mastering both sides of the application, full-stack developers ensure that all parts of the system work together, providing a smooth and efficient user experience. Understanding full-stack development gives a glimpse into its scope. Next, we'll explore the principles that empowers full-stack developers to manage both front-end and back-end processes effectively. These principles ensure that all elements, from front-end interfaces to back-end processes, integrate smoothly to deliver a cohesive user experience. Full-stack developers should master both front-end and back-end, deliver end-to-end solutions, optimize performance, prioritize security, ensure accessibility, and embrace responsive design. We'll discuss each of these principles in detail, starting with mastering both front-end and back-end. First, full-stack developers need to master both the front-end and back-end to be effective. This means having the ability to build user interfaces with technologies like HTML, CSS, and JavaScript to create an intuitive experience. It also involves being able to handle server-side tasks like database management and API integration using tools like C#, Python, or Ruby. Mastering both the front end and back end equips full-stack developers with the skills needed to deliver end-to-end solutions. Full-stack development prioritizes creating smooth interactions between the user interface and the server. This means ensuring that data flows seamlessly from the front end to the back end and back to the user. For example, a full-stack developer might focus on ensuring that when a user inputs their credit card information, that data is correctly processed quickly and the user immediately receives a confirmation message. Delivering end-to-end solutions requires full-stack developers to optimize performance. By fine-tuning every layer from the user interface to the back-end database, full-stack developers ensure that the application runs efficiently, providing users with a fast and responsive experience. Performance refers to how quickly and efficiently the site or application responds to users' requests. For example, when you click on a button on a website, high performance ensures that the page loads instantly, providing a smooth experience. As full-stack developers fine-tune the system for speed, they must also embed robust security measures at every layer to protect against threats. This ensures that the application remains safe and reliable. Security refers to the measures and protocols developers implement to protect websites and applications from unauthorized access, data breaches, and other cyber threats. As a full-stack engineer, you must ensure that every layer of your application is protected, from the database to the user interface, against potential threats. Just as security safeguards the application, ensuring accessibility broadens its reach. Full-stack developers must design with inclusivity in mind, making sure their secure, high-performing applications are usable by everyone. Accessibility ensures that websites and applications are usable on a variety of devices by everyone, regardless of their abilities. Full-stack developers make websites and applications accessible by creating interfaces that can be easily navigated and understood by everyone, including people with disabilities. Building on the principle of accessibility, responsive design is essential to ensure that applications adapt seamlessly to various devices. By embracing responsive design, full-stack developers make their applications flexible and user-friendly, regardless of screen size or orientation. Responsiveness refers to the ability of a website to change its layout and content to fit different screen sizes and orientations. Responsiveness ensures that users have an easily navigable experience on any device, be it a desktop, laptop, tablet, or smartphone. In this video, we've defined full-stack development and discussed its principles. By understanding both front-end and back-end development and applying these core principles, full-stack developers can create cohesive, high-performing, and inclusive web applications that meet the diverse needs of users. Imagine you're working at a small startup and your job is to build a web application that could change how people use technology. You need to create a smooth, user-friendly front end and make sure the back end can handle thousands of transactions per second without any issues. In this fast-paced environment, mastering full-stack development enables the delivery of a product that can succeed in a competitive tech market. In this video, we will explain the best practices of full-stack development. Full-stack development is the development of both the front end and back end of a web application. To create efficient and effective web applications, full-stack developers follow best practices. These best practices can be grouped into two main categories: technical skills and development practices. First, we'll explore the technical skills that every full-stack developer needs. Technical skills include proficiency in front-end and back-end technologies, familiarity with version control systems, and knowledge of database management. Let's explore each of these in more detail. First, full-stack developers must be proficient in both front-end and back-end technologies. Being proficient means you're not just familiar with these technologies, you're skilled and comfortable working with them every day. Front-end technologies include HTML, CSS, and JavaScript. These technologies are the building blocks of the web and enable you to create engaging user interfaces. On the back end, it's all about server-side languages like C#, Python, Ruby, or Node.js. Mastery of these languages allows you to build robust server logic that supports the entire application. Keep in mind that you do not need to know all of these. Next, let's focus on version control systems. Imagine you're working on a team project and suddenly you need to revert to an earlier version of your code. With version control systems like Git, this is simple and efficient, saving you hours of potential rework. Version control systems are tools that help developers track and manage changes to their code. These systems allow multiple developers to work on the same code base simultaneously without conflicts. Another critical technical skill is knowledge of database management. Database management involves organizing and storing data in a way that can be easily accessed, managed, and updated. You should be familiar with SQL databases like MySQL, as well as NoSQL databases like MongoDB. Proper database management ensures that your application can store and retrieve data efficiently and securely. With a strong technical foundation in place, let's now explore the development practices that will help you build secure, maintainable, and efficient applications. These include writing clean, maintainable code, applying security best practices, debugging and optimizing code, and continuous learning. Let's explore each of these in more depth. First, writing clean, maintainable code is crucial. Clean code refers to code that is easy to read, understand, and modify, while maintainable code is code that can be easily updated or expanded upon by others. Full-stack developers writing clean, maintainable code means following coding standards, writing meaningful comments, and organizing your code logically. Clean code reduces bugs and makes it easier for teams to work together, ensuring long-term success. Next, let's focus on applying security best practices. Security best practices are guidelines that help protect software and data from unauthorized access, breaches, or other threats. As a full-stack developer, this means implementing data encryption, secure authentication, and input validation to protect your applications from threats. Now let's discuss debugging and optimizing code. Debugging focuses on identifying and fixing errors in code, while optimization enhances code efficiency and performance. This includes reducing load times, improving database queries, and simplifying your code. Efficient code leads to better performance, which is crucial for user experience. Finally, let's talk about continuous learning. Continuous learning refers to the ongoing process of developing new skills and knowledge. In the fast-paced tech industry, staying updated with latest tools and trends is essential for career growth. As a full-stack developer, you should always be exploring new technologies, frameworks, and best practices to stay competitive. Engaging in continuous learning helps you adapt to changes and advances in the field, ensuring that you remain an effective developer. In this video, we explored the best practices of full-stack development. We discussed the importance of proficiency in front-end and back-end technologies, writing clean and maintainable code, familiarity with version control systems, knowledge of database management, applying security best practices, debugging and optimizing code, and continuous learning. By mastering these best practices, you'll be well equipped to tackle the challenges of full-stack development. Imagine you're working on a team where everyone has a specialized role. Some focus on the visuals, others on the behind-the-scenes logic. But who ensures that all these pieces fit together? That's where the full-stack developer comes in. The role of a full-stack developer is one of the most versatile and essential in the tech industry today. Full-stack developers are skilled professionals who bring together front-end and back-end development, ensuring the applications are both visually appealing and functionally robust. In this video, we will identify the key roles of full-stack developers in the industry. We'll also explore that role in more detail by examining the responsibilities full-stack developers have. As we further explore the full stack developer's world, let's start with our primary role. The primary role of a full stack developer is to bridge the gap between the front end and back end development. They understand both sides and ensure all components of an application work together. Now that you understand the primary role of a full stack developer, let's explore specific responsibilities that enable full stack developers to fulfill this role. Full stack developers can take on several key responsibilities within a development team, which involve working across different parts of the technology stack to ensure the application runs smoothly. These responsibilities include front-end development, back-end development, database management, security, DevOps, and testing and debugging or repairing issues in the code. Let's examine each of these responsibilities in more detail, starting with front-end development. A well-crafted user interface is crucial for any application, and full-stack developers take on this challenge by being responsible for front-end development. Front-end development involves building and maintaining the user interface of one or more applications. In this role, developers implement the designs and functionalities of a website or application using languages such as hypertext markup language, also known as HTML, to structure the content of a web page. They use cascading style sheets, also known as CSS, to style that content, making it visually appealing. Finally, they use JavaScript to add interactive elements like form validation or dynamic content loading. For example, full-stack developers might create a responsive navigation bar that works well on both mobile devices and desktops. While a seamless user interface is important, it's the back-end systems that provide the foundation for front-end functionality. Let's explore how full-stack developers ensure that these two sides work together. This is where the responsibility of back-end development comes in, focusing on the server-side infrastructure that powers the application. In this role, they manage databases, servers, and APIs to ensure that the back-end communicates effectively with the front end. For example, setting up an API that allows the front end to get user data from the database. To ensure that the backend operates smoothly, full-stack developers must also manage the application's data. This leads to another crucial responsibility, database management, where full-stack developers design and manage the databases that store the application's data. They ensure that data is stored securely and can be retrieved efficiently by the application. For instance, designing a database to store user information securely and retrieving it when needed for user authentication. With data in place, the next critical focus is on safeguarding the entire system. Security becomes crucial, and full-stack developers take on the responsibility of protecting data and maintaining user trust. In this role, they implement security measures such as encryption, secure authentication, and authorization to safeguard the application. For example, setting up user authentication and encrypting sensitive user data to protect unauthorized access. With security in check, the next major challenge is bringing the application to life through deployment. Here, full-stack developers can take on DevOps responsibilities where they handle the deployment of applications to production environments. This involves setting up CI/CD pipelines to automate application deployments to a server. For example, using Docker to containerize an application and deploying it to a cloud server. Even after deployment, the job is far from over. Ensuring that applications run flawlessly requires continuous testing and debugging. Full-stack developers as problem solvers take on the critical task of identifying and fixing issues across both the front end and the back end. For instance, debugging an issue where a front-end feature is not displaying correctly due to an error in the back-end logic. Each responsibility builds on the next to help full-stack developers fulfill their primary role of connecting front-end and back-end development. In this video, you learned about the key roles and responsibilities of full-stack developers in the industry. Their ability to work on both front-end and back-end tasks make them invaluable in ensuring the seamless integration and functionality of applications. Understanding this role and its responsibilities can help you appreciate the versatility and importance of full-stack developers in the tech world. As a full-stack developer, your work shapes the digital world, from creating user-friendly interfaces to powering the engines behind them. In today's tech-driven landscape, your versatile skills are crucial. whether it's for a startup app or a corporation's systems. Your role is more important and exciting than ever. In this video, we will describe the industry demand for full-stack developers and potential career paths. A full-stack developer has the skills to build and maintain every aspect of a web application, from the front end, which users understand and interact with, to the back end, which processes logic, data, and security. Whether you're interested in building dynamic websites, developing powerful applications, or even shaping the architecture of software systems, there's a path for you. The roles we'll cover include full-stack developer, full-stack application developer, software architect, and DevOps engineer. Understanding each of these roles will give you a clearer picture of your potential career path. We'll start by exploring the role of a full-stack web developer. As a full-stack web developer, your focus is on creating and maintaining websites, ensuring they are functional and aesthetically appealing, and optimizing performance. But what if you're more interested in developing software beyond just websites? The role of a full-stack application developer might be for you. A full-stack application developer is responsible for building and maintaining software applications that can be used on desktop computers, mobile devices, or web platforms, giving you the opportunity to work across different mediums and reach a wider audience. As you gain experience developing websites or applications, you might naturally progress towards a more strategic position. This brings us to the role of software architect. As a software architect, your focus shifts from building individual components to designing the overall structure of applications, ensuring they work seamlessly. Full-stack developers are well suited for this position because their deep understanding of both front-end and back-end technologies equips them to make informed decisions about how each piece of the application fits into the larger picture. On the other hand, if you find yourself drawn to the deployment and operations side of software, you might consider the role of a DevOps engineer. DevOps engineers manage application deployment, infrastructure, and maintenance. Full-stack developers are well suited for DevOps because their broad expertise across the application lifecycle, from development to production, enables them to specialize in ensuring that systems are deployed smoothly and operate reliably. Many different industries, including technology, finance, healthcare, and e-commerce, and entertainment, need full-stack developers. Let's explore how these industries need full-stack developers, starting with the technology industry. From startups to large corporations, tech companies are major employers of full-stack developers. Your ability to create complete digital products makes you a valuable asset. In this industry, you might be working on an internal tool for the company or an end product for users. Financial institutions, for example, require robust and secure applications for everything from online banking to investment management. Full-stack developers play a key role in building and maintaining these systems. And full-stack developers in healthcare industry build digital solutions for patient management, telemedicine, and data analysis. In a similar way, online retailers need full-stack developers to build and maintain their websites, manage inventory systems, and provide a seamless shopping experience for customers. Full-stack developers are also vital in the entertainment industry. From streaming services to gaming platforms, full-stack developers are needed to create engaging and scalable digital experiences. With these insights in mind, let's now explore the specific career opportunities available to full-stack developers. The choice between freelancing, working at a startup, or joining a large corporation can significantly impact your experience. These environments differ greatly in terms of team size, the speed of work, and the level of responsibilities you shoulder. Let's explore these opportunities in more detail, starting with freelancing. Many full-stack developers choose to work as freelancers or consultants, offering their versatile skills to a range of clients. As a freelancer, you'll have a large number of responsibilities, but have a lot of flexibility in terms of the types of projects you work on. For example, a freelance full-stack developer could take on specific gaming application projects for different companies, providing comprehensive development services on a contract basis. If running your own business doesn't seem attractive, but you want to experience many different responsibilities, you might enjoy working at a startup. Full-stack developers are highly valued in startups due to their ability to handle multiple responsibilities. Startups are often fast-paced and employ work on a number of different tasks. For example, a startup might need a full-stack developer to build a new product from scratch, manage implementing a new marketing tool, or secure the company's cloud servers. This diverse range of tasks can be incredibly rewarding, but if you prefer a more structured environment with the opportunity to work on a large team, you might consider working at a corporation. Large tech companies often seek full-stack developers to build their products and maintain and expand their platforms. Understanding the types of roles, job types, and industries full-stack developers can get hired into is important as you consider the role you might want in the future. In this video, we explored the industry demand for full-stack developers, the key roles in industries, and the various career paths available. Understanding these opportunities can help you navigate your career in full-stack development. Think about the last website or app you used. Was it beautiful? Did it load quickly? These experiences are the result of a well-coordinated front end and back end. But what exactly do these roles involve, and how do they work together to create the digital products we rely on every day? Full-stack developers bridge the gap between front end and back end development, ensuring that the user interface is both beautiful and functional, while the underlying systems work smoothly. Understanding both sides is crucial for delivering a complete, user-friendly experience. In this video, we will compare the roles and responsibilities of front-end and back-end developers. First, let's explore why this comparison is helpful for full-stack developers. As a full-stack developer, you're expected to handle tasks from both sides, so comparing them helps you grasp the full scope of your role. By comparing them, you'll get a clearer picture of what each side involves, helping you to balance your work and identify areas to improve. This comparison also enhances collaboration. Knowing the distinctions allows you to communicate better with front-end and back-end team members, leading to smoother teamwork. Let's define both front-end and back-end development. Front-end development is the practice of building the visual and interactive elements of a website or web application that users directly interact with. But what about the parts of the application that users don't interact with? That's where back-end development comes in. Back-end development is the practice of building and managing the systems that power apps and websites, such as data processing, storage, and application logic. Given these differences, what are the responsibilities of front-end and back-end engineers? Let's start with the responsibilities that front-end engineers and back-end developers have in common. Front-end, back-end, and full-stack developers spend their days on three important tasks: coding, testing, and debugging. Even though both front-end developers and back-end developers spend a large portion of the day coding, their focus and the technologies they use are different. When we talk about coding, we are referring to implementing the front-end designs, functionalities, and back-end systems of a website or application using programming languages. For example, front-end developers implement an application's visual and interactive elements using languages such as hypertext markup language, or HTML, to structure a web page's content. Cascading style sheets, or CSS, to style that content, making it visually appealing, and JavaScript to add interactive elements like form validation or dynamic content loading. And most backend engineers spend a significant portion of their day writing server-side code. Writing server-side code involves creating the logic that powers the application. Backend engineers write server-side code in languages like C#, JavaScript, Ruby, and Python. After completing the coding phase, the next crucial step is testing, where both front-end and back-end developers ensure the code functions correctly, interacts smoothly with other parts of the application, and meets user experience standards. Developers conduct different types of tests, such as unit tests for specific sections of code, integration tests to ensure parts work together, and user interface tests to confirm their sites behave correctly in real-world conditions. After testing, developers spend time debugging. This means finding and fixing the bugs or issues discovered during testing to make sure everything works correctly. Along with these common daily tasks, front-end developers and back-end developers have specific responsibilities. While front-end developers focus on responsiveness, accessibility, and security, back-end developers take on responsibilities such as API development, data management, and system reliability. Let's go into more detail about each of these responsibilities, starting with the front-end responsibility of responsiveness. Responsiveness refers to the ability of a website to change its layout and content to fit different screen sizes and orientations. Responsiveness ensures that users have an easily navigable experience on any device, be it a desktop, laptop, tablet, or smartphone. Now that we've explored how front-end developers ensure websites adapt to different devices, let's consider another important responsibility: accessibility. Accessibility ensures that websites and applications are usable by everyone, regardless of their abilities. Front-end developers make websites and applications accessible by creating interfaces that can be easily navigated and understood by everyone, including people with disabilities. Similar to how responsiveness and accessibility enable a diverse range of users to use websites and applications, front-end developers are responsible for security, which ensures these users can safely perform a growing and diverse range of tasks online. Security refers to the measures and protocols developers implement to protect websites and applications from unauthorized access, data breaches, and other cyber threats. Now let's explore some of the back-end developers' primary responsibilities, starting with API development. First, back-end engineers are responsible for API development, which includes creating, documenting, and maintaining APIs. An application programming interface, or API for short, is a set of rules and tools that allow different software applications to communicate with each other. Backend developers enable seamless data exchange and functionality across various systems by ensuring that APIs are efficient, secure, and well documented. Next, backend developers are also responsible for data management and security. Data is information that is collected, stored, and used by computers, often in the form of text, numbers, or other formats, to drive decisions and operations in various applications. Data management and security involves managing the flow of data, storing data efficiently, and protecting sensitive data. Finally, backend engineers are responsible for system reliability and maintenance. This includes robust error handling, logging, regular maintenance, and updates. These practices help backend engineers quickly identify and address issues, minimize downtime, ensure a stable user experience, and keep the system secure and functioning at its best. While their tasks and responsibilities differ, both front-end and back-end developers contribute to robust user-friendly applications. In this video, we compare the roles and responsibilities of front-end and back-end developers. Each role is vital to the development process, and their collaborative efforts ensure the creation of functional, user-friendly, and robust applications. As a full-stack developer, understanding these roles not only makes you more versatile, but also equips you to create more cohesive and high-performing applications. Have you ever wondered how websites and apps work so seamlessly? The way the user interface operates and the processes being executed in the background are interconnected in ways you might not even realize. This connection is at the heart of full-stack development. In this video, we'll explain the integration of front-end and back-end development in full-stack development. Full-stack development is the development of both the front-end and back-end of a web application. Full-stack developers have the skills to work across both the front-end and the back-end, ensuring that the user interface, referred to as the UI, and the underlying systems are seamlessly connected. This begins with front-end development, which focuses on creating responsive and interactive user experiences. After establishing a solid and user-friendly front-end, the focus shifts behind the scenes to the back-end, where full-stack developers manage the core functionality that powers the entire application. While front-end and back-end development addresses different aspects of the application, they need to be seamlessly connected. This is where integration comes into play. Most full-stack developers excel at integrating the front-end with the back-end APIs and services, ensuring that the user interface works seamlessly with the underlying logic. To understand how this integration happens, let's explore APIs and services in more detail. An application programming interface, or API for short, is a set of rules and tools that allows different software applications to communicate with each other. full stack developers not only develop APIs, but also ensure they are effectively integrated into the overall application architecture. These APIs often work in conjunction with services, which are server-side functions that handle specific tasks like processing requests, managing data, or handling authentication within an application. By defining the data architecture and establishing communication protocols, full-stack developers ensure that the front-end and back-end work together smoothly, creating a cohesive and functional application. With these components defined, let's now explore how full-stack developers bring everything together through a typical development workflow. To build an application, full-stack developers typically begin with planning and design, next development, then continue to integration and testing, and finally deployment. A successful development project can't begin without planning and design. Here the developer gathers requirements, collaborates with stakeholders, and defines the technical specifications. Once the design is in place, they focus on front-end development using tools like HTML, CSS, and JavaScript frameworks to build the user interface. Simultaneously, they work on the back end, setting up the server, creating the database, and implementing the application's logic. After both the front end and back end are developed, the focus shifts to integration. The developer connects the front end with the back end APIs and services, ensuring smooth data flow and error handling. Once all the connections are in place, testing can begin. During this stage, the developer conducts thorough tests to identify and fix any issues. Once everything is working perfectly, the application is deployed and the developer continues to monitor its performance, making updates as necessary. Throughout this workflow, full-stack developers focus on integrating the front end and back end to create cohesive, functional applications. By understanding and working across both areas, full-stack developers ensure that everything works together, providing users with a smooth and engaging experience. In this video, we explained the integration of front-end and back-end development in full-stack development. We covered both front-end and back-end development and how full-stack developers integrate the two. We also explored the workflow full-stack developers use to integrate front-end and back-end development to create cohesive applications. In the digital world, front-end technologies help developers build visually appealing and engaging websites and applications, ensuring they are accessible, user-friendly, and work smoothly. In this video, we will list the key front-end technologies used in full-stack development. The front-end technologies used in full-stack development include coding languages, frameworks, and libraries. First, let's start with a definition. Coding languages are the tools developers use to give instructions to computers. It's important to understand that computers can only understand binary code, which is a series of ones and zeros. Most coding languages are designed in a way that makes them simpler for humans to write, but also easier for machines to interpret. In this way, the computer takes the code you write and translates it into something that it can understand, which is binary code. Now that we understand what coding languages are and how they work, let's dive into the foundational languages of front-end development: HTML, CSS, and JavaScript. Let's explore each of these languages in more detail, starting with HTML. HTML is the standard markup language for creating web pages. It provides all the structure that holds all content together. Whether it's text, images, or interactive features, HTML organizes elements and gives you browser-specific instructions on how to display them. Elements are web page components such as paragraphs, links, and media files. HTML defines these elements using a system of tags. So how does this work in practice? Each element in HTML is wrapped in tags that mark the beginning and end of the content. An element usually consists of a start tag, content, and an end tag. For instance, to create a paragraph in HTML, you would write it like this: open bracket, P, close bracket. This is a paragraph. Open bracket / P, close bracket. The P tag tells the browser that the text inside should be treated as a paragraph, and the closing P tag denotes that the paragraph is ended. Now, while some elements are straightforward like this example, others come with additional options known as attributes that provide extra details or settings. Attributes are often used to specify things like an image's source, a button link, or an element's styling. Let's explore an example of how attributes work within a link element. A link element starts with an opening tag, A. This tag stands for anchor, which is used to create hyperlinks. Next, we add an attribute. In this case, the href attribute specifies the URL that the link will navigate to when clicked. For example, href https www.example.com. The attribute is followed by the content that users will click on. In this example, visit example website. Finally, we close the link with the end tag, /a. This marks the end of the link element. Now you know how to add elements to a web page, but what if you want to change their size, font, or color? HTML style attribute can modify font styles and colors, but it's inefficient for large websites. You need to style each element individually, making updates repetitive and time-consuming. This is where CSS comes in. CSS separates content from design, allowing you to style multiple elements consistently, making your code easier to maintain and update. CSS is the language used to style HTML elements, changing their appearance and layout. For example, using CSS, you can transform a basic HTML button into a stylish interactive element by changing its color, border, and adding shadows. When styling with CSS, you use a combination of selectors, properties, and values. First, think of the selector as the target, the HTML element you want to style, such as a paragraph or a link. Then the property is the specific style you want to apply, such as the color or font size. And finally, the value is the exact setting you choose, like blue or 16 pixels. Let's put this into practice. If you want to make all the links on your website blue with a 15 pixel font size, you'd write the CSS code like this. A, open bracket, color blue, font size 15 pixels, close bracket. Here, A is the selector targeting all links. Color is the property and blue is the value you're applying. After using CSS to design your website's visual aspects, the next step is to make it interactive. This is where JavaScript comes into play. JavaScript is a programming language that enables interactive websites. To understand how JavaScript works, it's essential to get familiar with its two fundamental building blocks, statements and expressions. Statements are instructions that tell the computer what to do. They usually perform an action like declaring a variable or calling a function. For example, to store the string Alice in a variable called name, you would write let name equal Alice. An expression is a piece of code that the computer can evaluate to produce a result, such as a math equation or a logical comparison. For example, to check if 5 is greater than 3, you would write 5 greater than symbol 3. The output would be true because 5 is indeed greater than 3. Mastering these three languages is just the beginning. To truly excel in front-end engineering, you need also to become proficient in key technologies such as frameworks and libraries. Let's examine these essential technologies, focusing on frameworks first. Frameworks are pre-written code structures that offer a standardized way to build and organize code. They provide a foundation for building applications, making development faster and more efficient. Popular front-end frameworks include React, Angular, and Vue. Next, let's explore libraries, which allow engineers to control the application's flow and custom code and select only the components they need. Libraries are collections of pre-written code used to perform common tasks. They often include objects and functions used individually to solve specific problems. Popular libraries include Node.js, React.js, and Vue.js. These front-end technologies make applications functional and ensure they are visually appealing and user-friendly, enabling full-stack developers to create cohesive and engaging user experiences. In this video, we listed the key front-end technologies used in full-stack development. Understanding and using these technologies is key to building effective and engaging user interfaces. Imagine you're working on a popular e-commerce platform where thousands of users browse products add items to their cart, and complete purchases all at once. Behind the scenes, complex processes manage user requests, interact with databases, and ensure that every transaction is smooth and secure. To build such a system, you need a strong foundation in backend technologies. These are the invisible engines that power the logic, database interactions, and API integrations essential for your application to function seamlessly. In this video, we will list the key backend technologies used in full-stack development. In full-stack development, backend technologies handle the heavy lifting behind the scenes. They manage the server-side logic that processes user requests, ensure smooth communication with databases, and delivers the right content to the front end, all essential functions that keep your web application running smoothly. The backend technologies used in full-stack development include coding languages, frameworks, and libraries. Let's explore specific tools developers use, beginning with the coding languages that form the foundation of server-side programming. These are the core tools that backend developers use to write the code that powers the server side of a web application. Some of the most powerful and commonly used languages in backend development include C#, Ruby, Python, and JavaScript. C# is a modern, object-oriented programming language that's well suited for developing web APIs and Windows applications. It's highly valued for its ability to handle complex server-side logic. Object-oriented programming, or OOP, is a programming style that organizes code into objects, self-contained units that represent different parts of an application, such as users, orders, or products. This approach makes the code more modular, maintainable, and scalable. When you're building a web application, you might use C# to create a robust API that handles everything from user authentication to data retrieval from a database. For instance, imagine an online store. C# can be used to create an API that processes customers' orders, calculates shipping costs, and it interacts with the inventory database to update stock levels, all in real time. Just as C# is valued for its robustness in API development, Ruby shines in its ability to simplify the coding process, making it another powerful tool for server-side development. Ruby is a versatile programming language known for its simplicity and readability. This makes it ideal for building web applications quickly with clean, maintainable code. Its syntax is designed to minimize complexity, enabling developers to focus on solving problems efficiently. For instance, when developing a social media platform, Ruby allows for the rapid prototyping of essential features like user profiles, friend connections, and real-time messaging, all while maintaining code clarity. Python is another powerful language that excels in handling complex tasks such as business logic, data analysis, and machine learning, making it an ideal and essential tool in backend development. It is frequently used in systems where large-scale data processing or intricate algorithm implementation is required. For instance, imagine developing a financial application that needs to analyze stock market trends and provide real-time investment advice. Python's extensive libraries and frameworks are perfectly suited for processing vast data sets and generating accurate predictions, ensuring reliable insights for users. JavaScript, commonly associated with front-end development, is also a powerful tool for the backend thanks to Node.js. Node.js enables developers to use JavaScript to handle tasks like processing requests, managing databases, and generating dynamic content, all in a language they're already familiar with. Node.js is a runtime environment that enables JavaScript to run on the server, allowing for the creation of fast and scalable applications. But what is a runtime environment? A runtime environment is a system that provides the necessary tools and settings for code written in a particular language to run and perform its tasks. Node.js enables developers to build fast and scalable network applications. For example, imagine developing a real-time chat application. Node.js is perfect for this because it's designed to handle multiple connections simultaneously, allowing the chat to update instantly for all users without delays. While coding languages are essential, frameworks and libraries help developers build applications faster and more efficiently. Let's examine these technologies and see how they fit into the bigger picture of backend development, starting with frameworks. Frameworks provide a developer with a standardized approach to building and organizing code, streamlining the development process, and ensuring consistency across projects. Backend frameworks like Express, Django, and Ruby on Rails provide developers with standardized methods for organizing code and managing server-side functions more effectively. Let's explore each of the frameworks, starting with Express.js. Express.js is a tool that helps developers build websites and apps using Node.js. It makes creating both simple and complex web apps easier by handling common tasks like routing, deciding how users get from one page to another, and managing server-side code. For example, if you're building a content management system, Express.js could be used to manage the different routes users take to view, edit, or delete content. And Django is a high-level framework for Python that's particularly well suited for data-heavy applications. It comes with built-in tools for managing databases, handling user authentication, and securing data. Imagine you're developing an online learning platform. Django can manage the courses, track student progress, and securely store user data. Its admin interface also allows you to easily manage the platform's content and users without needing to write a lot of extra code. Ruby on Rails, or just Rails, is a framework that helps developers build web applications using Ruby. It's designed to make the process faster by providing ready-made solutions for common tasks so developers don't have to start from scratch. If you're building an e-commerce site, Rails can handle everything from managing product listings and processing orders to sending confirmation emails. While frameworks provide a structured approach to building applications, libraries offer ready-made solutions for specific tasks. Let's explore how these collections of pre-written code can speed up development and add powerful functionality to your projects. For example, if you're working on a complex dynamic application, you might use libraries like Node.js, React.js, or Vue.js alongside your backend code. These libraries allow you to create a smooth, interactive user experience by efficiently managing the flow of data between the server and the user interface. Understanding and mastering these backend technologies is essential for any full-stack developer. Whether you're handling server-side logic, managing databases, or ensuring your application is scalable and secure, these tools are the building blocks that will enable you to create robust and reliable web applications. In this video, we listed the key backend technologies used in full-stack development. Understanding and using these technologies is key to building robust server-side logic and effective database management.
A beautiful symphony is composed of many intricate elements. Musicians with their instruments ready to play, sheet music that guides each note they produce, and a conductor who ensures everything is in perfect harmony. Backend development projects are like a symphony. Developers craft the code, the music of the software world, using their tools. Project planning tools are like sheet music, outlining what needs to be built and when. At the center, integration acts like the conductor, ensuring that the proper development tools and project planning tools work together. In this video, we'll explain how to integrate project planning tools with development workflows. Integration is the process of combining or coordinating different tools or systems so they communicate and work together. When project planning tools are integrated with development workflows, project management and execution align more closely, leading to more effective and efficient projects. Let's explore the specific tools that developers rely on and examine how integrating these tools, starting with project planning tools, can streamline processes and improve collaboration. Project planning tools such as Jira, Trello, and Asana are software applications that help manage tasks, track progress, and facilitate collaboration within development teams. These tools provide a structured way to manage tasks, enable team communications and collaboration, and track progress and deadlines. You can integrate these project planning tools with development tools to create a seamless workflow. One key development tool is the Integrated Development Environment, or IDE. An integrated development environment is the primary tool a developer uses to write, test, and debug their code. It combines essential tools such as a code editor, compiler, interpreter, and debugging tools in a single interface. Some popular IDEs include Visual Studio Code, Eclipse, and Xcode. Suppose a team uses Jira for project management alongside Visual Studio Code for development. By integrating Jira with Visual Studio Code, a developer can manage the tasks directly within the IDE. This integration not only simplifies task management by keeping it within the development environment, but also ensures that updates are synchronized across both platforms. Another integral part of the developer's workflow that can be integrated with project planning tools are version control systems. Version control systems are tools that track and manage changes to code over time, allowing multiple developers to collaborate on the same project without overriding one another's work. Integrating project management tools like Jira, Trello, and Asana with version control systems like GitHub links project tasks to code changes. For example, committing code to GitHub can automatically update the related task status in Jira. This synchronization ensures all team members stay informed of the latest developments and can track progress in real time. With a clear understanding of the key project planning tools and development tools, we can now turn our attention to the practical steps of integrating these tools within development workflows. While individual tools differ in specific integration steps, they generally follow the same basic steps. First, define the workflow, outline key development stages, planning, development, testing, and deployment, and decide which stages would benefit most from integration, such as linking tasks to code commits or updating task statuses based on code reviews. Next, it's time to set up the integration. This step will be different depending on the tools you use. However, there are three common ways to integrate tools: native integrations, middleware tools, and custom APIs. Many tools come with native integrations, which are built-in connections provided by software platforms that let users link with other applications directly without the need for additional coding or third-party software. Developers can also use middleware tools to integrate tools. Middleware tools are third-party tools that act as a bridge between different software applications, facilitating communications and data management between systems that may not have direct integration capabilities. Some examples of middleware tools might be Microsoft BizTalk, Flow middleware platforms, or IBM WebSphere. In addition to native integrations and middleware tools, developers can also choose to develop and use custom APIs for integrations. This approach involves creating tailored connections using an API to link different software systems in a specific way, often requiring custom coding, but offering the highest level of customization. The final step of integration is to set up the automations. Set up the integration automations so actions in the development tools like commits, pull requests, or successful builds automatically update tasks in the project planning tool. Once the integration is complete, it offers many benefits, including enhanced productivity, better project tracking, and improved collaboration. Integration reduces the need for manual updates and data entry, enhancing overall productivity. This allows developers to focus more on coding rather than administrative tasks, thus speeding up the development process. Also, tracking project progress becomes easier with integrated tools, providing a comprehensive view of the project status. And integrated tools provide team collaboration, allowing them to share updates and feedback in real time. In this video, we discussed integrating project planning tools with development workflows and tools. Integrating these tools ensures seamless transitions between planning and coding, making project management more efficient and effective. Imagine you're navigating through a complex city without a GPS, only a paper map. Each time you reach a new intersection, you have to stop, unfold the map, and figure out your next move, all while hoping you haven't taken a wrong turn. Now, think of a project being managed in a similar way. Each step of the development process requires manual updates, constant back and forth with the project manager, and an outdated task list that only one person controls. Without integrated tools to guide you in real time, your development project will become just as cumbersome and prone to delays as navigating that city was without a GPS. In this video, we will describe the advantages of integrating project planning with development tools. Integrating project planning tools like Jira, Asana, and Trello with development tools such as integrated development environments, also known as IDEs, and version control systems provides multiple benefits for backend development projects. Teams that use these integrations experience enhanced productivity and better project tracking, improved collaboration, and increased alignment between planning and execution. Let's begin by exploring how integration can enhance productivity. Integration reduces the need for manual updates and data entry, enhancing overall productivity. This allows developers to focus more on coding rather than administrative tasks, thus speeding up the development process. It can automate certain processes. For example, when you commit code for a new API feature to a version control system like GitHub, an integration can automatically trigger the start of automated tests in a continuous integration tool. Integrations also help manage individual tasks without human intervention. For instance, when you commit code for the new API feature, the integration automatically updates the task status in your project management tool, saving you time and effort. When the integration between the IDE and the project planning tool automatically updates the status of your tasks, it also minimizes context switching. Context switching refers to shifting your attention from one task or system to another, which can disrupt focus and reduce productivity due to the mental efforts required to reorient to each new task. The automation allows you to stay within your IDE to continue working, testing, and committing code. This increased productivity enables you and your team to accomplish more in less time, resulting in faster project completion and more efficient resource use. Additionally, integrated tools ensure better project progress tracking. When project management tools are integrated with development tools, project progress tracking becomes automated and instantaneous. For example, when you mark tasks as complete directly from your IDE, the project management tool automatically updates the progress. This integration removes the need for manual entry, ensuring that the project status always reflects the latest developments without any delay. The project manager and others on the team know exactly what the task status is at any given time. This real-time project tracking can allow for quick adjustments and informed decision-making, ensuring that the project stays on track and within scope. Integrated tools also improve team collaboration. When working with your team, integration between tools means that whether you are writing code, the project manager is updating project plans, or a marketing team member is reviewing timelines, you are all accessing the same tools and information. These tools also often come with integrated communication features. This integration ensures that the communication about specific issues or updates is immediate, clear, and always linked to the relevant project context. These tools also improve collaboration with their many shared documentation features. Finally, integration enables teams to have increased alignment between project planning and project execution. Closely integrating the development work with the project plan helps ensure that the development work aligns with the project's goals. It also allows teams to adjust the plan as the project progresses and provides a continuous feedback loop between the planning teams and the execution teams. Better alignment between planning and execution ensures that the project remains focused on its goals, reduces the risk of scope creep, and improves the chances of success. In this video, we cover the advantages of integrating project planning with development tools, including improved collaboration, enhanced productivity, real-time tracking, and better alignment between planning and execution. Implementing these integrations ensures that your development processes are streamlined and effective, leading to successful project outcomes. Imagine you're a chef in a bustling kitchen, working with a team to perfect a complex recipe. Each of you contributes your unique techniques, adjusting ingredients and testing different approaches. But what if at any moment you could not only see who added what, but also have multiple chefs experiment with variations simultaneously without affecting the original dish? That's exactly what Git allows you to do in backend development. Track changes, collaborate in real time, and experiment with new ideas, all while preserving the integrity of your codebase. In this video, we will describe the basic Git commands and their uses in backend development. Version control is crucial because it tracks all changes made to the code, allows multiple developers to collaborate simultaneously, enables easy reversions to previous versions, and lets developers work on new features or fixes without affecting the main codebase. Though there are other version control systems, most developers use Git for version control. Git is a distributed version control system that helps developers track changes, collaborate, and maintain the history of their code. Think of Git as the essential kitchen tools every chef needs, like knives and cutting boards, which help them create and manage versions of their culinary creations. GitHub, on the other hand, is like the central kitchen where all chefs store their recipes and tools, showcase their dishes, and collaborate with other culinary experts. So how does Git enable developers to maintain the history of their code, track changes, and collaborate? Git involves the use of repositories and branching. In Git, a repository is a storage space where all files related to a project are kept, including their complete change history. These repositories hold snapshots of all versions of the code, allowing developers to track changes, maintain history, and roll back to a previous version if necessary. Next, let's explore branching. If you think of the main code as the main branch, developers create other branches when they need to add new code or make changes to the existing code. Think of branching like making a copy of a folder. And when a new branch is created, it's like making a copy. Developers can add to, modify, and test the documents in this copy without impacting the original. Once they're sure the edits are correct and stable, they can merge the changes in the folder back into the main branch, updating it with all the new modifications. Developers use repositories and branching to manage their code with the help of Git and GitHub. But how do developers interact with these tools? They execute commands. Developers execute commands from the command line or through an application like GitHub. These commands include clone, branch, commit, push, and pull. Let's explore each of these commands in detail, starting with clone. The clone command creates a local copy of the repository a developer is working on. This allows them to start working with the codebase on their own machine. To use the clone command, you would type git space clone space, then the URL of the repository. For instance, if you're developing a new feature for user authentication, you would first clone the existing project to your machine. Once you have a local copy of the repository with the clone command, the next step is to create a new branch. Branching allows you to work on specific features or fixes without affecting the main codebase, keeping your changes isolated until they're ready to be merged. For example, to create a new branch for your feature, you would type git space branch space followed by the branch name. For your user authentication feature, you might create a branch by using the command git branch feature-authentication. Now, you're ready to get started on the development work. Once you write some code or make some changes to the existing code, you will commit your code. The commit command captures a snapshot of the changes in a project. This allows you to track your progress and revert to a previous version if needed. To use the commit command, you would type git space commit space -m, then a commit message in quotes. Notice that commit commands include a commit message. This is where developers write a meaningful message to describe what changes were made to the codebase. For example, after creating the basic structure for a registration form, you might commit with a message, initialize user registration form. When you're done with all of the changes, you can use the push command. The push command updates the remote repository with local changes, allowing others to see and use those updates. To use the push command, you would type git space push space, then the name of the remote repository, and finally, the branch name. Once you're satisfied with the development and testing of your new user registration feature, the next step is to share your work by pushing it to GitHub. Just type git push origin feature authentication to upload all your commits from the feature authentication branch. The next day, you're ready to start working on the next feature, so you execute a pull command. The pull command updates your local codebase with the latest changes from the remote repository, ensuring you have the most current version. To use the pull command, you would type git space pull space, then the name of the remote repository, and finally the branch name. You use the pull command git pull origin feature authentication to pull down the latest version of the code in the repository. After pulling the latest updates, you can go back and use the branch command to create a new branch from the updated main branch to start working on your next feature. This workflow maintains the integrity and continuity of the project, allowing all developers to work collaboratively and efficiently. Today, we covered the basic Git commands and their uses in backend development, including clone, branch, commit, push, and pull. Understanding these commands is essential for tracking changes, collaborating with team members, and maintaining a reliable code history. Integrating Git into your development workflow will significantly enhance your efficiency and productivity. Imagine stepping into a team tasked with developing a cutting-edge telemedicine application. You're responsible for bringing to life features like virtual consultations, patient record management, and appointment scheduling. Together, you'll transform innovative ideas into a fully functional platform that could revolutionize healthcare. To keep everyone on the same page, your team relies on GitHub, a powerful version control system that allows for seamless collaboration, change tracking, and efficient peer reviews. In this video, we will explain how to use GitHub for collaborative backend development. GitHub is more than just a place to store code. It enables collaboration through the lifecycle of a project, making sure that everyone's contributions fit together seamlessly. Instead of developers working in isolation and trying to merge their work at the end, a process prone to conflict and errors. GitHub allows developers to continuously observe how their contributions fit with the team's work, ensuring seamless integration. It also allows them to share resources such as common libraries, tools, and code snippets to increase efficiency and consistency across the project and follow clear workflows for coding, reviewing, testing, and building. Now that we've covered why GitHub is such a powerful tool for collaboration, let's explore the specifics of how developers can actually use it to work together effectively. You can both collaborate and manage projects by using GitHub to create a repository, manage branches, submit pull requests, and conduct code reviews. So where does your project start? It all begins with creating a repository, the home base for all your code and collaboration. Creating a repository involves logging into GitHub, navigating to the repositories section, and clicking the New button. You will need to provide a name for your repository, an optional description, and choose whether it will be public or private. For example, you might start a new project by creating a repository named Telemedicine App on GitHub, making it private to protect sensitive patient data. With a repository in place, your team is now ready to start developing. But how do you make sure that multiple people can work on different parts of the project without overwriting each other's code? This is where managing branches comes in. To create a branch, navigate to your repository on GitHub and use the Branch drop-down menu to create a new branch. Naming conventions often include the feature or fix being worked on. For your telemedicine application, you might create a branch for the new feature, virtual consultations, to ensure the main branch remains stable and production ready. Now that you've made progress on your branch, it's time to merge your changes back into the main project. To do this smoothly and with oversight, you'll submit a pull request. After committing changes to a branch, navigate to the Pull Request tab in your repository and click New Pull Request. You can then compare changes across the two branches and provide a description of the proposed changes. For instance, you submit a pull request to merge your virtual consultations branch into the main branch, describing the new virtual consultation functionality you've implemented. Finally, it's time to have a colleague review your work. You initiate a code review that involves a team member reviewing changes proposed in a new pull request to ensure code quality and functionality before merging. Reviewing a pull request involves checking the code for errors, adherence to coding standards, and overall functionality. Reviewers can comment on specific lines, suggest changes, and approve the pull request once satisfied. Your team members review your virtual consultations pull request, while you get a code review request from another team member working on the patient record management feature. You notice that the code lacks encryption for sensitive patient data, so you add this as a comment into your review. This code review helps maintain high-quality code and ensures the application complies with data protection standards. In this video, we explained how to use GitHub for collaborative backend development, including creating repositories, managing branches, submitting pull requests, and conducting code reviews. By setting up and using GitHub repositories, development teams can effectively collaborate, manage code changes, and maintain a high-quality code base. This enhances productivity and ensures successful project outcomes.
Understanding the full scope of full-stack development is essential for creating seamless and dynamic software applications. We began by defining full-stack development and its role in the software lifecycle. We explored the responsibilities of full-stack developers, how they differ from front-end and back-end roles, and the essential tools and technologies they rely on. Then we delved into the critical functions full-stack developers perform and their value within the tech industry. We also discussed the rising demand for these adaptable experts and the diverse career paths open to them. We then compared full-stack development with front-end and back-end roles, highlighting how each plays a distinct part in software projects, and how full-stack developers bring these skills together to build seamless, integrated solutions. Finally, we explored the key tools and technologies that full-stack developers rely on, focusing on both front-end and back-end components essential for creating robust and interactive applications. Mastering full-stack development equips us to build dynamic software solutions by integrating front-end and back-end skills with essential tools and technologies, meeting the demands of today's tech landscape. Welcome to Introduction to Logical Thinking and Problem Solving. This module equips you with the core skills of logical thinking and problem solving in programming, teaching you how to break down challenges, apply effective reasoning, and code confidently, essential tools to kickstart your programming journey. We'll start by defining the fundamentals of logical thinking in programming, focusing on key logical processes and the types of logic essential for effective problem solving. Next, we'll examine the steps of deductive reasoning in programming and how this method can be applied to solve problems logically and systematically. Then we'll explore techniques for problem decomposition, breaking down complex issues into manageable parts for more effective problem solving. Next, we will explore top-down and bottom-up problem-solving approaches, comparing their strengths and how they apply to different scenarios. Next, we will identify coding techniques for simple problem solving, focusing on using pseudocode to structure your approach before writing actual code. By the end of this module, you'll have the essential skills to think logically and solve problems effectively in programming, from breaking down challenges to applying structured reasoning and coding confidently. Let's get started with Introduction to Logical Thinking and Problem Solving. Imagine you're planning a road trip. You need to decide the route, stops, and duration at each place. These decisions follow a logical sequence, much like how programming works. In this video, you will learn how to explain what logical processes are and their relevance in programming. Before we discuss how logical processes work in programming, let's explore what logical processes are. Logical processes are the fundamental components that make up the code in programming languages. Logical processes are not separate from the code. Rather, they define the flow and control within the code itself. They are the building blocks of programming that provide the structure for how the program should operate. Every aspect of the program has to be assembled and made to work together properly for the entire program to function as expected. Logical processes are what programmers use to make sure this happens. The first logical process we'll explore are sequences. In programming, a sequence is the simplest form of control structure where the code is executed in a specific order. When following a morning routine, you might have a sequence of actions like brushing your teeth, then showering, and finally having breakfast. In programming, sequences ensure that instructions are executed in a specific order to achieve a correct result. To illustrate how a sequence works in code, we'll use pseudocode, which is a simplified, informal way of writing programming logic using plain language. In pseudocode, a sequence might be structured like this. Step 1, open the Applications folder. Step 2, open the text editor. Step 3, create a new document. Sequences aren't the only logical process in programming. To make programs responsive to different conditions, programmers use a logical process called control structures. Control structures are statements that determine the flow of code execution based on specific conditions. Deciding whether to go for a walk based on whether it's raining or not is a real-life example of a control structure. In programming, if-else statements are used to make decisions, allowing programs to react differently under various conditions. Because of this, programmers also call these conditional statements. These statements are logical because they control the flow of the program, even though the conditions may not be known until the program runs. For example, suppose a user is filling out a form in an application and leaves the age field blank. In pseudocode, a control structure for asking for the user's age would be, if the age field is blank, then prompt the user. Otherwise, or else, move to the next field. In this case, the user left the age field blank, so the logic dictates that the application should prompt the user. Control structures help in directing the code down a specific path, and this does a lot of logical work in a program. However, if a developer needs a particular code to run over and over, they use another logical structure called an iteration. Iterations, also called loops, are statements that enable a program to repeat a set of actions until a specific condition is met. When you're learning any new skill, you need to practice repeatedly until you master it. This is similar to iterations in programming, where loops execute the same block of code multiple times to perform repetitive tasks until a specified condition is met, such as processing items in a list until the end of the list is reached. For example, suppose you have a database with 10 records and need to write a program that capitalizes the data in the last name field for all 10 records. In pseudocode, here's how the logic of your program would work. 1. Load a record. 2. Capitalize the last name field. 3. If it's the last record in the database, exit, else move to the next record. 4. Repeat the process. It's important to understand that computers are logic machines. Therefore, when developers think in terms of logical structures, they're better able to think about how they should write computer code. Logical thinking also enables programmers to solve code problems and debug their code because they're better able to break down complex problems into manageable parts. Now let's tie all these ideas together with a simple example. Consider the logical structure that a developer would need to create a simple task list app. Users need to be able to add tasks using code that processes the steps in a specific sequence. Next, the programmer needs to make sure users can mark tasks as complete or incomplete using control structures in the form of if-then statements. Finally, the developer will need to save and load all the tasks in memory or data storage when the user opens or closes the application using an iteration. By using logical structures, the app can efficiently manage and provide tasks, ensuring a smooth user experience. In this video, you learned how to explain what logical processes are and their relevance in programming. Logical processes, such as sequences, control structures, and iterations, are the building blocks of any program. Understanding and applying these structures help programmers write efficient and error-free code. In programming, logical operations involve operators such as and, or, and not that manipulate true or false values to direct a program's decision-making process. These operators are fundamental to developing conditional logic and managing a program's flow. In this video, we will identify and describe different types of logic used in programming. The first, Boolean logic, is the branch of logic that deals with true and false values. When programs run, they process data, respond to user input, and address conditions on the machine where they are running. In programs, these are represented as expressions, which is a line of code that can be either true or false. Every expression can be in a variety of conditions, and programmers use Boolean operations to process them. Whether an expression is true or false is called its truth value. Boolean operations are those that evaluate truth values. Now let's explore the fundamental operations of Boolean logic and how they're used in programming, starting with the AND operator. The AND operator evaluates two expressions. The result of the evaluation is true only if both expressions are true. If either expression is false, or both expressions are false, the result of the evaluation is false. Suppose a program is processing two items of data, a first and a last name in a record. The program evaluates whether both fields have a value. The first table has a record with the first name Paul and the last name Picasso. Both fields have values, so the truth condition is true for the first name and the last name. This makes the AND operation true. Now in the second table, the record shows the first name Paul, but the last name is null, or does not have a value. Here, the truth condition is true for the first name but false for the last name. This makes the AND operation false. The next Boolean operator, the OR operator, also evaluates two expressions. The result of the evaluation is true if either expression is true or both expressions are true. If both expressions are false, the result of the evaluation is false. Suppose we change our program to evaluate whether at least one of the fields in our record has a value. The first table has a record with the first name Paul, and the last name has a value of null. The truth condition is true for the first name and false for the last name. Because at least one of the fields has a value, the OR operation is true. Now, in the second table, the record shows the first name null and the last name is null. Here, the truth value is false for both fields. This makes the OR operation false. The NOT operator is the last of the Boolean operators we will examine. Unlike AND and OR, the NOT operator operates on a single expression, and it negates the truth value of the expression. If an expression is true, applying the NOT operator makes it false. If the expression is false, the NOT operator will make it true. We'll change our program one final time and use it to evaluate whether the last name field has a value, or, put another way, the last name field is not null. In the first table, we see a record with the first name Paul, and the last name has a value of null. The truth condition for whether the last name is null is true. The truth condition for the NOT operator is false. Now in the second table, the record shows the first name Paul and the last name is Picasso. Because the last name has a value, the truth condition for whether it's null is false, and for the NOT operator is true. Boolean logic isn't the only logical tool programmers can use to control how a program runs. While Boolean statements tell a program the truth value of an expression, programmers also need a way to respond to changes in those truth values. Conditional statements are how programmers use Boolean values to control the flow of a program. Let's explore these by starting with the most fundamental version, the if statement. If statements are used to operate on one or more expressions. They evaluate the truth value of the expressions, and they execute a block of code based on the evaluation result. For example, suppose your program needs to prompt a user if either the first name or last name in their record is null. You would write an expression that uses an if statement to determine the truth value of the expression. The program would evaluate if the first name field is null or the last name field is null, and then prompt the user if either field doesn't have a value. If statements are well designed to address expressions that evaluate to a single truth value. In many cases, programmers need to direct the program's flow for a variable that can have a variety of possible values. One option is to string together multiple if statements. Another option is to use a switch statement. Switch statements operate on an expression that can have a variety of values and executes a block of code when a particular value, called a case, is true. Switch statements also include a default option in case none of the values is true. For example, suppose your program needs to evaluate the country field for a particular record and show a specific license agreement for 3 different countries, Germany, Kenya, and Japan. If the country field isn't one of those countries, the statement can show a general license agreement. The switch statement would have a case for each country and show that country's license agreement and a default option for the general license agreement. These conditional statements help the programmer guide the flow of the program and execute specific code based on conditions. Sometimes programmers need to perform the same tasks on multiple data items. For these types of tasks, they use statements called loops. Loops allow us to repeat actions in a program, either a specific number of times using a for loop or until a condition is met using a while loop. Let's explore for loops first. A for loop executes a block of code a specific number of times. A programmer can specify the number of times they want the code to repeat, or the number can be a property of the variable itself. Imagine you have to process 10 records in a database by removing spaces before and after the first and last name fields. You can bring the data into a for loop as a special variable that can store all 10 records. You can then loop through each record in the variable until the loop gets to the last record. A for loop is helpful in cases where the number of values the programmer has to process is known. In cases where the number isn't known, the programmer can use a while loop to create a loop with a condition. The truth value of the condition tells the loop when to stop executing the code block. A while loop executes a block of code as long as a specified condition is true. While loops can be used with Boolean statements to create the conditions the programmer wants to evaluate. Suppose you're processing records in a database and need to remove duplicates. You can use a while loop to check if a record has duplicates and delete them as long as they exist without needing prior knowledge of how many duplicates there are. In this video, you learn to identify and describe different types of logic used in programming. Boolean logic statements and conditional statements are ways programmers evaluate and guide what code runs in a program. By using these statements, you can create dynamic programs that do a lot of valuable work. The main focus of front-end developers' work is writing application code. However, before writing even a single line of code, developers need to design the program's logical flow. In this video, we will demonstrate how logical processes are applied in real-world programming scenarios. Two common tools used by developers to help design a program's logical flow are flowcharts and pseudocode. Let's begin by exploring flowcharts. A flowchart is a diagram that represents a process. It uses various shapes to show the application's logic and arrows to illustrate the paths users can take through the software. Flowcharts help developers plan the logic before writing the code, making it easier to understand and communicate complex processes. Developers often use flowcharts to map out the logic of their applications. For instance, a developer can use a flowchart to represent the steps a user can possibly take in a login system. For example, suppose we are developing an e-commerce checkout process. The flowchart would include steps like 1. Selecting products, 2. Adding them to the cart, 3. Entering shipping details, 4. Choosing a payment method, 5. Confirming the order. When a customer selects a payment method, there are multiple paths they might take. The flowchart makes sure all these options are mapped out. To build this flowchart, the developer can use a tool like Visio or Miro to create shapes that represent each step in the flow. The shapes represent certain types of events in the flow. The developer begins by designing the e-commerce checkout process with the start point using an oval shape with the word "start" in it. The oval clearly marks the beginning of the process, signaling to anyone reading the flowchart that this is where the customer's journey begins. Next, the developer creates the Select Products step, which is represented by a rectangular shape containing the words Select Products. The rectangle indicates a process or action step. Here, the customer browses through the product catalog and selects items they want to purchase. The developer uses this rectangular shape to capture the action of product selection. An arrow from the Start oval to the Select Products rectangle illustrates the direction of the process's flow. Following product selection, the developer designs the Add to Cart step depicted by a rectangle containing the words Add to Cart. The developer chooses the rectangle again to signify the simple process action, where the customer places the selected items into the shopping cart, a temporary holding area, before proceeding to checkout. The developer adds an arrow that points from Select Products to Add to Cart. The developer then moves to the View Cart step, using another rectangle, this time containing the words View Cart. This shape represents a regular process step where the customer reviews the items in their cart, checks quantities, and makes any necessary adjustments before moving on. An arrow is added that points from the Add to Cart shape to the View Cart shape. Once the customer is satisfied with the cart,
The developer sets up the Proceed to Checkout step marked by a rectangular shape with the words Proceed to Checkout inside the rectangle. This shape indicates the action of transitioning from the shopping phase to the purchasing phase. The developer adds an arrow that points from the View Cart shape to the Proceed to Checkout shape. Next, the developer designs the Enter Shipping Details step, which is represented by another rectangle, this one containing the word Shipping Details. The rectangle shows this as a process step where the customer inputs shipping information to ensure correct delivery. The arrow points from the Proceed to Checkout shape to the Shipping Details shape. At this point, the developer introduces a decision point, Select Payment Method. The developer uses a diamond shape here containing the word Select Payment Method because it represents a decision that leads to multiple paths. This shape visually distinguishes it from process steps and signifies that the customer must choose from various payment options, such as a credit card or PayPal. The arrow points from the Shipping Details shape to the Select Payment Method shape. At this point, the developer can illustrate different payment methods by adding arrows and shapes to show each possible method. After selecting a payment method, the developer adds the Confirm Order step using a rectangle with the words Confirm Order added. This shape represents the final action step where the customer reviews and confirms their order details, ensuring everything is correct before completing the transaction. The arrow points from the Select Payment Method shape to the Confirm Order shape. Finally, the developer concludes the process with the End, using the oval shape containing the words End. The oval marks the completion of the checkout process, clearly indicating that the customer's journey has reached its conclusion and that the order has been successfully placed. The final arrow points from the Confirm Order shape to the End shape. This simple flowchart visually illustrates how a user will move through the checkout flow and also shows the logical order of events the application must support. The arrows and their direction can be translated into code as logical operators, and the flowchart helps the developer understand that logical flow. Now that we've seen how flowcharts help in visualizing program logic, let's explore another essential tool, pseudocode. Pseudocode further refines this logical process by describing what a piece of code should do. Pseudocode is a detailed and readable description of what a computer program or algorithm must do, expressed in a natural language rather than in a programming language. This helps connect the initial concept and the actual code. For example, the developer starts designing the e-commerce application by illustrating the program logic in a flowchart. Next, they take the high-level design and start to translate each of the steps in the process into pseudocode to get a better idea of what the actual code should do. Let's examine a pseudocode example using the Add Products to Cart step. The code needs to support the customer in picking a product. The pseudocode will begin with Step 1, Start function, add to cart, product ID, quantity. And then Step 2, retrieve the product details from the database using product ID. Then Step 3, if product is available in the desired quantity, Option A, add product and quantity to the cart, and Option B, update the inventory. Then Step 4, confirm addition to the cart. Next, Step 5 states that if the product is not available in the desired quantity, then show an error message to the user. Finally, in Step 6, end function. This pseudocode outlines the steps and conditions in a clear and concise way, ready to be translated into actual code. In this video, you learned how logical processes are applied in real-world programming scenarios. Understanding and applying logical processes are critical skills for any software developer. By using tools like flowcharts and pseudocode, developers can effectively map out and plan their program structure before starting the actual coding process. Imagine you're a front-end developer working on a critical bug that causes the entire application to crash. The stakes are high and you need to fix the issue fast.
Just like a detective solving a mystery, you need to gather evidence and apply logical steps to find and fix the bug. In this way, deductive reasoning is one of your most powerful tools as a developer, helping you systematically understand and structure your code and resolve issues efficiently. In this video, we will define deductive reasoning and its importance in programming. Deductive reasoning is a logical process by which conclusions are drawn from given premises. This type of reasoning helps developers make informed decisions based on established logical principles and factual information. For example, if we start with the premise that we know that all functions in a code base should have a clear and defined output, then our conclusion is that any function we write should meet this criterion. Now that we've explored the foundational concept of deductive reasoning, let's examine how this logical approach can be applied in real-world scenarios with front-end development. One key area where deductive reasoning plays a crucial role is in designing responsive user interfaces. Consider how front-end developers at a technology company use deductive reasoning to architect software systems. They start with a broad understanding of the project requirements and use logical steps to break them down into smaller, manageable components. Responsive design is an example of where deductive reasoning can be applied. In practice, the premise that we know that a responsive design is essential leads to a conclusion that developers will ensure all UI elements are adaptable to different screen sizes. Establishing causal relationships between parts of code is another area where developers can apply deductive reasoning. By understanding how one part of their code affects and impacts another part, developers can create more efficient and less buggy software. For example, working with the premise that a change in the state of a component should update the display, then any change to that state should trigger a UI update is the conclusion. Front-end developers use deductive reasoning for tasks other than structuring their code. They are responsible for managing data for user interactions and communicating with the backend. Using deductive reasoning, developers start with a broad understanding of the data their front-end needs, and then deduce how different data entities should interact. For example, if an e-commerce site needs to track user purchases, the premise, they can conclude that the data model will include relationships between users, products, and transactions. A table that tracked purchases might have fields that store the record ID, an ID for the user that made the purchase, an ID for the product they purchased, and a field for the transaction ID, so all the fields are related. Developers also use deductive reasoning when creating the user interface itself. Developers establish how users will interact with the application based on requirements and data from studying user behavior. They use this information to deduce a design for the user interface. For example, knowing that users prefer quick access to navigation is the premise, and that developers will implement intuitive and accessible navigation menus is the conclusion. For example, a file menu item should have items like new for creating a new file and open to open a file, and shouldn't have items like bold for bolding text and bullets for creating bullets. Besides architecting software and developing interfaces, developers use deductive reasoning to debug their front ends. Let's explore how this skill might help them identify and fix bugs. In debugging, deductive reasoning allows developers to identify and fix errors efficiently. By starting with the issue they observe, they develop premises that state the facts about the issue. From there, they draw conclusions that help them find the problem area in the code. For example, if an application crashes when a user submits a form, that's the premise. Developers will check the form validation and submission process to find the specific error as the conclusion. In this video, you define deductive reasoning and its importance in programming. By applying logical steps to reach specific conclusions, developers can create efficient, effective, and user-friendly applications. Your company's login page has gone down during the busiest time of the year. A recent update tried to address the issue, but it was unsuccessful. How can you use the problem's symptoms to help you identify its cause? This process is known as deductive reasoning, and with strategy and practice, you'll be able to build strong deductive reasoning skills that will help you as a developer. In this video, we will outline the steps involved in applying deductive reasoning to solve problems. Recall that deductive reasoning is a logical process by which conclusions are drawn from given premises. It's similar to solving a puzzle where you begin with the pieces of the puzzle, the premises, to understand the completed puzzle, the conclusion. In programming, this method helps developers solve complex issues by breaking down problems into smaller, manageable parts. Deductive reasoning typically is put in the context of an argument. An argument in logic is different from an argument you may have over a disagreement. In logic, an argument has three parts: premises, which are the evidence you cite, a conclusion, which is what you want people to believe from the evidence, and a supporting relation between the two. Stated another way, an argument is premises that support a conclusion. Although people have a natural ability to reason deductively, you can train your mind to follow a process that will help you identify premises more quickly and precisely, so you can draw more accurate conclusions. Next, let's explore the deductive reasoning process using a real-world example. The first step in this process is to identify the argument's premises. Premises are the statements that you believe to be true. For example, if your website's login page isn't working, your premises might be: 1. The login function recently was updated to fix a bug that prevented them from logging in. 2. Users are unable to log in. Identifying these premises is the foundation of deductive reasoning because it provides the basis for drawing a conclusion. Once you've identified the premises, in step 2 you can analyze the premises to figure out how they relate. For example, you might check the recent updates to the login function to verify if there's a bug in the code. This step is essential for revealing what you know and what you need to discover, and a large part of analyzing premises is understanding how to craft good ones. When crafting good premises, know that they should be clear, factual, and your premises should be directly related to the issue or problem that you're trying to solve. For example, the premise, "the website has errors," is less clear than the premises, "the login function was recently updated and users are unable to log in." Good premises are crucial because they lead to accurate and logical conclusions. Next, in step 3, once you have clear premises, you can draw a conclusion based on them. Using the prior example, based on the premises about the login function and user experience, you can reasonably conclude that the login's code bug was caused by the recent update to fix another login issue. Drawing a conclusion helps identify the exact cause of a problem based on logical connections. To relate premises to conclusions, find a direct cause and effect relationship. Ask yourself, if the premises are true, what also must be true? For example, setting aside any other factors, if the website was updated to fix a login bug is true, and it's also true that users cannot log in after the website was updated, then it must be true that the login bug was not fixed. Finally, in step 4, it's important to test your conclusion to confirm it's correct. For example, you can perform a code review and further testing to determine if there's still a bug in the login code. This step is critical as it validates your deductive reasoning process by ensuring the conclusion you've drawn from the premises is correct. In this video, you learned to outline the steps involved in applying deductive reasoning to solve problems. Deductive reasoning is a powerful process for solving problems. By identifying premises, analyzing them, drawing conclusions, and testing those conclusions, you can efficiently debug and fix issues in your code.
Wouldn't it be nice if all software issues were straightforward to fix? Sometimes a simple misspelling can cause an application to crash, and developers can quickly locate and fix the bug with software tools,
But what if you're dealing with a core issue in an application where the problem is spread throughout the code? You have limited time to fix it, but you don't know where to start troubleshooting. This is where problem decomposition comes in. By breaking the problem into smaller, manageable parts, you can more easily find and address the issues. This process is what decomposing is all about in programming. In this video, we will explain the concepts and benefits of decomposing complex software. Problem decomposition is the process of breaking down a complex problem into smaller, more manageable parts. Decomposing software problems makes them easier to understand, manage, and solve, especially in intricate and multifaceted programs. Let's use a real-world example of problem decomposition to illustrate. Suppose a company has an issue with its order processing system. By breaking the software down into component parts like user authentication, order placement, and payment processing, developers can isolate and fix the problem faster. But the benefits of decomposition don't stop at debugging. Let's explore how this approach also simplifies implementation. Implementing smaller parts of a program is simpler and less error-prone than attempting to develop all aspects of the application at once. Suppose a grocery store is implementing software to track inventory. When the software's developers break down the implementation into areas like tracking stock levels, updating stocks after sales, and notifying suppliers when inventory is low, each part can be developed and tested independently. By decomposing software into smaller components, systems can be developed by more than one software engineer, enhancing collaboration. Decomposing problems allows multiple team members to work on different parts simultaneously, improving efficiency and collaboration. For example, one team can develop the inventory tracking software, another could focus on developing the user interface, and another team can work on the backend inventory management system. Creating smaller components also helps developers maintain their code base, making maintenance easier. If a change is needed in one part of the system, the isolated component can be updated independently without impacting the other parts. This also can reduce the impact on users if developers can update components without having to shut down and refresh the entire system. This helps reduce downtime. Now let's explore the steps involved in decomposing software for debugging and implementation. The first step is identifying the problem or goal the developer needs to address. A clear problem statement lays the foundation for effective decomposition. Second, developers divide the main problem or goal into smaller, more manageable parts. This is the focus of decomposition. This step can take time and may require collaboration with other team members to ensure decomposition is done properly. The third step is to analyze and address each part individually, fixing bugs or implementing individual components. Complex bugs can require fixes across many components and programs with a large number of features, and developers might need to write multiple components at once. When bug fixes and components have been verified and tested, they can be integrated into a full software solution. Integration may introduce new bugs or require additional components that might require further decomposition. Now, how does this process play out in a real-world scenario? Let's examine a case study where a problem decomposition was key to developing a new software feature. Imagine a grocery store called Pure's Grocery, which faced challenges with tracking stock levels, managing supplier information, and handling order fulfillment. By decomposing these challenges into smaller tasks, their software developers could create a robust inventory management system. Let's explore the steps they took to achieve this. First, the store identified the goal to improve its order management system. Second, they created a module to track stock levels in real time. Third, developers worked on a system to manage and update supplier information. Finally, in the fourth step, they implemented an order fulfillment process that syncs both the stock levels and supplier data. By decomposing this development project, the development team added the benefit of being able to perform targeted improvements. This eased maintenance and significantly enhanced overall development efficiency and user experience. In this video, you learned how to explain the concepts and benefits of decomposing complex problems. understanding and implementing problem decomposition can greatly simplify complex programming tasks, making them more manageable, efficient, and easier to maintain. Imagine reviewing a program's code that's hard to follow logically and is filled with errors, leaving you confused and unsure of where to start. Solving such problems can be overwhelming if approached all at once. But what if you can break down this complexity into smaller, manageable pieces? This technique, known as problem decomposition, is a fundamental strategy in software development that allows you to tackle even the most daunting coding challenges with ease. In this video, we will describe various techniques for decomposing problems. Problem decomposition allows you to tackle complex problems by breaking them down into smaller, more manageable pieces, making it easier to plan, code, and troubleshoot. There are two main approaches you can take when decomposing a problem. The first, called top-down approach, is to examine the problem as a whole and then discover the parts that make it up. The second, called modularization, is similar, except it categorizes the parts by area or function. Let's explore each of these approaches to problem decomposition. The top-down approach is a method of problem solving that begins with a broad overview of a problem and breaks it down into smaller, more manageable parts. This technique is similar to creating an outline for an essay. First, you start with the main topics, and then you add subtopics and details. Similarly, in deductive reasoning, you start with a general statement of the problem and then use evidence and argument to discover the reasons that are the underlying causes of the problem. Let's illustrate this approach using an example of building a website. When building a website, your first task is to define the overall goal and structure, and then create a list of the individual pages and features you need to create. Using the top-down approach, you might decompose the development as follows. First, begin with the overall goal, for example, build an e-commerce site. Second, decompose or break down the development tasks into main sections: the home page, the product pages, and the checkout process. And third, you can further decompose these sections into even smaller tasks like designing the layout, coding the functionality, and testing the features. The top-down approach is very useful for general problems and particularly for less complex problems. As problems become more complicated, a modular approach to decomposition can not only help solve the problem initially, but also prevent further problems in the future. We call this modularization. Modularization is a decomposition approach where you fragment a complex issue into smaller, independent parts that each carry out a specific role. This approach simplifies problem solving by allowing each part to be developed and refined separately, making it easier to manage and understand the overall problem. Modularization involves breaking a problem or goal into self-contained units or modules. Each module performs a specific function or set of related functions, making the larger problem or goal simpler to manage and understand. This process is similar to organizing a room by categories. First, you might organize all your clothes in the room regardless of where you keep them. Then you might focus on your books, even though you might have some on the shelf, some on the desk, and some by your bed. The process works similarly in software development. For example, a website may use authentication logic on many pages on the site. You might separate all the pages that use authentication logic into a category, and then create a single module that works on authentication for all the pages. To recap, the top-down approach allows you to start with a broad goal and break it down step by step, while modularization focuses on creating independent modules for each key function. Both techniques are invaluable for managing complex problems efficiently. In this video, you learned how to describe various techniques for decomposing problems. Remember, breaking down a problem into smaller parts not only helps you understand it better, but also makes the process of solving it more structured and efficient. So next time you take on a big project, start by decomposing it into smaller, manageable tasks. Have you ever faced a problem so complex that you didn't know where to begin? In software development, taking on large-scale issues can feel overwhelming. But there's a powerful method that can make this process more manageable called the top-down approach. This approach breaks down complex problems into smaller, actionable tasks, helping you navigate from broad issues to specific solutions efficiently. In this video, we will apply the top-down approach to problem solving. The top-down approach is a method of problem solving that begins with a broad overview of a problem and breaks it down into smaller, more manageable parts. This method is particularly useful in software code debugging and feature development because it allows developers to focus on broad aspects early before addressing the finer details. For example, when debugging code using the top-down approach, the developer will start with a general examination of the system. This helps them identify which specific area or component might be causing an issue. Once they've settled on a specific area of the code to focus on, they can begin exploring the details of specific lines of code to debug. The top-down approach is systematic. By implementing this methodology, the developer can more efficiently and accurately build software and address bugs. Let's explore ways to implement the top-down approach when designing software and then when debugging code. Software is built to accomplish a set of goals or solve a problem. To implement the top-down approach in software design, the developer starts with a broad design goal or problem statement. In this approach, it's helpful for the developer to state the goals and problems that are out of scope, clearly providing what the software won't do or problems it won't solve. For example, the developer might have a design goal of creating software that catalogs books by subject matter. They might further specify that the software will not enable people to catalog books from their personal library or create custom categories. Now that the developer has defined the design goal the software should accomplish or problem it should solve, the developer can break it down into specific steps for development. For example, the book catalog system would need the following features, which can be turned into development tasks. First, it would need a way to import book data. Second, it would need a set of categories into which the software would place each book. Third, the software would need the ability to display the books by category. In the fourth and final task, the developer might want to include the ability to modify a category if the software placed a book in the wrong one. These are high-level tasks, and the developer can create subtasks for each task to refine it even more. The top-down approach helps developers go from a big idea to specific tasks when developing software. Now let's explore how this approach can be used to debug software. Imagine a situation where a web application crashes when a user submits a form. The developer starts by identifying the broad issues such as form submission causes a crash. Next, the developer breaks the issue down into smaller, specific tasks that might lead to the cause. For example, they might check server logs for error messages, examine network requests the form is making, and inspect the form's input validation logic. The next step in the top-down approach is to isolate the issue by focusing on each component. By working through each task, the developer might discover that the problem lies in a specific area, such as the input validation logic. Without using the top-down approach, the developer may have searched randomly for the problematic code. By taking the systematic approach, they could validate components that were working properly while discovering the problematic code. The final step in the debugging process is to address the specific issue that was causing the problem. In this case, the developer corrects the input validation logic to manage unexpected input properly. By following these steps, they methodically narrow down the problem from a broad issue to a specific fix, ensuring a structured and efficient debugging process. In this video, you explored how to apply the top-down approach to problem solving. Applying the top-down approach in software development and debugging helps you manage complex issues by breaking them into smaller, more manageable parts. Next time you encounter a complex problem, remember to start broad and systematically work your way down to the specifics. When you meet a new person, you know very little about them. As you get to know them, you learn what they like, what upsets them, how they think about the world, and what interests them. Over time, you develop a more complete picture of who they are. This inductive method uses a bottom-up approach where you build a full picture from individual pieces of information. Software developers can use this bottom-up approach to debug and develop software. In this video, we will apply the bottom-up approach to problem solving. Let's start with a definition of the bottom-up approach. The bottom-up approach is a method of problem solving that begins with small, manageable parts and combines them to create a broad composite. By starting small and focusing on each component, you'll learn to build reliable software that meets the challenges of complex development projects. The approach can be used to solve problems or to design and develop just about anything. Now let's explore how developers use the bottom-up approach to design and develop software. Generally, developers using the bottom-up approach will create individual components first and then integrate them into a complete system. This enables developers to focus attention on each part without having to integrate them into a larger system while they're developing. To understand this bottom-up approach in action, let's consider an example. Imagine developers are building a social media application. They would start by working on individual functions or modules and handling a specific task. Once these modules are working well, they integrate them to form the complete application. Let's explore how this works step by step. First, they build the user authentication module to manage the application's login and security aspects. Second, they might work on a profile management module where users can create their username, add their billing information, and adjust their privacy settings. For the third step, the team moves to developing the messaging module so users can create posts, react to other people's posts, upload images, and send and receive messages. Once these modules are developed, the fourth step involves integrating the components into a single application. Although the bottom-up approach begins with the individual components, it does not mean that the team lacks an overall design. Instead, this approach determines how the design is implemented. Also note that while specific components are completed at each step, the team does not have a complete application until all the parts are combined into a single system. This final step is called integration. Integration is the process of combining parts of a problem or design into a complete composite and unified whole. When developers use the bottom-up approach to develop software, they need to create the parts in a way that allows them to be integrated. Each part needs to have interfaces that expose its functionality to other parts of the application. These interfaces also need to be written to protect private or financial information so that data isn't exposed during integration. After integration, the parts should function as a unified whole, and developers should test to verify this. Let's review a software project where the development team uses a bottom-up approach to create a composite application from individual parts. Let's start by listing the project's goals. Suppose a company needs to develop a complex e-commerce application for its new online store. The company wants to create a modularized system so developers can create and maintain individual parts. They use automation to integrate the parts and then manually test the integrated application. Given these goals, the company decides to use a bottom-up approach. The development team starts by creating individual modules for each functional area of the site, like user authentication, product listing, shopping cart, and payment processing. Next, the team tests each module individually to ensure it functions properly. For instance, they ensure the user authentication module properly registers and logs in users. The team then begins the integration phase. They use software tools to combine the tested modules one by one. First, the tool combines user authentication with the product listing module. It then adds the shopping cart module, followed by the payment processing module, automatically testing each integration until it builds the complete application. Their final phase is conducting a holistic test to make sure all the integrated parts seamlessly work together. The team validates that users can log in, browse products, add items to the cart, and complete purchases without any issues. By following the bottom-up approach, they build a robust application from individual parts. This approach will also help them update and maintain the application over time. In this video, you learn to apply the bottom-up approach to problem solving. Applying the bottom-up approach to problem solving in software development lets you focus on building and perfecting individual components before integrating them. Next time you develop a complex application, start small, perfect each part, and then bring it all together for a polished final product. When you're presented with a problem, you most likely evaluate it and begin to strategize how you're going to solve it. Do you have a good idea of what the problem is? Do you break the problem down into smaller pieces and make it easier to manage? Or is the problem unclear and do you need to gather more information before you can have a better idea of the situation? The answers to these questions help you decide whether to take a top-down or bottom-up approach to solving the problem. Developers can use these approaches when developing and debugging software. In this video, we'll compare and contrast the top-down and bottom-up approaches. The top-down approach is a method of problem solving that begins with a broad overview of a problem and breaks it down into smaller, more manageable parts. The top-down approach is useful when you have a clear overview of a problem, but need to break it down to gain further insights and make it easier to manage. Let's now explore some of the benefits and limitations of this approach. One benefit of the top-down approach is that you can address the problem in small, focused tasks. This in turn facilitates a deeper understanding of the major areas of the issue. Additionally, it can foster collaboration by enabling a team to work on individual parts of the problem. However, despite these benefits, the top-down approach can sometimes limit problem solving because it requires the developer to have a clear understanding of the high-level problem at the start. Without this, the developer may be unable to break the problem down accurately. Furthermore, because the parts are dependent on the problem definition, the approach can be rigid and lack flexibility once the developer defines the problem. The top-down approach helps developers move from a big idea to specific tasks when developing software. But it's not always ideal. Sometimes developers need to gather more information when debugging or take a modular approach to software development. In these cases, they may prefer the bottom-up approach to solving the problem. The bottom-up approach is a method of problem solving that begins with small manageable parts and combines them to create a broad composite. The bottom-up approach benefits developers because it enables them to explore problems or begin development without having a lot of information from the start. It's an exploratory approach to solving problems in development, which makes it very flexible as the developer can experiment and try new ways of doing things. It also enables the developer to scale their research and development efforts as needed. While the developer may have a development goal or problem definition, they're not constrained by a rigid direction at the beginning of the process. The exploratory nature of the bottom-up approach offers many benefits, but there are some limitations to consider as well. For example, because there's not a clear problem definition at the start, this approach can be unwieldy, leading the developer in unsuccessful directions and wasting their time. Additionally, developers may not know when to stop their research or development efforts, making the approach unconstrained. Whether the developer should use the top-down or bottom-up approach depends on the type of problem that they need to solve, available resources, and their objective. Answering a series of questions can help the developer or their team decide on which approach may be more appropriate. The first question to ask is whether the problem or development goal is clearly defined. If it is, a top-down approach may be more appropriate. Otherwise, the developer may take a bottom-up approach in order to gather more information or start developing code. The second question the developer should ask is whether the problem or project needs to focus on the specifics or the overall goal. They need to decide which takes priority. For example, if the developer needs to create a new encryption algorithm that requires careful attention, but is not focused on where in the application it will be used, they may take a bottom-up approach. In contrast, if the developer is attempting to address a recurring crash on a critical system, breaking the problem down to find the issue quickly may require a top-down approach since the problem is well defined. Finally, the third question the developer should consider is whether they're resource constrained or if time, money, and people resources are more flexible. A startup that has no deadline to meet on a new project and wants to explore all its options may take a bottom-up approach so it can have the maximum amount of flexibility and scale. In contrast, a business that is working on a deadline with a limited budget may need to take a top-down approach with a clearly defined goal in order to stay within its resource constraints. Use the top-down approach when you need a clear overall structure from the beginning, while the bottom-up approach is best when the project involves developing intricate components with a need for detailed testing and validation, or the problem information is unclear and you need more information. In this video, you compared and contrasted the top-down and bottom-up approaches. Understanding the strengths and weaknesses of both approaches allows you to choose the best method for your project.
Computers operate on a binary system made up of ones and zeros. Writing program logic in binary would be very difficult and time-consuming. Modern programming languages use a specialized syntax to make things simpler for developers. But before you start writing code that the computer can understand, it can be very helpful to write out the logical flow of the program in natural language like English or Spanish. Pseudocode is exactly this. It's a way of describing the structure of a program in plain language to make it easier for the developers to work out any challenges in the program's logic and even debug their existing programs. In this video, we will write pseudocode to outline problem-solving steps. Pseudocode is a detailed and readable description of what a computer program or algorithm must do, expressed in a natural language rather than in a programming language. Pseudocode serves as a bridge between natural language and programming code. Developers use it to outline the logic of a program before translating it into actual code. Pseudocode helps developers plan and communicate their ideas clearly so they can verify that the logic is correct and easy to follow before spending their time coding. For example, writing pseudocode for a sorting algorithm allows a developer to focus on the steps involved without worrying about the syntax. Even though pseudocode is written in a natural language, developers should follow some guidelines so the pseudocode is used similarly for all developers. Guidelines also help developers write pseudocode with a structure that they can use to translate the pseudocode to actual code more easily. First, when writing pseudocode, use plain language. Write the logical steps in simple, clear language that any other developer can understand. For example, if you need your code to increase each number in an array, your pseudocode should be written as, for each number in the array, add 1, rather than something more cryptic like, for number in array plus 1. Second, be concise. Keep each logical step brief and to the point, avoiding unnecessary details. Suppose you want to evaluate a variable and move to the next record if it has a value. You can describe this concisely by writing, if the variable first name is not null, move to the next record. You should avoid longer descriptions that don't add a lot of value, such as evaluate the variable called first name and determine if it has a value. If it does, then the program should move to the next record. The third guideline for writing pseudocode is that developers should structure pseudocode like actual code. Use spacing and structure similar to actual code, including loops, conditionals, and function calls. For example, when writing a function that subtracts one number from another and returns the difference, you can write 3 lines of pseudocode. On line 1, you write function to subtract a from b. The next 2 lines should be indented like they would in actual code. And then line 2 would be written as set variable c equal to b minus a. And then line 3, send back c. You could write the same function as, the function called subtract number should take 2 variables called a and b. Inside the function, a variable c should be set to equal the difference of a subtracted from b, and then send back the value of c. But this hides the structure and is more difficult to understand. The fourth and final guideline for writing pseudocode is that developers should focus on logic. They should concentrate on the program's logical flow rather than specific syntax. For example, if you need to write a loop, you might say repeat until all items are sorted, instead of using specific code syntax. When you write out pseudocode using these guidelines, you can more easily spot logic errors or code blocks that may not work as expected. You can also use pseudocode in reverse to debug it. If your actual code isn't working, you can write out the code block in pseudocode to troubleshoot it. For example, suppose you wrote code where you mistakenly used the greater than symbol to check a variable called number for a negative value. Your code states that if the variable is greater than 0, print the number is negative to the console, else print the number is positive to the console. It might be difficult to spot the logic error when you're searching for the bug. You could write this in pseudocode as, if number is greater than 0, then print the number is negative to the console, otherwise print the number is positive to the console. Using pseudocode, you could more easily spot the error. In this video, you learned how to write pseudocode to outline problem-solving steps. Pseudocode is a powerful tool that developers can use to design and troubleshoot their code. By using natural language to describe code logic, developers can get deeper insight into how their programs will function.
Mastering logical thinking and problem solving is essential for tackling program challenges effectively. We began this module by defining the fundamentals of logical thinking in programming, highlighting the key logical processes and types of logic essential for effective problem solving. Next, we explored the process of deductive reasoning in programming and how this approach can solve problems logically and systematically. Then we examined methods for problem decomposition, simplifying complex challenges by breaking them into smaller, more manageable parts for more effective problem solving. Next, we explored top-down and bottom-up problem-solving strategies, comparing their strengths and their application in different scenarios. Finally, we discovered coding for simple problem solving and learned how to write simple code for simple problem-solving scenarios. Congratulations! You have completed Introduction to Logical Thinking and Problem Solving. Welcome to Algorithms, Flowcharts, and Data Types. This module introduces you to the fundamental concepts of structuring logic with algorithms and flowcharts, and mastering data types in C#. By the end, you'll have skills to tackle complex problems and bring your code to life. We begin by defining algorithms, flowcharts, and data types, highlighting their crucial role in programming. Next, we'll explore the basics of flowchart, learning how to visualize logic, creating practical flowcharts, and analyze them effectively. Then we'll examine the fundamental data types, learning how to identify, categorize, and convert them effectively in programming. Next, you will learn how to declare and initialize variables in C#, covering different data types and the key concepts for effective variable management. Finally, we'll delve into designing algorithms and translating them into C# code, mastering the art of implementing these algorithms efficiently in your projects. By the end of this module, you'll have the foundational skills to structure logic with algorithms, visualize it through flowcharts, and effectively manage data types in C#. Let's get started with algorithms, flowcharts, and data types, and bring your code to life. Algorithms are the foundation of how computers solve problems. Whether it's processing data, making decisions, or controlling the flow of a program, algorithms guide each step with precision and logic. Understanding these structures is essential for anyone writing efficient, effective code. In this video, we will describe the basic structures of algorithms. Let's get started by defining what an algorithm is. An algorithm is a set of step-by-step instructions used for solving a problem or performing a task. Let's imagine you are in a maze and need to find the exit. You're positioned at the maze's entrance, ready to navigate through it. In coding terms, this is where your algorithm starts executing. Your pseudocode will read set position to start. As you start moving, you need to decide which direction to go. This is similar to making decisions in your algorithm. You've moved past the starting point, making your next move into the maze. The algorithm moves to the next position. In pseudocode, you might write, if there is a path to the right, take it, or if there is a wall ahead, turn left. These decisions are like conditional statements in your code, guiding your movements based on certain conditions. To avoid getting lost, you might mark your path with chalk, ensuring you don't take the same path twice. In algorithms, this is similar to keeping track of visited nodes to avoid loops, which can be represented in pseudocode as mark position as visited. As you continue, you encounter dead ends. When this happens, you need to backtrack to the last decision point and try a different path. This backtracking process is a critical part of many algorithms. In pseudocode, you might write, if no unvisited paths are available, return to the previous position. Eventually, you find the exit. This is the goal of your algorithm, to reach a solution. Your pseudocode will conclude with, if exit is found, stop and return success. With this example, we just created an algorithm, or a set of step-by-step instructions, to help us find our way through a maze. In pseudocode, our algorithm looks like this. Set position to start, mark position as visited. While position is not exit, if there is a path to the right and it is unvisited, move right. Else if there is a path forward and it is unvisited, move forward. Else if there is a path to the left and it is unvisited, move left. Else if there is a path backward and it is unvisited, move backward. Else, backtrack to the previous position. Mark new position as visited. If exit is found, return success. Else, return failure. With a solid understanding of what algorithms are, let's explore how they make decisions. The building blocks of these decisions are statements, starting with one of the most fundamental types, conditional statements. A conditional statement allows a program to make decisions and take different actions based on whether a condition is true or false. It is a fundamental building block of algorithms that controls their flow and manages complexity by determining which parts of the code to execute, skip, or repeat. Let's explore conditional statements further with one of the most common types, the if-then statement, which is crucial for making straightforward decisions in your code. An if-then statement is a specific type of conditional statement. It checks a condition, and if the condition is true, executes a block of code accordingly. An if-then statement is like a light switch. Imagine that you are in a dark room and you want to turn on the light. You are now leaving the lit room and you want to switch off the light. In pseudocode, you might write an if-then statement that reads, if the light switch is off, then turn the light switch on. Or, if the light switch is on, then turn the light switch off. First, the if-then statement sets the conditions for the algorithm by checking the position of the light switch. It's either in the on position or off position. Second, it creates an action. If the switch is off, then the action is to turn it on. In this case, if the switch is on, the action is to turn it off. Without conditional statements like an if-then statement, the algorithm wouldn't be able to perform a comparison and make decisions based on it. This analogy of the light switch helps illustrate how conditional statements guide decision-making processes based on specific conditions, similar to how we decide to turn a light on or off based on its current state. Building on our understanding of if-then statements, let's explore a more versatile tool for working with multiple conditions, the switch statement. This will help us manage more complex decision-making scenarios in our algorithms. A switch statement is a programming tool that helps a computer choose from several code blocks to execute. It's a structured way of making decisions when you have multiple possibilities. A switch statement is like a weekly planner that tells you what to do each day of the week. Each day, you look at your planner and follow the specific activity planned for that day. In your weekly planner, each day has a specific task or value to be checked. Each day of the week is a different case. The planner looks at what day it is and decides what task you should do. The action is the task you performed based on the day. If there's not a specific day listed, you could have a default task like do the laundry. Pseudocode example for a switch statement using the weekly planner as an example will be organized as follows. If the day of the week is Monday, then start home project. If the day of the week is Tuesday, then go bowling. If the day of the week is not Monday or Tuesday, do the laundry. With switch statements, we can work with multiple conditions efficiently. Now let's shift focus to categorical statements, which help us organize and classify data logically. A categorical statement is a method for analyzing and classifying statements like all cats are animals or some dogs are not friendly. It uses logical rules to determine whether these statements are true or how they relate to each other. Categorical statements use a system of affirmative or negative statements to determine if something is true or how it relates to something else. These statements are classified based on the relationship between the subject and the predicate or the presumption. They group and categorize data based on certain criteria and are useful for organizing and managing data efficiently. Let's explore the different types of categorical statements. The first one is the universal affirmative statement. If S is the subject or category and P is the predicate or category to which the subject is being related, a universal affirmative statement might be all S are P. In pseudocode, you might type all dogs are mammals. Another type is the universal negative statement, which might be no S or P. In pseudocode, you might write no cats are reptiles. A third type of categorical statement is a particular affirmative statement. Such a statement might be some S or P. In pseudocode, that might be some birds can fly. And lastly, a particular negative statement is some S are not P. In this case, the pseudocode might be some fish are not carnivores. By using these logical structures, we can effectively analyze and categorize different statements and understand their relationships. After understanding how to categorize data, let's examine binary structures where decisions are distilled down to just two possible outcomes. This approach is fundamental in making quick, efficient choices in your code. Binary structures are data structures that are based on the concept of a binary system, where decisions in data organization are made based on two possible outcomes, often represented as true or false, or yes or no. Binary structures involve making decisions based on two possible outcomes. This can be represented through binary decision diagrams where each decision point or node leads to one of two subsequent paths. Let's consider an example where we want to determine if an animal is a fish or a cat based on whether it has fur. In pseudocode, it would look like this. The root question is, does the animal have fur? The binary decision function follows a path on the diagram based on the user's responses. If yes, then it will return the animal is a cat. In this video, you learn the basic structures of algorithms. As we've illustrated, mastering the basic structure of algorithms like conditional statements, categorical statements, and binary structures equips you with the tools to solve problems efficiently and write more effective code. These foundational skills will serve you well as you attempt increasingly complex programming challenges. Imagine trying to navigate a city without a map or GPS. Every decision would be a guess, and you might end up lost or stuck in traffic. In the world of software development, algorithms are your map, guiding you through complex decisions and leading you to efficient solutions. Whether you're a front-end, back-end, or full-stack developer, mastering different algorithm structures can turn you into a problem-solving navigator, ensuring you'll always find the best route to success. In this video, we will apply algorithm structures to real-world examples. Conditional statements in programming, like if-then and switch, are used to control the flow of a program. An if-then statement executes a block of code if a condition is true, while a switch statement allows you to choose from multiple code paths based on the value of a variable. Let's use an example in pseudocode to illustrate a conditional algorithm. In this example, we want to print, "You are eligible to vote when someone's age is over 18, we want to print "you are not eligible to vote" if their age is under 18. To do this, we will set the age equal to 18 by set age equal 18. To set the condition to print for ages over 18, you will use an if-then condition. If the age is greater than or equal to 18, then print "you are eligible to vote." This means if someone inputs an age of, say, 25, it will print that they are eligible to vote. Then we use the else to indicate when the age is not greater than or equal to 18, so that it sets a separate condition to follow in this case. For this example, for anything that is not greater than or equal to 18, it will print "you are not eligible to vote." This means if someone inputs an age of 17, it will print that they are not eligible to vote. Now that we've explored how conditional statements guide decision making based on true or false conditions, let's shift our focus to categorical statements. These are essential when your task involves organizing and classifying data, helping you create clear paths based on specific criteria. Categorical statements in computer code logic are used to classify and group data based on specific criteria. This categorization helps organize data, making it easier to manipulate, analyze, and make decisions based on different data attributes. Let's try an example in pseudocode that demonstrates categorical statements. Imagine that you are organizing an outdoor festival that is targeted towards families. Of the people who pre-registered for the event, you want to know how many kids, teens, and adults already registered to attend. You start by creating 3 empty lists categorized as children, teens, and adults. Next, you establish the criterion for each of the 3 categories. Attendees categorized as children are represented by if age is less than 13, add age to the children list. Attendees categorized as teens are represented by else if age is between 13 and 19. Lastly, attendees categorized as adults are represented by else add age to the adults list. Now the function returns data containing 3 lists, each representing a different category: children, teens, and adults. With categorical statements, we learned how to group data into categories based on characteristics. But what happens when decisions are between just 2 options, like yes or no? That's where binary structures come in. Let's explore how these simple yet powerful structures can drive critical decisions in your programs. Binary structures and algorithms involve decisions that have 2 possible outcomes, much like binary states such as 0 and 1, true and false, yes and no. Let's discuss an example of binary structures in pseudocode. At your festival, you would like to have an event space for adults only, which requires attendees to be identified as 21 or older with a wristband. You want to know how many attendees that RSVP'd are 21 or older. To do this, you will create 2 lists, one for people who are 21 or older and one for people who are under 21. Now for each age in the 2 lists you've created, specify how you want the ages to be grouped by stating, if the age is 21 or older, add the person to the 21 or older group. Otherwise, add the person to the under 21 group. The algorithm iterates through each age in the provided list of attendees. For each age, it checks whether the age is 21 or older using the condition, if the age is 21 or older. If the condition is true, the age is added to the 21 or older list. If false, the age is added to the under 21 list. Once the algorithm is initiated, it will return data in 2 lists, one for those who are 21 and older, and one for those under the age of 21. In this video, you learned how to apply algorithm structures to real-world examples. Applying algorithm structures such as conditional, categorical, and binary structures allows developers to create efficient and effective solutions to complex problems. By understanding and utilizing these structures, you can write clear, organized, and efficient code that enhances the performance and functionality of your applications.
Imagine trying to explain a complex process to someone without using any visual aids. It'd be challenging, right? Flowcharts are like visual maps that help us understand and communicate processes clearly and effectively. By breaking down a process into steps and decisions, flowcharts allow us to visualize how everything fits together. In this video, we will explain the basic components and symbols used in flowcharts. A flowchart is a diagram that represents a process showing the steps as symbols of various kinds, and they're ordered by connecting them with arrows. HHAI is a telemedicine company offering virtual consultations and health monitoring services. The following example flowchart demonstrates the booking process for a virtual consultation. In a flowchart, rectangles represent processes or actions. They indicate a step where something happens, such as a calculation or an operation. For instance, in the HHAI flowchart, a rectangle might represent the process of entering patient details. Diamonds represent decision points. They indicate a point where the process can branch based on a yes-no question or a true-false condition. In the HHAI consultation booking flowchart, a diamond might represent a decision point for verifying if the patient already has registered or has an existing account, or if they still need to register. Arrows show the direction of flow in a flowchart. They connect different symbols and indicate the sequence of steps in the process. In the HHAI flowchart, arrows would guide the user from entering patient details to verifying the account and then booking the consultation. Ovals represent the start and end points of a flowchart. They indicate where the process begins and ends. In the HHAI consultation booking flowchart, the start oval might be labeled Begin Booking, and the end oval, Booking Confirmed. Now let's explore the 4 steps to creating an effective flowchart. Starting with step 1, you define the process. Clearly define the process you want to visualize. Identify the starting point, key steps, decision points, and the end point. This helps in outlining the flowchart structure. For example, define the process of booking a consultation on HHAI from start to finish. Step 2, break down the process into key steps and decision points. Where are the key steps taking place in the workflow, and where do the decisions happen? Lay these items out in a logical order. Use rectangles in the flowchart to define processes and diamonds for decisions. Ensure each step is clear and necessary for completing the process. Step 3, use standard symbols to draw the flowchart. Start with the oval for the starting point, connect processes with rectangles, and decision points with diamonds. Remember to use arrows to indicate the flow of control. For HHAI, draw the flowchart starting from Begin Booking, including steps like enter patient details if the patient registered, and booking confirmed. Lastly, step 4 is to review the flowchart to validate that it accurately represents the process. Check for any missing steps or unclear decision points. Ensure that the flow is logical and easy to follow. At HHAI, the team would review the consultation booking flowchart to confirm it covers all necessary steps and decisions. In this video, you learned how to explain the basic components and symbols used in flowcharts. Grasping the fundamental symbols and structure of flowcharts is vital for visualizing and communicating processes clearly. By using standard symbols like rectangles, diamonds, arrows, and ovals, and following a structured approach, you can create straightforward and logical representations of any process. Think about the last time you ordered something online. With just a few user actions, your order was processed and on its way to you. But behind those simple actions is a complex series of steps, verifying payment, checking inventory, and calculating shipping. Flowcharts simplify these intricate processes, turning them into clear, manageable steps. In this video, we'll create flowcharts to visualize the logic of a conceptual program. Let's explore an example flowchart of a simple login process. The flowchart will represent the steps a user takes to log into an application. Start the flowchart with an oval to indicate the process has begun. An oval shape is a universal flow symbol that represents a starting point of a flowchart. Before moving on to the next step in the flowchart, you will want to indicate which way the sequence flows by using an arrow to point to the next step. As you build your flowchart, continue using directional arrows to indicate the proper flow to the next step. In this example, the process flow is moving in a downward direction, so the arrow connecting the oval to the rectangle is pointed in a downward position. Now that you have established the flow, state the first process that will occur in the program sequence. Use the universal flowchart symbol of a rectangle to indicate a process. In this example, display the login form. Consider the next process in the sequence using another rectangle to indicate the action, which in this example is to enter credentials. Think about what happens after the user has entered their credentials. What comes next? The next step in the process is to submit the form where users entered their login credentials. Use a rectangle with the word Submit Form to note this process. Notice the diamond-shaped symbol in the sequence with the words Validate Credentials followed by a question mark. This is where a decision needs to be made, and in this case, the program will decide if the login credentials are valid. This is considered a split in the road, where two paths will take the user through different actions. If their credentials are valid, represented by yes, the path will continue to the right. If their credentials are not valid, represented by no, the path will continue to the left. Let's say the user credentials are valid, following the path to the right. The next step in the process indicates that the user will be able to log into the application. Now let's say the user's login credentials are not valid, so the next step in the process is to create an account. Notice the vertical line that takes the path back to the top of the flowchart where the login process began. For users that need to create an account, the flow continues back through the same decision point where the program will validate the user's credentials. Assuming the login credentials are valid, the user will now be able to log in. The flowchart ends with the same shape it began with, an oval, with the words Login Process Complete. This indicates the process is complete. In this video, you learned how to create flowcharts to visualize the logic of conceptual programs. Creating flowcharts to visualize the logic of conceptual programs is an essential skill for developers. By using flowcharts to represent processes like logging into an application or sorting algorithms, you can simplify complex logic and communicate it effectively. Picture this. You're designing a new app and everything is working perfectly until you hit a problem. Users are reporting errors that seem to come out of nowhere. After digging through the code, you realize the issue wasn't in the programming. It was in the flowchart that guided your design. Just like a faulty blueprint can lead to a collapsed building, an inaccurate flowchart can bring your entire project to a fast stop. The same goes for flowcharts. If they don't accurately represent the logical steps, they can lead to confusion and errors. In this video, you'll learn how to analyze flowcharts to ensure they accurately represent logical steps. Having unclear instructions can be easily prevented with attention to detail and verifying the flowchart for accuracy. Let's explore the 4 easy steps to analyze the accuracy of a flowchart. HHAI is a telemedicine company offering virtual consultations and health monitoring services. Let's examine their flowchart for virtual consultation bookings. Begin with step 1, analyze each step. Start by reviewing each step in the flowchart and checking if it accurately represents the logical part of the process. Make sure that all necessary steps are included and correctly ordered. In a flowchart for HHAI's virtual consultation booking, analyze the steps such as enter patient details and confirm booking, and determine that they are clearly represented in the correct sequence. Step 2, check decision points. Carefully check each decision point represented by the diamond symbol to ensure it works correctly for all possible outcomes and leads to the appropriate next steps. In the HHAI booking process, a decision point like, is the patient registered, should have a clear path for both yes and no outcomes. Step 3, validate the flow of control. Ensure that the arrows or flow of control correctly connect each step and decision points in the proper sequence. Verify that the flowchart doesn't have any disconnected steps or loops that don't make sense. For HHAI, ensure that the flow from enter patient details to is the patient registered and booking confirmed is logical and seamless. Finally, step 4, confirm the start and end points. Make sure the flowchart has a clear starting and ending points represented by an oval symbol. the flowchart should have a defined starting point and a logical conclusion. In HHAI's flowchart, the start point might be begin booking, and the end point might be booking confirmed. Now that you're familiar with the 4 steps to analyze the accuracy of a flowchart, let's discuss some common flowchart mistakes. Missing steps. Omitting essential steps can lead to incomplete or inaccurate flowcharts. Always double check to ensure that all critical steps are included. For example, forgetting to include the enter patient detail steps in a registration process flowchart can lead to an incomplete process. The next common flowchart mistake is incorrect sequence. Placing steps in the wrong order can confuse the flow of the process. Verify that each step logically follows from the previous one. In the HHAI booking flowchart, ensure enter patient details comes before book consultation. Another common flowchart mistake is ambiguous decision points. Ambiguous decision points are vague or unclear and can mislead users. Make sure each decision point is specific and has clear outcomes. Avoid using generic terms like check without specifying what is being checked. The final common flowchart mistake is poorly defined start and end points. Unclear start or end points can make the flowchart confusing. Ensure that the flowchart has a well-defined starting point and a clear conclusion. At HHAI, reviewing flowcharts is a critical step for the development process. For instance, the team reviews the consultation booking flowchart to ensure all steps such as enter patient details, is the patient registered and booking confirmed, are accurately represented and logically ordered. Decision points like is the patient registered are checked for clarity and proper flow. This thorough review process helps HHAI avoid common mistakes and ensures a smooth, user-friendly experience. In this video, you learned how to analyze flowcharts to ensure they accurately represent logical steps. Analyzing flowcharts to ensure they accurately represent logical steps is crucial for creating clear and effective processes. By verifying each step, checking decision points, validating the flow of control, and confirming starting and end points, you can create accurate and reliable flowcharts and avoid common mistakes like missing steps, incorrect sequences, ambiguous decision points, and poorly defined start and end points. This ensures your flowcharts are comprehensive and easy to follow.
Think of programming as a cooking recipe with data types as your ingredients. Just like potatoes, salt, and oil are essential for creating a dish, data types like integers, doubles, strings, and booleans are the building blocks of every program. Now imagine you need bowls, cups, or jars to store and use these ingredients as you cook. That's where variables come in. Variables are the containers that hold your data, allowing you to mix, measure, and prepare your program just like you would a recipe. Data types are the ingredients, and variables are the containers that store and manage those ingredients. In this video, we will describe the fundamental data types used in programming. Let's begin by defining what variables and data types are. Variables are a way to store data in a program. Think of it like a labeled container where you can put information, such as a number, a piece of text, or a true-false value. This labeled container can be used and changed throughout the program. Now that we have defined what variables are, let's define what data types are. Data types are classifications of data in programming that define the types of values a variable can hold. Understanding data types is crucial because they determine the operations that can be performed on the data and how the data gets stored. Now let's explore the 4 basic data types: integers, doubles, strings, and booleans. Each type has its own unique characteristics and uses, so we will examine each in more detail, starting with integers. Integers store whole numbers, both positive and negative, and do not include fractions or decimal numbers. And they are used for counting and arithmetic operations. For example, using integers for basic arithmetic might be written like this in pseudocode: integer 5 plus integer 10 equals 15. In basic terms, this reads 5 plus 10 equals 15.
The integer data type is only for values that are whole numbers. But what if we have values that are decimals? For these more precise values, we use the data type called double. Doubles are referred to as floating point numbers because the decimal place can float anywhere in the number. Doubles are used when a value of greater precision than a whole number, like a fraction or a decimal, needs to be stored. Examples might be when performing calculations in scientific research or finance. An example of calculations with doubles might read as follows. Double 7.15 times double 3.2 equals 22.88. In basic terms, this reads 7.15 multiplied by 3.2 equals 22.88. While the integer and double data types work with numbers so that we can perform calculations, what about all the other kinds of data we want to work with? To store characters that do not represent numbers, like letters, words, and exclamation points, we use the string data type. Strings are sequences of characters used to represent text. Strings are essential when you need to work with text in your programs, whether it's a single word or a sentence. Strings can include letters, numbers, symbols, and spaces, and often are used to manage and manipulate textual data. Note that strings can include characters that are numbers, but they're not considered numbers that can be used for calculations. They're considered text. Strings are used to store and manipulate text data through operations like concatenation. This involves combining multiple pieces of text. Let's illustrate this with an example. An example string manipulation is to concatenate strings. Set a variable to hold the first name as John. Set another variable to hold the last name as Doe. Combine the first and last name with a space in between to create a full name. Store the combined result in a variable for the full name. John plus a space plus Doe equals John Doe. This example reads the first name John plus a space and plus the last name Doe for the full name John Doe. Finally, let's examine the Boolean data type, which is used for logical operations. Booleans are particularly useful when making decisions in your code, like determining whether a condition is true or false. Booleans store data as either true or false. They manipulate data through logical operations like AND, OR, and NOT to control program flow and decision making. Now that we understand the importance of Booleans in decision making, let's use an example to illustrate this. A Boolean logic example using Booleans in conditions. Start by setting a condition. For instance, the phrase, set a variable to represent whether it is raining to false, sets a parameter that must be false. But what happens if it's raining? The program will display a message, take an umbrella. Otherwise, the program will display, enjoy the sunshine. Since you have been through examples of each data type and understand their purpose, let's put them into a single application to demonstrate how they might work together. In a weather application, different data types are used to handle various information. Integers for temperature, int temperature equals 25. Doubles for humidity, double humidity equals 75.5. Strings for descriptions, string weather description equals sunny. Booleans for alerts, bool is storm warning equals false. By appropriately using these data types, the application can accurately represent and manipulate weather data. Now that you're familiar with the four basic data types, integers, doubles, strings, and booleans, let's discuss how different programming languages might treat data types in terms of how strict or flexible they are about enforcing data type rules. We will explore the concepts of type-safe and non-type-safe languages. Type-safe languages are programming languages that enforce strict data type rules. Strict enforcement of data type rules reduces errors by ensuring that variables are used consistently with their defined types. In contrast, non-type-safe languages offer more flexibility, but this comes with its own set of challenges. Non-type-safe languages are programming languages that are more flexible about data type rules than type-safe languages. Non-type-safe languages do not offer strict enforcement of data type rules, which can lead to unpredictable behavior like errors that are difficult to debug and potential security vulnerabilities. Advantages to non-type safe languages offer faster development, greater flexibility, and more concise code by not requiring explicit data type declarations. This makes them ideal for rapid prototyping and dynamic environments where handling varied data types is essential. It's like building with plastic bricks. You can grab any piece you want without worrying about the rules. You can build quickly and try different ideas. That's like using a non-type safe language. To illustrate this, let's use the example involving a weather application. When using a type-safe language, each type of data in your weather app, like temperature or humidity, has strict rules. For example, you must store the temperature as a whole number or decimal depending on the precise needs, humidity as a float or double, and weather descriptions as a string. These rules make sure your weather app works correctly, but can slow you down because you have to get the data types exactly right. This makes your app more reliable, but takes longer to set up. When using a non-type safe language, you can mix different types of data freely as the language figures out how to handle it automatically without needing you to specify the type. For instance, using an integer or decimal for temperature, integer or decimal for humidity, and a string for the weather description, all together without strict rules, allowing you to build the app faster. However, you have to be careful not to cause errors by using the wrong data types. In this video, we described the fundamental data types used in programming and how using them effectively is essential for writing efficient and error-free code. Understanding data types is one of the fundamental building blocks you will need as a developer. You get a lot more opportunities to use this knowledge as you progress through this course and as a working developer. Imagine you work at a fruit store and you've been tasked with putting prices on each piece of fruit and putting them out for customers to find. To do this, you'll need to be able to identify what kind of fruit each piece is so that you know where to put it in the store and what price to put on it. If fruit is put in the wrong place or has the wrong price, customers won't be able to find it, or they will pay too much or too little for it. We have to do that in programming too. We have to be able to identify and categorize variables to ensure they work in our program properly. In this video, we will identify and categorize different data types through examples and exercises. To categorize data types, we're going to follow these 4 steps. Step 1, start with identifying data types. Step 2 is checking data type compatibility. Step 3 is converting data types. And step 4 is validating the conversion. Let's examine each of these steps more closely. Step 1, identifying data types, uses programming language functions to identify data types. For example, you can identify the variable by asking what type it is, similar to how you might pick out an apple from a produce stand that offers different fruits. To do this, you use the function getType. The use of the term function might be new to you, so let's define it. A function in programming is simply a block of code designed to take input, process it, and return an output. For example, the getType function takes in a variable, processes what kind of data type the variable is, and then gives us the data type as output. In C#, let's start by declaring our variable string myVariable equals this fruit is an apple. We can now use the getType function to find out the data type for the variable myVariable. We write this function by starting with a new kind of data type called type. Type is used in C# to represent the type of an object or variable. In this example, it's the variable name myVariable. We also need a variable to store the result of the type that the getType function returns to us. So let's use the variable name dataType. So the function will read as follows: type dataType equals myVariable getType. This asks the computer to check the data type of the variable myVariable and store the resulting value in the variable data type. Then we can ask the computer to tell us the value of data type by asking it to print it to the console using this line of code: console.writeLine dataType. We get the result in the console of system.string. With the data type identified, we move to step 2, checking its compatibility. The function will determine if the data type needs conversion based on the context. It uses conditional statements to compare a variable's type against the expected type. The function myVariableGetType will determine the data type. The function performs specific actions or prints messages based on the type. This approach ensures that the variable's type is compatible with the expected operations. An example in C# might be where the variable 123 is an integer. We're declaring a variable named myVariable, but instead of specifying a concrete data type like int or string, we're using the object type. In C#, object is the most generic type. It can hold any type of data, including numbers, text, or even complex objects. By using object, we're allowing myVariable to potentially hold any type of value. We're assigning the variable 123 to myVariable. Since 123 is technically an integer, but right now myVariable is just an object that happens to contain an integer, we're using an if statement to check the type of myVariable. The method getType is called on myVariable, which returns the actual data type of the value stored inside it. Type of int represents the type int in C#. This line is comparing whether the actual type of myVariable, obtained using getType, is the same as the int type. If my variable contains an integer, this comparison will be true, and the code inside the if block will run. If it contains any other type, the code in the else block will run. If my variable is indeed an integer, the program will execute the first console.writeLine statement. It will print a message saying the variable 123 is an integer. The $myVariable syntax inserts the value of my variable directly into the string. So if my variable is 123, the message will read, the variable 123 is an integer. If my variable is not an integer, the program will execute the second console.writeLine statement. This prints the variable 123 is not an integer. To sum up the checking data type compatibility, declare a variable, myVariable, and assign it a value. In this case, it's 123 stored as an object. Check the actual type of myVariable. If it's an integer, print a message saying it's an integer. Otherwise, print a message saying it's not an integer. The output based on the condition should be the result of the type comparison, the appropriate message that is then printed to the console. This code is a simple but powerful example of how type checking works in C#. It shows that even though a variable is declared as a general object, you can still inspect and react to the actual data type it holds. This makes C# both flexible and type safe. The next step is step 3, converting data types. Step 3 happens after the program has determined the variable and checked it for compatibility with another data type. The function int.parse takes a variable as input. It converts the variable to the desired data type and returns the converted value. If the target type is unsupported, it raises an error. An example in C# might be where the variable is a string represented as 123 and it's converted to an integer 123. In this example, we're declaring a variable named myVariable and assigning the string value of 123. Notice that 123 is in quotes, which means that myVariable is actually a string. This means that the variable is treated as text, not as a number. Even though the string 123 appears as a number, it's currently just a sequence of characters, not something you can perform arithmetic operations on. We're converting the string 123 into an integer using the int.parse method. Int.parse is a method that takes a string as input and converts it to an integer, assuming the string represents a valid number. If the string contains a non-numeric character or isn't a valid number, this method will throw an error. After this conversion, number will hold the integer value 123, not the string version of 123. This allows you to perform numeric operations with the number if you need to. Converting a string to an integer is useful when you're dealing with user input or data that may come in as text, but needs to be treated as a number in your program. This line prints the value of number to the console. The output will be 123, but now it's printed as an integer, not as text. This means that if you wanted to perform math operations on this variable later, you could. To recap, we start with a string that looks like a number, but it's actually just text, in this case, 123. So we converted the string to an integer using int.parse converting string 123 into the integer 123. Finally, you print the integer value to the console, showing that the conversion was successful. The final step is step 4, validating the conversion. A function can validate a data type conversion by checking whether the conversion was successful and by managing any errors that may occur during the conversion process. We are declaring a variable named myVariable and assigning it the value 123 as a string. int.tryParse is a method that tries to convert a string to an integer. Unlike int.parse, which gives an error if the conversion fails, int.tryParse returns a Boolean value, true if the conversion is successful and false if it's not. There are parameters built into this function. The first parameter, myVariable, is the string we're trying to convert. The second parameter, outIntNumber, is where the converted integer will be stored if the conversion is successful. The out keyword allows the method to pass this value back to the caller. The code checks if int.tryParse successfully converts myVariable to an integer. If it does, the value is stored in number and the condition evaluates to true, so the code inside the if block runs. If the conversion fails, the condition evaluates to false, and the code inside the else block runs. If the conversion is successful, the program executes the first console.writeLine statement. It prints a message that says conversion successful, followed by the converted integer value. The curly braces allow us to group multiple lines of code that will execute when the condition is true. For example, if my variable was 123, then int.tryParse would successfully convert it, and the output would be conversion successful 123. If the conversion fails, for example, if my variable contained ABC instead of 123, the program executes the second console.writeLine statement, printing conversion failed. This lets the user know that the string couldn't be converted to an integer. Let's briefly recap how the function validates the data conversion. We started with a string 123, which looks like a number, but it's actually text. We tried to convert the string to an integer using int.tryParse. The program attempted to convert the string to an integer and stored the result in a number variable if it's successful. If it is successful, the console prints a message with the converted integer value. If unsuccessful, the console prints a message saying the conversion failed. In this video, you learned how to identify and categorize different data types through examples and exercises. By mastering how to identify and convert data types, you can reduce the chances of bugs in your programs and ensure that they work as designed. Working with data in programming can come in many forms. But what happens when data you're working with isn't in the right format? That's where understanding how to convert between data types can help you build systems that can work with each other. In this video, we'll explore how to convert between data types in programming. Let's begin by defining data type conversions. Data type conversion is the process of changing data stored in a variable from one type to another, like converting a variable from a string to an integer. Data type conversion is essential when operations or functions require specific data types. There are two types of data type conversion. Let's explore both types, starting with implicit conversion. Implicit conversion is the ability to convert data types automatically without specific instructions from the programmer. For example, suppose we declare a variable named num1 as an int with a value of 5, and a variable named num2 as a double with a value of 3.14. We then create a double variable called result and assign it the sum of num1 and num2. Because the program has been asked to add two different data types, it will perform an implicit conversion. It will automatically convert the integer to a double. In this case, if we write the value to the console, the result will be 8.14, a double data type. In many cases, leaving data conversion to the program can be risky since the data may not be converted as the developer expects. Instead, the developer may choose to state how they want variables converted. This is called explicit conversion. Let's explore this concept next. Explicit conversion is the process of manually converting a value from one data type to another. Several methods exist for explicitly converting data types. We'll cover two of the most common: casting and parsing.
Let's examine each of these programmatic methods further, starting with casting. Casting converts a variable from one type to another, explicitly stating the desired type. An example of casting in C# might be to convert a double to an integer. Suppose we declare a variable called pi_var as a double. We initialize this variable with the value 3.14, a double value. Then we declare another variable called pi_int as an integer. In order to assign this variable to the value of the double variable pi_var, we have to cast pi_var to an int. We do this by placing the type we want to cast in parentheses before the variable name pi_var. In C#, the cast is written as int pi_int equals open parentheses int close parentheses pi_var semicolon. The new value of the variable will be printed to the console, and it will be a value of 3, an integer. Now let's explore the data type conversion method called parsing. Parsing is used with the string data type. Parsing involves interpreting a string representation of data and converting it to another data type like an integer. An example of parsing in C# might be to convert a string to an integer. Suppose we're working with a string variable named myString, which has a value of 1, 2, 3. Even though the value is 1, 2, 3, it's not numerical data, but text data. It can't be used in mathematical operations because it's a string. We can convert myString to an integer by parsing it. To parse a variable, you can use methods that are part of the C# system. The methods evaluate the value you want to convert and attempt to change it to the new type. To convert myString to an integer, we use the parse method that is a part of the C# int type. The code to parse myString to an int is int.parseMyString. In this example, the string 1, 2, 3 is converted into the integer 1, 2, 3 by using the parse method. Data type conversion is used in a wide variety of scenarios. For example, a banking application might accept user input on their website as string data. This data needs to be parsed into numeric types like a double for accurate currency calculations and storage in a database. After the calculations have been performed and stored, these values are converted back into strings for display, formatted with currency symbols. This process ensures precision, interoperability, and the reliability of financial data. In this video, you learned some methods for converting data types. Applying conversion methods like these ensures that your data is in the right format for the tasks you need to perform. Ever wonder how computer programs remember things like a customer's name and account number, or the date something was purchased? My work calendar remembers my birthday. How does it do that? It happens with the use of variables, one of the most fundamental programming tools you will use throughout your journey as a developer. In this video, we will define what variables are and their role in programming. Variables in computer code are named storage locations in memory for storing data that allows programmers to store, retrieve, and manipulate data during a program's execution. For example, you can store a user's age, a product price, or any other piece of data in a variable, making it easy to work with this information later. Variables must be named or labeled appropriately through meaningful naming conventions so that their data can be easily retrieved later. Let's discuss some best practices for naming variables. One best practice for naming variables is using descriptive names. It's important to choose names that describe the variable's purpose. For example, age, total price, or username are descriptive names that make the code easier to understand. Avoid single letter names like A, B, or X. Another best practice for naming variables is following naming conventions. In C#, for example, it's common practice to use camel case for variable names. This means starting with a lowercase letter and capitalizing the first letter of each subsequent word, like user age, total amount, and first name. When using camel case, words are placed together without spaces, hyphens, or underscores. For example, user age, total amount, and first name follow the camel case convention. Another best practice for naming variables is to consider the scope.
The scope of a variable refers to where it can be accessed in the code. Use meaningful names with the appropriate scope. Here's a simple example of global and local scope. Think of a school. The principal is a global figure who can make decisions for the entire school, so they are accessible everywhere. Global scope. Now, inside a classroom, the teacher is only in charge of that specific room, local scope, and can only make decisions within that room. The principal can affect the whole school, but the teacher's influence is limited to the classroom. In coding terms, a global variable is like the principal. It can be accessed anywhere in the program. A local variable is like the teacher. It can only be accessed within a specific function or section of code. Now that you understand what variables are and some common best practices for naming them, let's explain how to create them. In programming, we use the term declare to describe this process, as in, let's declare a variable. Let's complete some examples using this programming language C#. Declaring an integer variable to store an age might be int age equals 25 semicolon. The int or int part is short for integer and tells the program that the variable being declared is an integer data type, and age is the variable name. It's how we will refer to this variable throughout the code. We then use an equal sign to assign a starting value for the variable, and we finish with a semicolon, which is used in C# to indicate the end of that line of code. Therefore, with this line of code, we created or declared that the variable age is an integer with a value of 25. Let's explore some more examples to illustrate variables of different data types. Our age variable in the last example is an integer with a value of 25, a whole number. This is fine when working with whole numbers, but what if we want a variable that can be a decimal, like a product's price? We will then need to use a data type called double. Declaring a double variable to store the price of a product, double price equals $19.99, semicolon. With this line of code, we declared that the variable price has a data type of double and a value of $19.99. Now, what if we want a variable that can store text like a person's name? For this, we will use the string data type. Declaring a string variable using C# to store a user's name. String username equals, quote, John Doe, end quote, semicolon. With this line of code, we declared that the variable username has a string data type and a value of John Doe. Note the quotes around John Doe. This is a requirement when using the string data type. Finally, we have the data type Boolean. This data type has just two possible values for the variable, true or false. Let's use an example to illustrate how to declare this type of variable using C#. Declaring a Boolean variable to store a true-false value, bool is student equals true, semicolon. With this line of code, we declared that the variable is student has the data type bool, short for Boolean, and a value of true. In this video, you learned about variables and their role in programming. You also learned some of the best practices for naming variables and declaring them using the C# programming language. Understanding how to use variables effectively is a critical part of writing code. You will build on this knowledge as you continue on this journey to becoming a developer.
Imagine trying to perform a calculation only to find that your numbers don't add up correctly. You look closer and realize the problem. What you thought were numbers were actually being treated as text. This is what happens when data types are used incorrectly in programming. The power of data types lies in their ability to store information in the right format, enabling accurate calculations and efficient operations. Without them, even the simplest tasks can lead to confusing results and unexpected errors. In this video, we will declare variables of different data types in C#. Variables hold data, and data comes in various formats or types like numbers, text, and true-false values. You can declare variables to hold a specific type or to hold any type of data. Now let's examine how C# handles variables. In C#, you declare variables so that they can only hold data of a specific type. Languages like C# that require variables to be declared with a specific type are called type-safe because the programmer always knows what the variable type will be. In other words, the type is safe once it's declared. For example, if you declare a variable as a string, your program will treat the data it contains as text. Common data types in C# include integer, double, string, boolean, and array. Each type uses a specific keyword. In contrast, JavaScript is a loosely typed programming language. In JavaScript, variables can hold any type of data, and the program determines the type of data the variable holds when the application runs. In order to declare a variable, developers use a specific syntax. Syntax refers to the set of rules that define the structure and arrangement of elements in a programming language. It's the vocabulary of the language. Now let's explore the syntax developers use to declare variables in different programming languages. First, declaring a variable starts with the type keyword, like string, telling the program what kind of variable to store. Next, the type keyword is followed by the variable name, an equal sign, and then the value the variable will store. Since a declared variable can hold any type of value in JavaScript, you can use the general type keyword var when declaring any variable. Next, let's investigate some examples of variable declarations of different types. In C#, you declare integer variables using the int keyword. Suppose you wanted to create a variable called age that stored a number representing a person's age. You want to set the initial value of this variable to 25. In C#, you would write the code as int age equals 25. In JavaScript, you can write the declaration as var age equals 25. Double variables in C# are declared using the double keyword. Double variables hold numeric data that include decimals. For example, if you wanted to declare a variable named temp to hold temperature data, you would write C# as double temperature equals 36.6. Similarly to the int declaration, in JavaScript you would declare the variable as var temperature equals 36.6. The previous examples show how you can declare variables that hold numeric data. Now let's explore how to declare variables that hold other types of data like text data and true-false values. String variables hold text data. In C#, the syntax for declaring string variables uses the string keyword. To declare a variable called name as a string variable that holds the value Alice, you would write the code as string name equals Alice. An example of a string variable declaration in JavaScript is var name equals Alice. Notice in both languages the data you assign to the variable has quotes around it. This is required when declaring string variables in any programming language. The next type, Boolean variables, are declared in C# using the bool keyword. Booleans store true and false values. For example, to declare a variable isStudent as Boolean in C#, you would use the syntax bool isStudent equals true. In JavaScript, you can declare it as var isStudent equals true. So far, we have examined how to declare variables to store a single value. The value can be changed, but they still have just one value at a time. Programming languages have a type called arrays that can store more than one value at a time. An array is a data structure that stores a collection of values sequentially, typically of the same type. Let's explore how to declare an array in both C# and JavaScript. In C#, arrays are declared using square brackets after the data type and the values between braces. You would write an array for a collection of integer values as int brackets numbers equals 1, 2, 3, 4, 5. In JavaScript, this array would be declared as var numbers 1, 2, 3, 4, 5. A JavaScript array declaration doesn't require brackets after the var type keyword, but does use brackets around the values. To recap, C# is type safe, requiring explicit data type declarations, which ensures precision and reduces errors. For examples, numbers can't be mistakenly treated as text. In contrast, JavaScript is dynamic, allowing variables to hold any type, though this can increase the risk of errors. Understanding these differences helps you write more reliable code in each language.
In this video, you learned how to declare variables of various types in C# and compare them with JavaScript. You also covered how to declare arrays in both languages. Variable declaration is fundamental to programming and ensures that data is stored and manipulated correctly. Imagine you're packing for an important trip. You need some things to stay exactly as they are, like your passport, while other items like clothes can be swapped or changed based on the weather. Variables in programming work much the same way. Some need to be flexible, allowing adjustments, while others must remain constant to keep your program running smoothly and predictably. In this video, we will use variable declaration keywords in C#. In C# and JavaScript, variable declaration keywords are words that specify how variables are declared and managed, defining scope, mutability, and sometimes the type of variable. A variable's mutability is its ability to be changed or modified after it's been created. A variable is mutable if it can be changed and immutable if it can't be modified after it's been created. Common data types in C# include integer, double, string, Boolean, and array. When you declare a variable using these type keywords such as int, double, or string without applying any additional modifiers, the variable is mutable. This means that after the variable is initialized, its value can be changed or reassigned during the program's execution. For example, we declare myNumber as an int and set its initial value to 10. It's a mutable variable because you can modify its value after it has been declared and assigned. We can immediately change the value to 20 to demonstrate its mutability. In JavaScript, variables can hold values of any type, and by default they are mutable. Without additional modifiers, you can use the var keyword to declare a mutable variable, meaning its value can be changed at any point in the code. Now let's explore how to create immutable variables in the C# and JavaScript programming languages. In C#, variable declaration keywords like const and read-only before the type keyword sets a variable as immutable. In JavaScript, similar concepts are managed with let and const. Now let's examine how these phrases work in C# to declare mutable and immutable variables. In C#, const is used to declare variables that can hold a value that cannot be modified after initialization. They have a constant value throughout the application's operation. Suppose you created a game program with a top possible score of 100. You need a variable that you know will always hold this maximum value. In C#, you declare a value using const by writing the code const int max value equals 100. This means that max value is a constant integer variable whose value is set to 100 and cannot be changed throughout the program. The const keyword ensures that the variable max value remains immutable, meaning its value is fixed and cannot be modified after its declaration. In JavaScript, you use const to declare a variable that can't be changed, meaning the variable's value can't be reassigned. For example, const max value equals 100, the max value variable cannot be given another value. However, there is an important exception. If a variable declared with const holds an object or an array, you can modify its contents, but you still cannot reassign the variable to a new object or array. This means you can add or remove members from the object or array, but you can't reassign it using the equal sign. Now let's examine another type of declaration variable keyword that creates immutable variables, and this is called read-only. In C#, read-only is used to declare variables that can be assigned a value only once at the time of declaration, or in a special code block called a constructor that runs in the same group of code in which the variable is declared. For example, in C# you can declare a read-only variable called maxAttempts. In a constructor called setMaxAttempts, you set the maxAttempts variable equal to 5, and then write the number of maximum attempts to the console. Because of the use of the read-only keyword, the max value variable can only be assigned once during the constructor. JavaScript doesn't have a keyword like read-only to make variables unchangeable. However, when you use const with simple values like numbers or strings, it works similarly because you can't change the value after it's set. Properly managing data in your programs will make them easier to manage, more secure, and cause fewer bugs.
Whether you need mutable or immutable variables will depend on the context, but you'll use both as you grow your programming skills. In this video, you learned how to use variable declaration keywords in C# and compare them with JavaScript, working through examples illustrating how const and read-only keywords can help manage a variable's mutability and immutability. Understanding how to use these keywords is essential for writing robust and maintainable code, and it will be a big part of your work as a developer. In any C# program, variables are fundamental for storing data, but how you declare and manage them impacts how your code behaves. Some values like a player's score in a game may change over time, while others such as mathematical constants should stay fixed. In this video, we will declare and assign variables using keywords for different data types. We'll explore mutable and immutable variables, illustrate how assignments work, and show the effects of immutability. Finally, we'll explore what happens when you attempt to assign an incorrect data type. First, let's examine mutable variables. These are variables that enable you to reassign them after they've been declared. This flexibility is useful in dynamic scenarios where the variable's value will change during the program's execution, such as in a program that will track a game's score. For example, we can declare a mutable variable score and assign it the value of 10. This variable is mutable because it contains no modifiers that would indicate to the program that it shouldn't be changed. We'll explore these modifiers shortly. After declaring a mutable variable, you can change its value at any point. For example, we can reassign score to 20. This flexibility is key when working with variables that require updates. Now let's examine immutable variables. These are variables that cannot be changed once they're assigned. Immutable variables are good for scenarios when you need a variable that will maintain a consistent value while the program runs. In C#, we declare immutable variables using the const keyword. We can declare a variable called pi and assign it the value of 3.14159. If you try to assign a new value to an immutable variable, C# will produce a compile time error. In this example, attempting to change pi to 3.14 results in an error. Immutability helps keep important values constant throughout your program. In the previous examples, we assigned a value to a variable at the time we declared the variable. Here's another example. Age is declared as a mutable integer with an initial value of 25, while the name variable is declared as an immutable string with the value Alice. Assigning a variable at declaration is a common practice in C# to make sure variables are initialized or have a value from the moment they're declared. Now let's discuss the importance of data types and how variables are assigned when they're declared. In C#, assigning a value of the wrong data type will result in a compile time error. This means that when the code you write is converted to code the computer can understand, the tool you use will tell you that you can't make the conversion correctly. For example, you cannot assign a string to an integer variable. Trying to assign the text value 10 to a variable called score, which is declared as an int, will cause an error because the types don't match. Now let's investigate this topic further by working through an example. Imagine you're building an application for a fitness tracker. You declare the variable username as an immutable string, and their step count as a mutable integer steps. As the user walks, you can update the step count. The value of steps is mutable, so it can be updated to reflect the user's progress. However, the variable username remains constant throughout the program, ensuring consistency in user data. In this video, we declared and assigned variables using keywords for different data types. We explored mutable and immutable variables, how reassignment works, and how to avoid errors related to data types. By using these tools, your variables will behave as expected and you'll avoid common coding mistakes. Algorithms are at the center of every program you write, from the simplest to the most complex application. Whether you're sorting a list of numbers or creating a game, mastering the art of algorithm design is key to transforming your ideas into functional, efficient code.
In this video, we will design a simple algorithm to solve a given problem. To structure our approach to designing algorithms, let's break it down into a couple of steps and explore each step in detail. The first step in designing an algorithm is understanding the problem and setting a goal. This means knowing what you want the algorithm to achieve. For example, let's say we want to create an algorithm to find the largest number in a list of numbers. Our goal here is clear: identify the highest value in the list. We understand the problem and our goal. In the next step, we can begin to diagram and outline it. When we diagram and outline a solution, we are just breaking down the problem into smaller, easier steps. To put this into practice, let's take our example of finding the largest number in a list and designing our algorithm using pseudocode. We start with the first number in the list and then compare it to the second number in the list. If the second number is bigger than the first number, it becomes our new largest number. After identifying the larger number in the first comparison, we'll continue this process for each number in the list until all numbers have been compared. Now that we've gone through all the numbers in the list, the last largest number is the result. Let's illustrate how this algorithm works using an example with an actual list of numbers. Our list of numbers is 7, 2, 8, and 3, and our goal is to find the largest number in the list. The first number in the list is 7. Let's compare it to the next number, 2. If the second number is larger, it becomes the new largest number. Because 2 is not larger than 7, it doesn't become the new number, and 7 is still the largest number. We repeat this until the end of the list. Is 7 larger than the next number, 8? It's not. 8 is larger, so now it's the largest number. Finally, we compare 8 to the last number on the list, 3. 8 is larger than 3, so 8 is the largest number on the list. In this video, you learn the foundational steps of algorithm design: understanding the problem, diagramming and outlining the solution, and writing it all down in pseudocode. By mastering these steps, you can break down even the most complex problems into manageable solutions. Imagine an algorithm as the blueprint for constructing a building. Just as a blueprint guides the construction process, an algorithm outlines the steps to solve a problem using code. In programming, these blueprints are crucial for turning logical plans into functional code. In this video, we will explore how to translate a designed algorithm into C# code. Translating an algorithm into C# means taking a step-by-step process, the algorithm, and writing it as code the computer can understand. We'll start by creating a simple algorithm and then writing the corresponding C# code to implement it. This method helps you plan your solution first, making it easier to write error-free, efficient code. Let's begin by writing our algorithm in plain language, also known as pseudocode. This way we can easily understand the steps without worrying about the code yet. For our example, let's create an algorithm for adding 3 numbers. Here's the process. Start by defining the first number, then define the second number. Next, define the third number. After that, calculate the sum of all 3 numbers. Finally, display the result of the sum. This step-by-step approach makes it easier to translate into code later. Now that we know the steps, let's translate them to C#, examining how each part of the algorithm becomes code. We'll start by declaring the 3 numbers. In C#, we use the int type to define the whole numbers. Let's name the first variable number 1 and assign it the value of 5. The second variable is named number 2 and assign the value of 10. And our third variable is named number 3 and assign the value of 15. Let's add those 3 numbers together. We'll store the result in a new variable called sum with the data type integer. Now that we've calculated the sum, we need to display it. In C#, we write console.writeLine sum. The console.writeLine function is used to output information to the screen. Let's break down how and why we use this. When we want to print something to the console, the window where our program runs, we use the console.writeLine function. Console refers to the area where the output is displayed, and writeLine means we want to print a line of text or data. The console.writeLine function takes an argument, the value we want to print, and displays it.
In our example, we want to print the value of the sum variable, so we pass sum as the argument. This is how we communicate with the user and show results. This line tells the computer to output the value stored in sum, which will be 30, to the console. When the program runs, it will print the result so we can see the output. In this video, you learned how to translate a designed algorithm into C# code. Translating an algorithm into C# involves first creating a step-by-step, the algorithm, then turning that plan into code. By understanding the logic first, we can write more reliable and effective programs.
A front-end developer must master algorithms, flowcharts, and data types. Understanding these fundamentals empowers you to create efficient, logical code and solve complex project problems. First, we described algorithms, flowcharts, and data types, highlighting their essential role in programming. Next, we examined the fundamentals of flowcharting, including how to visualize logic, construct practical flowcharts, and analyze their effectiveness. Then we explored the core data types, focusing on how to recognize, classify, and transform them. Next, we focused on the techniques for declaring and initializing variables in C#, including understanding various data types and the principles of effective variable management. Lastly, you learned to craft algorithms and translate them into C# code, honing your skills to implement these solutions effectively in your projects. Congratulations! You have completed algorithms, flowcharts, and data types. Welcome to Control Structures and Loops. This module explores key concepts and techniques for effectively using control structures and loops. You learn how to implement control structures, utilize loops for repetitive tasks, and integrate these tools to create efficient and dynamic programming solutions. We will begin by outlining control structures, including if-else and switch statements, and their significance in programming for making decisions and managing control flow. Next, we will explore advanced if-else statements and complex switch cases, focusing on their application in decision-making scenarios to enhance control flow. Then we will examine different loop constructs, including for loops, while loops, and do-while loops, to understand their uses and how to apply them for efficient repetitive tasks. Next, you will learn how to combine loops with control structures to optimize loop-based programming for repetitive tasks and enhance practical application. Finally, you will discover how to combine if-else statements and switch cases with loops to enhance control structures and streamline programming logic. By the end of this module, you'll have a solid grasp of control structures and loops, mastering their effective use in programming. You'll learn to apply and combine these techniques to craft efficient and dynamic solutions. Let's begin our exploration of control structures and loops.
I love ice cream. I do, but there's one flavor I don't like, and it's strawberry. So when picking out ice cream, one of my requirements is that it's not strawberry. As long as it's not strawberry, I will be happy to enjoy any other flavor of ice cream. Imagine writing a program to help me order ice cream. To do this, we can use an if-else statement. I can have everything else if the ice cream flavor is not strawberry. In this video, we will explain the purpose and syntax of if-else statements. Let's start by defining what an if-else statement is. An if-else statement is a conditional construct that allows a program to perform different actions based on whether a condition is true or false. Without if-else statements, your code would run in a straight line without any conditions to guide it. You can think of an if-else statement as a fork in the road. It allows your code to continue on one route or another depending on whether a condition is met. If a condition is met, you go left. Otherwise, you go right. Let's illustrate how if-else statements work with an example using pseudocode. An example of using an if-else statement is to control access for users below a certain age. Let's use 18 years old.
We start by declaring a variable named age and setting the data type to integer. Using pseudocode, the if-else statement would work by first asking the user to input their age. If the age is greater than or equal to 18, the program will print access granted. Otherwise, or else, the user is not allowed to access the website because their age is less than 18, so the program will print access denied. Let's now work on the same example, but this time using C#. We'll go through it step by step. Let's first declare the age variable as int age. The age variable holds the user's input, which our if-else statement will check. You need to get the user's age from the console. The console is an interface where you can input commands and read outputs. To prompt the user to enter their age, we use console.writeLine and put the text of the prompt to the user in parentheses. Our prompt will read, enter your age with a colon. The code prompts the user to enter their age and stores it in the age variable. Next, we assign the user's input to the age variable. Since inputs from the console are always in string format, we must convert the input to an integer to match the age variable's type. We can achieve this by using int.parse, which converts the string input to an integer. To do this, we write the following line of code. The variable age is equal to int parse, and in parentheses, we have the console.readLine, which is the input from the user in response to our prompt asking for their age. The if keyword begins with the statement followed by a condition in parentheses. This condition checks if age is greater than or equal to 18. If the condition is true, the code inside the curly braces runs, printing access granted to the console. The else keyword follows the closing brace of the if block. It indicates an alternative code block to execute if the condition is false. If the condition is false, the code inside the else block is executed, printing access denied to the console. In this video, you learn the purpose and syntax of if-else statements in C#. If-else statements allow developers to make decisions and control the flow of their programs based on variable conditions and user inputs. Mastering if-else statements is a key part of your journey to becoming a developer. When you write code, you often need to tell the computer what to do based on different conditions. Instead of using a lot of if and else statements, you can use a switch statement. It's a way to choose what part of your code to run based on the value of something. In this video, we will describe the purpose and syntax of switch statements. Let's start by defining what a switch statement is. A switch statement allows a program to evaluate a variable and execute different actions based on its value or case. The primary purpose of using switch statements is for developers to be able to work with multiple possible variable values, making the code more readable and organized than using multiple if-else statements. Now that you've been introduced to what a switch statement is and its purpose, let's explore its structure and how it works with an example, starting with one in pseudocode. Imagine a vending machine that checks which button was pressed and performs the corresponding action. If you press the button labeled water, the vending machine dispenses water. When you press the soda button, the machine dispenses soda, and when you press the coffee button, it dispenses coffee. If you press any other button not listed as a default, it displays an error message. The values of water, soda, and coffee are called cases in the switch statement. The use of default is also a kind of switch state case. In pseudocode, this example used the following structure. Using a variable with the name button and a data type string, create a switch statement with the variable button. Then a case and corresponding action for each selection. The first case will be called water and its action is to print dispensing water. The next case will be called soda and its action dispensing soda. The third case will be called coffee and if selected, the message dispensing coffee will be provided. And then there's the default case, which has an action of providing the message invalid option because a button has been pushed on the vending machine that doesn't have a case to match it. Now let's try the same switch example, but this time using C# and breaking down the syntax piece by piece. The variable named button represents the button in the vending machine, which we will check with our switch state. To define the variable, write string button, and a semicolon. The switch keyword begins the statement followed by the variable to be evaluated in parentheses. Opening and closing braces are then added. The switch statement's cases will be included within those braces. Each case keyword represents a possible value of the variable. If the variable matches the case value, the code block following the case is executed. When the button selected is water, a message is displayed or printed to the console stating that the vending machine is dispensing water. It's important to remember that the console is an interface for inputting commands and viewing outputs. The break keyword ends the current case. Without it, the program will continue to execute the next case regardless of its value. Now include all the additional cases for the button pressed in the vending machine. Soda dispenses a soda, and coffee dispenses coffee, adding a break keyword at the end of each case. Finally, don't forget to include the default case to manage any buttons with values that do not match other cases in the switch statement. This case begins with the default keyword and includes a code block to execute if none of the case's values match the variable. Be sure to include the break keyword as well. In this video, you learned about the purpose and syntax of switch statements. Switch statements are powerful tools for managing multiple possible values of a variable. Imagine you're planning your weekend activities. You decide based on the weather. If it's sunny, you go hiking. If it's raining, you stay and read a book. This decision-making is similar to how if-else and switch statements work in programming. In this video, we will apply if-else statements and switch statements to solve problems. In everyday life, we often make decisions based on conditions, similar to if-else statements in programming. Let's explore how this concept applies in everyday situations where if-else logic can be used. Example 1, choose an outfit based on the weather. If it's cold, wear a jacket, otherwise, wear a t-shirt. Example 2, decide on a meal based on dietary preference. If you're a vegetarian, choose a veggie burger, otherwise, choose a chicken sandwich. These scenarios mimic how we use if-else statements to decide between two options based on a condition. Now that we've reviewed some examples, it's your turn to apply these concepts to a practice problem. For practice problem 1, the scenario is that you're creating a program for Codemaster Institute that checks a student's grade and prints a message. The task for this problem is to write an if-else statement that prints passed if the grade is 50 or above, and failed if it's below 50. The first step is to create a variable we can check with our if-else statement. In this case, we will call the variable grade, which is an integer type. Second, we need to get the user's grade input from the console. This code prompts the user to enter a student's grade and then converts the input from a string to an integer. Now we will check the condition to determine if the student passed based on the grade. Recall that a student passes if the grade is 50 or above. We will add the if keyword and the condition to do this. Inside the condition, we will add the code to print the message indicating that the student passed. Finally, we will include the else clause and the code to indicate that the student failed. Now that we've explored how if-else statements help to make decisions between two options, let's explore how switch statements can provide a more efficient way to work with multiple conditions. Switch statements are like if-else statements but manage multiple conditions more efficiently. Here's an example. Determine a reward based on a loyalty program level. If it's bronze, 5% discount. If it's silver, 10% discount. And if it's gold, 15% discount. The default is no discount. This scenario demonstrates how switch statements can simplify complex decision-making processes by categorizing multiple conditions. Let's work through another practice problem, this time using a switch statement. For practice problem 2, you're developing a system for Codemaster Institute that assigns a grade based on a student's score. Your task is to write a switch statement that assigns A for scores 90 through 100, B for 80 through 89, C for 70 through 79, D for 60 through 69, and F for below 60. First, we will create the variable that we'll check using the switch statement. For this problem, we'll call the variable score, and it's an integer type. Second, we need to get the user score input from the console. This code prompts the user to enter a student's grade and then converts the input from a string to an integer. To assign a grade level, we'll use a switch statement to evaluate the result of dividing the user's grade by 10. Since the grade is an integer, this division will only consider the whole number part, making it easy to determine the grade level. As we assign the A grade for scores between 90 and 100, we need to create a case for when the division result is between 9 and 10. Case 10 and case 9 will print the A grade. Don't forget to include the break keyword to avoid the system executing the next cases. Next, we will add the cases for B, C, and D grades, which correspond to the division results of 8, 7, and 6, respectively. Add the code to print the grade for each case and include the break keyword. Finally, any value below 60 will result in an F grade. We'll use the default case to manage this, similar to how the else statement works in an if-else structure. We'll ensure that if none of the specified cases match, the default action will be taken. In this video, you learned how to apply if-else statements and switch statements to solve problems. These conditional statements are important for making decisions in programming, just like in real-life scenarios. By practicing these concepts, you can enhance your problem-solving skills and write more efficient code. In this step, we will explore the basics of if-else statements. These are fundamental control structures that allow programs to make decisions based on conditions. To start, let's understand what if-else statements are. They allow a program to perform different actions based on whether a condition is true or false. Imagine you want to build a simple program that checks if a person is eligible to vote based on their age. To do this, let's assume that the voting age is 18. If someone is 18 or older, they can vote. If they are under 18, they cannot vote. First, we need to declare a variable that will store the user's age. In programming, a variable is like a container where you can store information that you want to use later. Since we are working with whole numbers, ages, we will declare a variable of the type int, which stands for integer. The int type is used to store whole numbers, and we'll name this variable age. Next, we'll ask the user to enter their age. To do this, we'll use console.writeLine, which displays a message on the screen. This message will prompt the user to input their age. After displaying the prompt, we need to capture the user's input. The console.readLine function is used to read the input from the user as a string. However, since we need to work with an integer, we must convert the string into an integer using int.parse, and then we store the result in our age variable. Now that we have the user's age stored in the age variable, we can use an if-else statement to check whether the user is eligible to vote. If the user's age is 18 or older, the program will print, "You're eligible to vote." Otherwise, it will print, "You're not eligible to vote." Next, we will learn about switch statements, which provide a way to handle multiple conditions more efficiently than multiple if-else statements. Switch statements are similar to if-else statements, but are more efficient when you have many possible conditions. Let's use a switch statement to create a simple vending machine program. We'll begin by creating a new method called vending machine within the same project. A method is a block of code designed to perform a particular task. In this case, the vending machine method will simulate a vending machine where users can select a beverage. Inside the vending machine method, we'll declare a string variable called choice. This variable will hold a beverage selected by the user. The string type is used to store text such as words or sentences. Next, we need to prompt the user to select a beverage. We'll use console.writeLine to display a message that asks the user to choose between water, soda, or coffee. We'll then capture the user's input using console.readLine and store it in the choice variable. Now that we have the user's choice stored in the choice variable, we can use a switch statement to handle different possible selections. The switch statement will check the value of choice and execute the corresponding case block based on the user's input. If the user selects water, the program will print dispensing water. Similarly, it will print dispensing soda for soda and dispensing coffee for coffee. We will also include a default case to handle any invalid inputs
providing a message prompting the user to select a valid option. This step involves applying if-else statements to a real-world scenario. Imagine you are developing a program for a school to check if students pass or fail based on their grades. You will use if-else statements to implement this logic. We'll start by creating a new method called checkGrade. This method will contain the logic for checking if a student has passed or failed based on their grade. Inside the checkGrade method, declare an integer variable named grade to store the student's grade. The int type is used because grades are whole numbers. Next, prompt the user to enter the student's grade using console.writeLine. Capture the input using console.readLine and convert it to an integer using int.parse. This value will be stored in the grade variable. Now use an if-else statement to determine if the student has passed or failed. If the grade is 50 or above, the program will print passed. If the grade is below 50, it will print failed. Now let's implement a switch statement for a more complex decision-making scenario. Switch statements can simplify decision-making processes when dealing with multiple conditions. We will use a switch statement to assign letter grades based on numerical scores. We'll begin by creating a new method called assignLetterGrade within the same project. This method will contain a logic for assigning a letter grade based on a student's numerical score. Inside the assignLetterGrade method, declare an integer variable named score to store the student's score. The int type is suitable because scores are whole numbers. Next, prompt the user to enter the student's score using console.writeLine. Capture the input using console.readLine and convert it to an integer using int.parse. The result will be stored in the score variable. Now we'll use a switch statement to determine the student's letter grade. By using integer division, score divided by 10, we can group scores into ranges like 90 to 100, 80 to 89, etc., and assign the corresponding letter grades, A, B, C, D, F. Congratulations, you have successfully completed the lab on using if-else statements and switch cases. You learned how to make decisions in your code and handle multiple conditions efficiently. These skills are essential for building interactive and dynamic applications. As a developer, you will encounter challenges that require the code to make multiple levels of decisions. For example, if one condition is met, instead of ending, it leads to another set of conditions, and maybe even another set after that. In programming, we can use advanced if-else statements to manage these kinds of scenarios. In this video, we will learn how to implement advanced if-else statements in programs. Before getting started, let's review the concept, the if-else statement. If-else statements allow us to control the flow of a program by executing different blocks of code based on whether a condition is true or false. Complex problems often demand more than a straightforward true or false decision. This is where advanced uses of if-else statements like nested if-else and chained if-else statements become needed, enabling us to manage complex decision-making processes with greater precision and clarity. These structures allow the execution of different code blocks based on various conditions. Nested if-else statements allow you to check multiple conditions by placing if-else statements inside other if-else statements. Nested if-else statements are helpful when you have dependent conditions, where the evaluation of one condition depends on the result of another. Here's how nested if-else statements work. Start with a primary if-else condition. Inside the first condition, add an if-else statement to check an additional condition. You can add multiple layers of if-else statements if you need it. This allows for more complex decision-making by checking additional conditions within each branch. Now that we've introduced how nested if-else statements work, let's use this understanding to solve a real-world scenario. An example of using a nested if-else statement could be a store that wants to provide different discounts based on the total purchase amount and customer membership status. The first thing we do is check if the variable total amount is greater than 100. This is the primary condition that determines if any discount will be applied. If the total amount is less than 100, no discount is applied, regardless of the membership status. So the program goes to the code apply no discount with open and closed parentheses because the if statement was not met, and therefore no discount is to be applied.
When the primary condition is met, it will check if the customer is a member. This is the nested condition within the primary condition. Here we include the secondary condition to validate the membership status using a custom program function called isMember. If the customer is a member, the program calls the code applyMemberDiscount, giving the customer a special discount. If the customer is not a member, the program calls the method applyRegularDiscount, giving a standard discount. This ensures that members receive the best discount, while non-members still benefit if they spend more than a certain amount. While nested if-else statements are great for working with dependent conditions, sometimes you have situations where the conditions are independent and mutually exclusive. This is where chained if-else statements are used. Let's explore how they work and how they're useful. Chained if-else statements allow you to check various conditions in a sequence without nesting them. This keeps the code cleaner, more readable, and easier to follow. Chained if-else statements are ideal when you have several mutually exclusive conditions where each condition is independent of the others. Here's how chained if-else statements work. Start with a primary if condition. Then use else if for additional conditions. Add as many else if statements as needed. Finish with a final else to manage all other cases. Let's demonstrate how to use a chained if-else statement by using an example of determining shipping costs based on the customer's location. We first verify if the location is local. If this condition is true, we apply local shipping by calling the applyLocalShipping method. When the first condition is not met, the program moves to the next condition and uses an else if to check if the location is domestic. If it is, we should apply domestic shipping by calling the code applyDomesticShipping with open and close parentheses. If the location is neither local nor domestic, we execute the else block, which applies international shipping by calling the code applyInternationalShipping with open and close parentheses. As you start using nested and chained if-else statements, you must be mindful of how your code is structured. Without proper planning, these structures can lead to what developers often call spaghetti code, a tangled and confusing code base that's hard to maintain. Let's list some ways we can avoid this from happening. To avoid spaghetti code, follow these tips. Keep it simple. Break down complex conditions into simpler, smaller conditions. Use functions to encapsulate conditional logic within functions to make the main code easier to read. And finally, use comments to explain the purpose of each condition. In this video, you learned how to implement advanced if-else statements in programming. You examined how nested if-else statements can manage complex conditions and how chained if-else statements can help maintain clean, readable code. By applying best practices, you can prevent the dreaded spaghetti code and ensure your programs remain readable and easy to follow. In programming, there will be problems that are complex and require multiple levels of decisions. And sometimes to solve these kinds of problems programmatically, simple switch statements will not be enough. In this video, we will implement complex switch statements in programs. Before we explore some examples, let's quickly recap what switch statements are and why they're useful. Switch statements allow a program to evaluate a variable and execute different actions based on its value. For example, a program may use a switch statement to apply a different shipping method based on order size. To determine which order size matches which shipping method, switch statements use cases. A case is a specific condition in a switch statement that the program checks against the value of a variable or expression to determine what to do next. Each case represents a potential value that the variable might match with. When a match is found, the code block associated with that case is executed. Now we're ready to explore more complex uses of switch statements, like when multiple cases share the same action, and when a default value is used to manage a value that does not match any of the cases. In a simple switch statement, each case would have a corresponding action. For example, a switch statement with a case for each day of the week would provide a unique food recommendation depending on the day. But what if you wanted the food recommendation to be the same for Mondays and Wednesdays? Switch statements enable this by allowing multiple cases to share the same action. Let's explore this with an example in pseudocode.
First, let's review how this would be done using a simple switch statement. The action would be provided for each case like this. The first case would be Monday, and the action would be to print the message, eat cereal. And it would be the same action for Wednesday. The case would be Wednesday, and the action would be to print the message, eat cereal. Note that the action of printing the message, eat cereal, had to be provided 2 times, even though it's the same action for both days. Now, using a more complex switch statement, we can share multiple cases with Monday and Wednesday sharing the same action. We can rewrite the switch statement listing the case for Monday and then the case for Wednesday. Then just one action to print a message to eat cereal will apply to both cases. Another use of complex switch statements is pattern matching. Pattern matching allows you to use switch statements to handle different data types by comparing inputs against a predefined pattern. You can use this type of switch statement to determine if the input text contains a certain string of characters and then perform an action. In this situation, the input doesn't have to be an exact value, but it must contain a value that matches a pattern. For example, it could check if the input contains the word jazz and match the phrases like soft jazz or jazz nouveau. In that case, it would print the message, jazz music. Similarly, if the input contains the word rock, it would print the message, rock music. The final type of complex switch statement we're going to explore makes use of the default case. The default case is used in a switch statement to execute when none of the specified cases match the expression. Using a default case helps prevent the program from crashing or behaving unexpectedly. As an example, let's add a default case to our pattern matching example from earlier. We already have 2 cases, one for jazz and another for rock. But what if we needed to match a value that doesn't contain the string jazz or rock? We can manage these other values in the default case and have an action like printing a message, other type of music. Note that we use the default case last in this example, but the default case can occur anywhere within the switch statement and doesn't have to be at the end. In this video, you learned about complex switch statements. You explored how to manage multiple cases, apply pattern matching, and use the default case to manage unmatched values and ensure your code works smoothly. As a developer, you will be creating programs that use control structures like if-else statements and switch statements to solve real everyday problems. In this video, we will learn how to solve decision-making scenarios using control structures. Control structures like if-else statements and switch cases are statements that determine the flow of code execution based on specific conditions. Now let's explore how they work. We'll examine a few real-world scenarios in which these conditional statements help us make critical decisions in our code. Consider that a tech startup wants to manage inventory. The program needs to decide whether to reorder a product based on its current stock level. Next, the startup needs to process orders. The shipping method must be determined by the customer's location. Finally, we'll apply discount rates based on the total purchase amount and the customer membership status. We will use if-else statements and switch statements to solve these scenarios. In the first scenario, we need to decide whether to reorder a product based on its stock level. Here's how we can implement this using an if-else statement. First, we must evaluate whether the stock level is lower than the reorder threshold. If it is, we must reorder the product. Otherwise, we maintain the current stock using an else statement. After working with inventory management, the next challenge is processing orders. Let's figure out how control structures can help us determine the best shipping method based on a customer's location. Let's work through how we can implement this using a switch statement using C#. We start by creating the switch statement, and for the expression we use location. Next, let's evaluate the possible values for the customer's location and create the behavior for each case. If the customer's location is local, we must apply the local shipping method. If the location is domestic, apply the domestic shipping method. If the location is international, apply the international shipping method. We can also include a default case. This will provide an action to manage if the location does not match the specified locations. In this example, the program will apply the standard shipping method as the default case.
In this video, you learned how to solve decision-making scenarios using control structures. We explored using if-else statements and switch statements to evaluate variable values and program states. Control structures are essential for managing complex decision-making processes and writing clear, efficient code. Imagine you're the manager of a factory where thousands of items need to be checked for quality before shipping. Doing this manually for each item would take forever. But what if you had a machine that could inspect every item in a second with just a single command? That's what a for loop does in your code. It automates repetitive tasks, saving you time and effort while ensuring every step is completed flawlessly. In this video, we will explain the purpose and syntax of for loops. Let's start with a definition of a for loop. A for loop is a control flow statement that allows code to be executed repeatedly based on a condition. In many programming languages, for loops follow a basic pattern. The loop consists of a body, which is the code that you want to run repeatedly. It also includes a number or collection of items that determines how many times the body code will be repeated. Let's examine how to construct a for loop that includes these elements. Start by adding the keyword for. Then initialize a variable, often a lowercase letter I, to keep track of how many times the body code has been run. Next, set a condition, typically a number that determines when the loop should end. Then increment the variable I each time the body code runs. Lastly, add code to be executed during each loop. Let's now break down the structure and syntax of a for loop using C#. First, add the for keyword followed by parentheses. Next, initialize the variable I, setting it equal to 0 inside the parentheses. Then set a condition that needs to be met to initiate each loop. This also goes in the parentheses, and each item is separated by a semicolon. In this example, the condition is that I is less than 5. This means that the loop will run as long as I is less than 5. Next, we'll tell the loop to increment the variable I by 1 each time the body code runs. In C# we use the syntax I++, which adds 1 to I after each iteration. The value of I will be increased by 1 with every loop until it reaches 4, the final integer that's less than 5. This is how the loop knows when to end. Finally, add code to the body of the for loop to be executed during each loop. In this example, we use the code console.writeLine. This will print the value of I every time the loop is run. So the result will be 0, 1, 2, 3, and 4. In the next example, we'll work with a type of list called an array, which is commonly used in programming. An array is an ordered list of values used to represent a list of items. Let's explore the basic structure of an array using C#. Suppose we have an array of numbers and we want to calculate the sum. A loop will iterate or loop through the array, adding each number to the sum. To illustrate this, imagine we have an array named numbers with the values 1, 2, 3, 4, and 5. In C#, to define the array, we start with its data type. In this example, it's an integer. So we use the int keyword and then empty and close brackets. Then add the array's name, numbers, followed by an equal sign. After the equal sign, we add the list of items to be stored in the array enclosed in curly braces, and we finish with a semicolon. Next, we need to declare a variable to store the sum as the loop iterates through the array's values. For this example, we will name the variable sum and initialize it to 0 before starting the for loop. Otherwise, the program will restart the sum in each iteration. Now let's set up the for loop using the structure from earlier. In this example, we initialize the iterator or variable I to 0. Next, we specify the condition to process an iteration. Next, we specify the condition to process an iteration. In this example, the condition is that the iterator is less than the number of elements in the array. We'll use numbers.length to get the number of items in the array. Finally, we'll increment I by 1 after each iteration with I++. Now we specify the action for each loop iteration by adding the code to be executed during the loop. In our example, we will add the value of the position denoted by the value of the iterator I to the accumulated sum.
Starting with the variable sum equals to 0, each loop through the body code will add a value from the array, so the first loop will be the result of 0 plus 1, or 1. The second loop will use the new value of sum, in this case 1, and add it to the next value in the array. In iterating through the loop, we will have 1 plus 2 with the result being 3. It will repeat this for all values in the array and the final result will be 15. In this video, you learned how to explain the purpose and syntax of for loops. This includes using examples to illustrate the for loop structure and how it can be used with arrays. For loops can be powerful tools to automate repetitive tasks and efficiently process large amounts of data.
For loops work when needing to write code that repeats tasks and you already know how many repeats or loops are needed. But what if you don't know how many are needed? What if you need tasks to be repeated while a condition remains true? This is the work of while loops. In this video, we will describe the purpose and syntax of while loops. A while loop is a control flow statement that allows code to be executed repeatedly based on a condition. It checks the condition before each iteration and runs the loop as long as the condition is true. The purpose of while loops in programming is to make it possible to manage repeated actions when you don't know how many loops will be needed. They work by continuously monitoring conditions as opposed to a defined number of repetitions. Let's explore while loops further by comparing them to for loops. For example, imagine you're practicing your basketball shot and it's nearing the end of your practice. To end your practice, you decide to take 10 more shots and then you're done practicing. This is like a for loop. Each shot is a loop, and you perform the loop 10 times or take 10 shots and then you're done. This time, instead of having to take 10 shots, you decide practice is over once you make a single shot. So you can take one shot, and if you make that shot, practice is over, or you might have to take 20 shots before you make one, and then practice can be over. This is like a while loop. You don't know how many shots or loops will be needed to finish your practice. Now that you understand what a while loop is and how it differs from a for loop, let's examine its structure and syntax in a couple of examples using C#. The syntax and structure of a while loop in C# consists of the while keyword followed by a condition and the code block to be executed. The loop executes the code block as long as the evaluated condition is true. Let's break it down into code using a simple example of a while loop. In this example, we declare a variable named counter with an integer data type and set it equal to 0. Then, using the keyword while, we build our while loop by setting the condition of counter to less than 10. If this condition is met, the code to be performed is console.writeLine counter to print the counter and then increment it by 1 using the instruction counter++. This means that the variable counter starts at 0, and then as long as it's less than 10, it will print its current value to the console, increment by 1, and check the condition again. This process continues printing each number from 0 to 9 until the loop ends after 9 is printed, 9 being the last integer that is less than 10. Another typical example of using while loops is reading user input until the user prompts a specific command. We start by defining the string variable input and initializing it with an empty string with a set of 2 quotes. This sets up the loop's initial condition. Then we include the while loop, which runs as long as the condition input is different from exit using the exclamation equals operator. This means the loop will continue until the user enters the word exit. Inside the loop, the line console.writeLine, enter a command, prompts the user to type a command, and the line console.readLine captures whatever the user types and stores it in the input variable. After capturing the input, the loop checks the condition again. If the input is not equal to exit, the loop repeats, prompting the user for another command. If the user types exit, the condition becomes false and the loop stops. In this video, you learned how to explain the purpose and syntax of while loops, explore their role in iterative processes, and highlighted how they differ from for loops. Through coding examples, we demonstrated how while loops efficiently manage tasks that require repeated checks until a specific condition is met. In programming, there are times where you must ensure that a block of code executes at least once, regardless of any initial conditions. The do while can be used to accomplish this, whether managing user input, initializing important processes, or ensuring critical operations execute. In this video, we will describe the purpose and syntax of do while loops. Let's start with a definition. A do while loop is a control flow statement for iteration that allows code to be executed at least once before checking a condition. Think of it as attempting to open a door at least once before checking if it's unlocked. Unlike while loops, do while loops check the condition after executing the code block, guaranteeing at least one execution of the loop body. Use a while loop to execute a code block only if the condition is true from the start, like when validating input before processing. Use a do while loop to execute the code block at least once before checking if the condition is true. The basic structure of a do while starts with the do keyword, followed by the code block you want to execute, and then the while condition determining whether the loop will continue. Now let's explore the do while loop further with an example using C#. In this example, we declare and initialize a variable named counter to 0. We will use the variable to control the loop's execution. We then use the keyword do and a set of open and close curly braces. Within the curly braces, we include the code to be executed, which will print the value of the variable counter to the console, and then counter ++ to increment the value of the variable by 1. Finally, we use the keyword while and the condition counter less than 10. So what this code will do is first print the starting value of the variable counter, 0, and then check the condition. While the condition is true, it will iterate. The result is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. In that example, the result is no different than if we used a while loop rather than a do while loop. But what if the initial value of the variable counter was 10? If we initialize the counter to 10, the loop would print 10 and then check the condition while counter is less than 10 and stop because the condition is not true. Therefore, the result is simply the number 10. This example illustrates how the do while loop differs from the while loop. In this video, you learned how to describe the purpose and syntax of do while loops. This included comparing the do while loop to the while loop and exploring its structure and syntax using examples in C#. Imagine you're building an application that processes user input, like recommending a food option based on user responses to a survey. You'll need to use a loop to check each response and a control structure like an if-else or switch statement to process and decide what happens next. In this video, we will use loops in conjunction with control structures to solve problems. Let's start with an example that uses a loop with an if-else statement. In this example, we want to check an array of numbers and print whether each number is even or odd. We're going to build the code using this example piece by piece using C#. First, let's define an array named numbers to hold the list of integers we want to evaluate. Our array contains the numbers 1, 2, 3, 4, and 5. This is our starting point before we introduce the loop. We're going to use a for loop that iterates from I equals 0, the first index of the array, to I is less than numbers.length, the last index of the array. The condition I is less than numbers.length ensures that the loop runs as long as I is less than the total number of elements in the array. Inside the loop's body, we use an if-else statement to check whether the current number is even or odd. We do this with the help of the modulo operator. Let's explore the use of this operator in more detail. The modulo operator calculates the remainder of a division. In this example, it divides numbers I by 2 and returns the remainder. If the remainder is equal to 0, the value from the array at the index I is even. If the remainder is not 0, the value is odd. For example, let's use I equals 3, the fourth index in the numbers array. Remember that we start counting indices of an array at 0. So if it's index 3, that's the fourth item in the array. At index 3, we have the number 4. Using the modular operator, we can find the remainder after dividing 2 into 4. Since 4 divided by 2 equals 2 with no remainder, it's an even number. Now let's get back to our code example. When the if statement condition is true, there's no remainder, so we use a console.writeLine to display the value checked, followed by is even. If the condition is false, that means there's a remainder and the value is odd. We use an else statement for this and display the value to the console with is odd after it. Now that we've explored how loops work with if-else statements, let's move on to how they can be combined with switch statements to evaluate data. Imagine creating a program that tells you how to prepare for the day based on expected weather. When it's expected to be cold, it will display a message like dress warm today, and if it's going to be rainy, then it will remind you to bring your umbrella. We begin by defining the array that holds the different weather forecasts. Our array is named weather forecasts and it contains 3 strings: sunny and warm, rainy with thunderstorms, and cloudy and cold. Next, we open a for loop to iterate over each element in the array. Then we add a switch statement to the body of the for loop to classify each element in the array. The switch statement will have 3 cases, one for each type of weather forecast. When a case is matched, a message to the console will be displayed. For example, the first case has a weather forecast that's sunny and warm. When this one is matched, the message that's displayed will read, "Today will be sunny and warm, so bring your sunglasses." The second case has a weather forecast of rainy with thunderstorms, and if it's matched, it will display the message, "Today will be rainy with thunderstorms, so bring your umbrella." And the third case will match with the weather forecast of cloudy and cold. If this is the forecast, the message will read, "Today will be cloudy and cold, so wear warm clothes." In this video, you learned how to use loops in conjunction with control structures to solve problems. Mastering how to combine loops with control structures is going to be a fundamental part of your work as a developer. Imagine you're working on a project where you need to process hundreds or even thousands of data entries, like updating records in a database or analyzing daily user activity. Doing this manually would take hours, if not days. This is where loops in programming become extremely useful. By using loops, you can automate these repetitive tasks, saving time and reducing the likelihood of errors. In this video, we will implement loops and solve practical repetitive tasks. Before moving on, let's recap the concept of loops in programming. A loop is a construct that repeats a code block multiple times. There are 3 main types of loop structures, each suited to different scenarios. Let's recap each one, providing basic examples. You can use the for loop when you know how many times the loop should execute, or if you're working with a collection or sequence. One common task is iterating through a list of values like an array to process each element. For example, we want to print all elements of an array. Let's work through this example step by step. The first step is to define the array. We define the array named numbers that contain the values we want to evaluate. In this example, those values are integers. Then in the second step, we use a for loop to iterate over each element in the array. To do this, we create our for loop with the keyword for. We then declare the iterator an integer value named I and set it equal to a starting value of 0. The condition will be I is less than the length of the array named numbers, and we increment I by 1 with I++. Finally, within the for loop, we will have the value of I printed for each loop, where I refers to the index or position in the array starting from 0 for the first element. For example, if I is 3, the system prints the number located at the 4th position of the array. In our example, this means that if I is 3, then the integer in the array at that position is 4. This can be tricky at first, but keep in mind that I started at 0, so the positions in the array begin at position 0. Let's do one more just to ensure we understand how this works. Let's figure out the array value at position 0. The array results are 1, 2, 3, 4, and 5. I starts with a value of 0, so it's the first position in the array. In our example, it's the integer 1. Iterating through an array is a very common application of the for loop. Now let's explore how we can use the while loop. You can use the while loop to iterate until a certain condition is met, and you don't necessarily know the number of iterations in advance. An example to explain this loop is generating a sequence of numbers, like printing numbers from 1 to 10. Let's work through this example step by step. First, let's define and initialize the variable to validate the condition of the while loop. This sets the starting point of our sequence using an integer variable named counter and setting it equal to 1. Second, we use a while loop and define the loop condition as the variable counter is less than or equal to 10. In the loop body, we include 2 instructions to print the counter's value to the console and increment it by 1. So far, we have used the for loop to iterate through an array and the while loop to execute while a condition is true. The next loop works almost exactly like the while loop, but with one key difference. It will execute at least once before checking the condition. This loop is called the do while loop. It executes and then checks the condition to determine if it needs to execute again. Let's use the example we used to explain the while loop to illustrate the do while loop. Let's work through this example step by step. First, let's define and initialize the variable to validate the condition of the do while loop. This uses an integer variable named counter to set the starting point of our sequence. In this example, it's set to the value 1. In step 2, we include the do while loop structure where we will add the code block. We simply use the keyword do. In the loop body, we include 2 instructions to print the counter's value to the console and increment it by 1. Finally, we must specify the condition to continue iterating the do while loop. As in the previous example, the condition is that the counter must be less than or equal to 10. Here we add the while clause expressing the condition. Now that we've covered the different types of loops and how they work, it's time to explore these concepts at work. Let's move on to a practical example where we will apply the loop to solve a real-world problem. Groove Eco needs to update the price of its eco-friendly products by increasing the price 5% due to the changes in material costs. Given its rapid expansion and growing number of products, manually updating the catalog would be time-consuming and prone to errors. The Groove Eco IT team can develop a program to iterate through an array of product prices and apply the appropriate price increases. This example effectively lets us practice the loop applications. Let's break it into code. First, we define the array of product prices. This array is named prices, and because prices require decimals, we will use the data type of double. Now we include the loop through each product price. For this example, we use a for loop. In the loop body, we increase the price of each product by 5% and then store them back in the array. Finally, during each loop iteration, we print the new price to the console. In this video, we have implemented loops to solve practical repetitive tasks effectively. By understanding different loop structures, for, while, and do while, you learned how to select the appropriate loop for various scenarios and automate repetitive processes efficiently. This knowledge will help you manage tasks such as iterating through data, and it will also significantly enhance your ability to manage complex data-driven projects with confidence and precision. As a developer, you might create programs and later discover that their performance can be improved by replacing existing code with newer versions that accomplish the same tasks but execute faster and more efficiently than the original code. One way to do this is by optimizing your use of loops. In this video, we will optimize loop-based programs for efficiency. Let's start with a definition of what loop optimization is. Loop optimization refers to techniques that make loops operate faster and use fewer resources. Inefficient loops can slow down your program, especially when dealing with large data sets or complex computations. By using some optimization techniques focused on minimizing iterations, you can make your loops perform more efficiently. Let's explore some common loop optimization techniques that can help our programs execute more efficiently. One technique for optimizing loops is to terminate loops early to reduce the number of iterations. When a condition is met, you can break out of the loop early with a break statement. Let's define what a break statement is. A break statement is a control flow statement used to terminate the execution of a loop or switch statement. This prevents the loop from continuing to iterate unnecessarily, thus saving time and resources. Another loop optimization technique is to avoid nested loops. Nested loops can be inefficient, especially if both loops iterate many times without needing to. Avoiding nested loops or minimizing their usage can improve performance. When possible, it's a good practice to break down loops into smaller, independent loops rather than nesting them. In this video, you learned about some techniques to optimize loops for greater efficiency. By applying techniques like early termination and avoiding nested loops, you can enhance the performance of your code. These are just a couple of techniques for optimizing loops. You will learn and use more as you continue to grow as a developer. In this first step, we will explore how a for loop can help automate tasks that need to iterate over a collection of items such as an array. An array is a collection of items like numbers that are stored together in a single variable. Arrays are useful when you need to store multiple values of the same type. In this case, we are storing 5 numbers in an array named numbers. In C#, array indexing starts at 0, so the first element of the array is at position 0, not 1. For example, in the array numbers equals 1, 2, 3, 4, 5, numbers index item 0 is 1, and numbers index item 4 is 5. We use numbers.length to get the number of items in the array. In this case, it's 5. The loop will continue to run as long as I is less than the length of the array, or I is less than the numbers.length. This ensures we don't access an index that doesn't exist, which would cause an error. A for loop is ideal when you know exactly how many times you need to run a piece of code. It has 3 parts: the starting point, or int I equals 0, the condition, or int is less than the numbers.length, which must be true for the loop to keep running, and how the loop updates, I++, which increases the value of I by 1 each time the loop is run. In this step, we will learn how to use a while loop. A while loop is different from a for loop because it doesn't have a set number of repetitions. Instead, it keeps running as long as a condition is true. We will use a while loop to generate a sequence of numbers from 1 to 10. The loop will keep running while the value of counter is less than or equal to 10. Each time the loop runs, we will increase the value of counter by 1. Unlike a for loop, a while loop doesn't automatically know how many times it should run. The condition you set controls how long it runs. In this example, the loop will run as long as counter is less than or equal to 10. As soon as counter becomes greater than 10, the condition is no longer true and the loop stops. You must remember to update counter using counter++, or the loop will run forever since the condition will never change. This is a common mistake for beginners, so always check that you're updating your counter in a while loop. Now we will combine loops with an if-else structure to add decision making within each iteration. We will check whether each number in an array is odd or even and print the result accordingly. To do this, we will use the modular operator, the %sign. This operator gives the remainder of a division. There is no remainder when dividing a number by 2. That means the number is even. If there is a remainder, the number is odd. The modular operator is used to find the remainder when one number is divided by another. When we divide a number by 2, if there's no remainder, that is, the number modulo 2 equals 0, it means the number is even. If there is a remainder, that is, the number modulo 2 does not equal 0, the number is odd.
We use this concept in programming to check if numbers meet certain conditions, like being odd or even. If you forget how the modular operator works, remember that it gives you the remainder of a division. For example, 5 divided by 2 gives 2 with a remainder of 1, so 5 is odd. In this final step, we will explore how to use loops in combination with a switch statement. A switch statement is similar to an if-else statement, but enables you to check a variable for more than one value at a time. Instead of using multiple if-else conditions, which can make your code harder to read, the switch statement lets you handle different cases in a cleaner, more organized way. For each weather condition, we will print a different message using the switch statement inside the loop. Imagine facing a challenging puzzle where you needed to sort through various options to find the perfect solution. Now add the complexity of navigating through multiple layers of choices that depends on each other. Sounds tricky, right? This is where the power of combining if-else statements with loops comes into play. It's like having a powerful tool that lets you successfully work on complex programming challenges. In this video, we will combine if-else statements with loops in coding exercises. Let's examine a few programming scenarios where combining if-else statements with loops provides an efficient solution. In our first example, we will be validating user input. Suppose we need to validate a number entered by a user in an application. We will use a loop combined with an if-else statement. The loop will prompt the user to enter a number, and the if-else will check if the number is between 1 and 10. The loop will continue to prompt for input until the condition is met. Let's break this down using an example in C#. First, we declare an integer variable called input to store the number entered by the user from the console. For this example, we're going to use a do-while loop. This loop will repeatedly execute the code block inside the curly braces until a specific condition is met. As the loop condition depends on an action taken by the user, like entering a guess, we can't check the condition in advance. This is why we use a do-while loop. Unlike other loops, a do-while loop ensures that the code inside will always run at least once, regardless of the condition. Then we use console writeLine to prompt the user to input a number between 1 and 10. We use console readLine to read the user's input, and then we use int.parse to convert the input from a string to an integer, which is stored in the input variable. We validate the input using an if-else statement. The if-else statement validates that the user entered a number between 1 and 10. If the input is not between 1 and 10, we handle this case using an else statement. The body of the else statement displays an error message using console.writeLine, prompting the user to try again. Once the user enters a number between 1 and 10, we will display a message using console.writeLine, indicating that the input is valid along with the number the user entered that's stored in the variable input. After that, we will include the break statement to exit the do-while loop, as the user has provided valid input, and the loop is no longer needed. The while statement sets a condition that determines when the loop should exit. For example, we could set a condition where input equals 5. On this condition, when the user enters 5, the loop exits. However, by using true as the condition, we're explicitly saying that the loop should continue indefinitely because true is always true. This creates an infinite loop, which will only stop when the break statement is reached after the user inputs a number between 1 and 10. Now let's explore a real-world example in C# where we will use a for loop to iterate through a list of student grades. We'll then use an if-else statement to determine whether each grade is passing or failing. First, we create an array to store the list of student grades. This will be a fixed array of integers named grades. Next, we will add a for loop to iterate over each element in our grades array. During each iteration, the current item from the array will be assigned to the variable grade. Now let's define a string variable named result. This variable will be used in our if-else statement to be either pass or fail based on the value of grade during that iteration. Next, we will use an if-else statement to validate if the student passes or fails. If the grade is greater than or equal to 65, the value of the result variable is pass. Otherwise, the grade will be below 65 and the value of the result variable will be fail. Finally, we use the code console.writeLine result to display the value of the result variable. When you run this code, the first 3 grades are greater than 65, so the code prints pass. When the loop gets to the value 64 in the array, the code prints fail, because 64 is less than 65. When the code reaches the final value in the array, 89, it prints pass. In this video, you learned how to combine if-else statements with loops using programming scenarios. Mastering these concepts will help you as you take on more complex programming challenges. As a developer, you'll be challenged to combine multiple programming tools to solve problems that include complex conditions. One example is integrating switch statements with loops. In this video, we will combine switch statements with loops in coding exercises. Let's start by exploring some complex programming condition examples where combining switch statements with loops provides an efficient solution. For example, in an e-commerce application, we might need to process multiple orders based on their status. We can use a loop to iterate through each order and a switch case to manage different statuses. Here's a code example in C#. First, we create the array named order statuses, which contains the order statuses we will process. For this example, we'll use a fixed array of a type string. Then we include a loop to iterate over the elements in the collection. In this example, we include a for loop, and each item will be assigned to the variable named status. Next, we will add the switch statement to check the value of the status variable so that we can match it against the defined cases. Then we include a case for each status in the system. If the status is pending, we print order is pending. If the status is shipped, we print order has been shipped. If the status is delivered, we print order has been delivered. If the status is canceled, we print the order has been canceled. Now, if the status doesn't match any of these specified cases, the default case is executed, printing unknown status. Don't forget to include the break keyword for each case to avoid unexpected behaviors. Now that we've optimized order processing by status by integrating a switch statement with a for loop, let's work through one more example. This time we will evaluate student grades with a for loop and a switch statement. In this example, we need to evaluate student grades and provide feedback. We can use a for loop to review each student's score and a switch case to give the appropriate feedback. Let's use C# to write our program. We start by creating an array named grades to store the list of student grades as integers. In the next phase, we will add a for loop to iterate over each element in the array. During each iteration, the current element will be assigned to the variable grade. Now we include the switch case to assign a letter grade based on the grade value. The switch statement checks the value of the grade variable and matches it against different cases, each defined with a condition using the when keyword. If the grade is 90 or higher, we print grade A, excellent. If the grade is between 80 and 89, we print grade B, good job. If the grade is between 70 and 79, we print grade C, fair. If the grade is between 60 and 69, we print grade D, needs improvement. If the grade is below 60, it does not match any of the conditions of the above cases and falls to the default case, printing grade F, fail. In this video, you learned how combining switch statements with loops can address complex programming conditions. Combining different programming tools in this way will be important for you as a developer, helping you overcome complex programming challenges. In this step, we will use a combination of loops and if-else statements to validate user input. Imagine you need to create a program that repeatedly asks the user to input a number between 1 and 10 and ensures the number is even. The loop will continue until the user enters valid input. We will use an if-else statement to check if the number is valid. In this step, we will use a do-while loop. A do-while loop is different from other loops because it runs the code inside the loop at least once before checking the condition. This means the program will ask for input at least once, even if the user enters a valid number right away. We also use the break statement to stop the loop once the input is valid. Break tells the loop to end immediately, so the program doesn't keep asking for input after we've received the correct number. In this step, we will use a for loop and an if-else structure to evaluate a list of student grades. For each grade, we will determine whether the student has passed or failed based on the grade value. We will write a program that iterates over an array of grades and uses an if-else statement inside a loop to check whether each grade is a passing grade. A for loop is useful here because we know how many grades we have, and we want to check each grade one by one. Each time the loop runs, it accesses the next grade in the array using an index, I. The index starts at 0, which means the first grade is grades 0. The loop continues until it has checked every grade in the array. Inside the loop, we use an if-else statement to check if the grade is 65 or higher, pass, or lower than 65, fail. In this statement, we will explore how to combine loops with switch statements to handle different cases. Specifically, we will write a program that processes multiple orders by their status. Each order can be pending, shipped, delivered, or canceled, and we will print a message based on the status of each order. A switch statement is better suited for cases where you need to check multiple specific values. For example, when dealing with order statuses like pending or shipped, a switch statement makes the code cleaner and easier to read. The switch statement checks the value of status and runs the code that matches the specific case, such as printing order is pending if the status is pending. This is easier to manage than writing multiple if-else conditions, especially when there are several possible statuses. In this final step, we will combine loops with a switch statement to evaluate student grades and assign letter grades. The program will use a for loop to iterate over a list of student scores and a switch statement to assign grades based on the score. In this example, we're using a switch statement with the when clause to check which range a student's score falls into. For example, if a student's score is 90 or above, they get an A. Then the when clause helps the switch statement handle ranges, like 90 and above for A, or 80 to 89 for B. This is similar to how we check conditions with if-else, but switch makes it more organized, especially when there are multiple ranges to check.
Mastering control structures and loops is essential for dynamic and responsive front-end development. These skills allow you to create interactive features and optimize performance, ensuring a seamless user experience across your applications. We began by exploring control structures such as if-else and switch statements, highlighting their role in decision-making and control flow management in programming. Next, we examined advanced if-else statements and intricate switch cases, emphasizing their use in refining decision-making processes and improving control flow. We then analyzed different loop constructs such as for loops, while loops, and do-while loops to understand their functions and how to apply them effectively for repetitive tasks. Next, we explored how to merge loops with control structures to streamline repetitive tasks and enhance your programming practices. Finally, you learned how to integrate if-else statements and switch cases with loops to refine control structures and simplify programming logic. Congratulations, you've completed control structures and loops.
Welcome to Introduction to Functions in Programming. This module covers essential techniques for leveraging functions and methods in programming. You'll learn to define and use functions, effectively call methods, and manage parameters. Integrating these concepts will enhance your ability to develop dynamic and responsive front-end applications. We will begin by introducing functions in programming and their importance in structuring and organizing code. We will also explore the basics of writing functions and how to incorporate them into your programs effectively. Next, we will explore various methods in C#, focusing on their syntax, different use cases, and how they can be applied to enhance your programming practices.
Then we will examine how to effectively call methods, including understanding their return values and exploring practical examples to apply these concepts in real programming scenarios. Next, you will discover how to use parameters and methods, focusing on passing data effectively and understanding their practical applications to enhance method functionality. To conclude, we will explore integrating functions and methods into program development, focusing on solving complex problems and creating comprehensive, effective solutions. By the end of this module, you'll have mastered the essential techniques for using functions and methods in programming, from defining and calling functions to managing parameters and integrating these concepts into your projects. Let's get started with Introduction to Functions in Programming. What if I told you there's a way to make your code more efficient, easier to manage, and quicker to update? This is the power of functions in programming. Functions help you write cleaner, more organized code, reducing your repetition and optimizing your development process. In this video, we will define what functions are and their importance in programming. Let's start with an overview of what functions are. Functions are reusable blocks of code designed to take input, process it, and return an output. Developers primarily use functions to manage repetitive tasks like processing data or checking values. For instance, a developer might create a function to perform a mathematical calculation. By passing values into the function executes the calculation and then returns the result to the code that called it. This ability to take inputs, perform operations, and return results is at the core of what makes functions so powerful. Let's take a closer look at the key benefits of using functions in programming. Developers use functions to create reusable code. A function can be used multiple times throughout the program without rewriting the code. In addition to reusability, functions also enhance modularity by helping to break down complex tasks into smaller, more manageable pieces that can be grouped into associated files and libraries. This helps make it easier to find and work with specific code. Moreover, functions improve maintainability by allowing developers to update code in one place, ensuring consistency across the entire program. If the developer needs to change the way the function manages a task, they only need to update it in one place rather than having to update multiple instances of the same code. Now that we have an understanding of why functions are so beneficial, let's explore how they are structured to provide these advantages. Every function includes a declaration, which simply defines the name of the function and specifies what it should do. Functions include parameters, which are the inputs that a function will process. Imagine you're at a grocery store and purchasing items. The cashier is like the function, and the money you give them is similar to the input parameters. The function body is where the core logic of the task is executed. This is where the function processes the input to produce the desired outcome. Once the task is completed, the function provides a return value. This return value is the final result that the function sends back to the part of the program that called it. Now that we've covered the essential components of a function, let's see how these pieces come together in a real-world example. We will use a function to calculate the total cost of items in a shopping cart for the fictional company Groove Eco. Groove Eco is launching a new retail clothing website, and one of the basic capabilities their website needs at launch is the ability to calculate the total price of items in a customer's cart. The first step is to declare the function by giving it a name and defining its purpose. For this example, we'll call this function calculateTotal. Once the function is declared, the next step is to specify an input parameter called items. This represents the products in the shopping cart. The body of the function contains the actual code that performs the task. The function calculateTotal on Groove Eco's site will loop through the items that were passed into the function and total their prices. Finally, the function returns a result using the return statement. The calculateTotal function returns the total price of all items in the cart, so Groove Eco can then display the total bill to the customer. This function enables Groove Eco's development team to ensure that calculations are accurate every time. They can also update the calculation logic if they need to, or reuse the function across different parts of the site, such as in the cart view, checkout page, or order summary. This is just one example of how powerful functions can be in programming. In this video, you'll learn that functions are blocks of code designed to perform specific tasks. They enable developers to pass in data, execute tasks, and return results. Functions are crucial for creating reusable, modular, maintainable code, which is essential in any programming project. Imagine building a complex application without the ability to reuse any of your code. Every time you needed to perform a task, you'd have to rewrite it from scratch, leading to a codebase that's not only overloaded, but also likely to have errors. This is where functions come into play. In this video, we will learn how to write functions to create reusable code blocks. Let's start with an overview of what functions are. Functions are reusable blocks of code that perform specific tasks. They allow developers to pass in data, execute tasks, and return results. Let's explore the structure of writing functions. When you're writing functions, there's a specific structure to follow. You start by declaring a function with a name that describes its purpose. For example, if you're writing a function to calculate the area of a rectangle using pseudocode, you might use the calculate area as the name of your function. Another part of the function structure is taking inputs, known as parameters, to work with different data. Using the same calculate area function example, the parameters could be the length and the width of the rectangle. The function body contains the actual code that performs the task. For the function body, we will want to calculate the area of the rectangle by multiplying the length and the width. When a function is called, it executes its code and typically produces a result. The return type indicates what value the function will return. In our example of calculating the area of a rectangle, the function return type will depend on the data type used by the function. Because the function is calculating the area of a rectangle, the return type will be a number, so it would either be a double or an integer. In this video, you learn the structure and syntax of writing functions using pseudocode, including the function's declaration, parameters, body, and return type. Understanding what functions are and how they are built is important, but how are these pieces of reusable code put to work in the bigger program? In this video, we will use defined functions within a program. To use a previously defined function, you need to call it from within the program. Let's break down the process of calling a function step by step. First, call a function by using its name followed by parentheses. Second, if the function has parameters, provide them within the parentheses. Suppose we have a function named calculateTotal to calculate the total cost of items in a shopping cart. To call this function, you would write calculateTotal, then open and close parentheses next to the function name. Inside the parentheses, write the words items, which is the parameter passed into the function. That's how functions are called in a program. When you call a function, it executes the code inside the body and performs the specific tasks. Now let's explore how the execution of the function works. First, the program control enters the function body. Second, the code inside the function is executed line by line. And third, if the function has a return statement, it returns a value to the caller. The return statement specifies the value that the function returns. You can store the return value in a variable or use it directly. In this video, you learned how to work with defined functions within a program. We explored how to call functions and understand their execution, as well as their return values. You already learned that functions are pieces of reusable code. Methods are very similar to functions. In fact, methods are a kind of function, but while methods are functions, not all functions are methods. In this video, we will define methods and how they differ from functions. Let's start by providing an overview of what a method is. Methods are reusable pieces of code just like functions, but what sets methods apart from functions is their connection with objects used in object-oriented programming, or OOP. A method operates like a function. However, a method is grouped with other code to work together as a single unit. Methods use the code they're grouped with to perform operations. Developers use the term class to refer to this unit of code. Now that we've defined methods in the context of classes, let's step back and recap the concept of functions. Understanding functions helps us understand the differences between methods and how we use them in object-oriented programming. Functions are blocks of reusable code designed to perform a particular task. We can call it at any time within the code. Think of a function as a standalone tool like a screwdriver that you can use anywhere you need. Now you might wonder, what's the difference between a method and a function? It's a great question and one that often confuses developers, especially when learning them. Methods and functions are similar but have distinct differences, especially in the context of OOP. A method is similar to a function but always is associated with a class. Methods can access and modify the data within the class. Think of it this way. All methods are functions, but not all functions are methods. A function can exist on its own independent of any class. For example, a function that calculates the square of a number can be used anywhere in your code without being tied to a specific class. On the other hand, a method is always a part of a class. With this overview of the distinction between methods and functions, let's explore how to define and create a method within a class. To define a method within a class, you need to write a function inside the class definition. For example, you can create a class called myClass and have a method in the class called myFunction that takes two properties, A and B. This associates the function with all the other code that's grouped within the class. Also, the myFunction method can only be called in other application code as a part of the class. It can't be called independently of the class. Think of a function like takeout food and a method like a dine-in meal. You can order a takeout sandwich from a shop and get it anywhere, but you only get the sandwich. If you want a specific meal at a dine-in restaurant, you have to go to the restaurant's location, but you also get to use all of its amenities and services. Functions allow us to create general reusable blocks of code that a program can use anywhere. For instance, a developer could make a function to calculate the total price of items in a shopping cart. They can then use this function anywhere in the application. In contrast, we can use methods for operations specific to data and behaviors in the class it's a part of. For example, you could create a product class with a method that updates the product's inventory count. This method is specific to the product class and modifies its data. Functions and methods are very similar in how they work, and their differences lies in how they're written in code. You can use both functions and methods to do work in code. Functions do their work independently, while methods do their work within classes. In this video, we define methods and how they differ from functions. Methods are functions associated with classes in OOP, while functions are general blocks of reusable code. Understanding these concepts is fundamental to efficient programming and prepares us for deeper exploration into object-oriented programming. Understanding syntax is crucial for any programmer. It's the foundation that allows you to write clear, error-free code. Grasping the syntax of C# methods is key to unlocking their full potential. In this video, we will explain the syntax of methods in C#. The syntax for creating methods in C# involves several key components: access modifiers, return type, method name, and parameters. Let's review these concepts. Access modifiers in C# are keywords that define the accessibility of a method, such as public, private, protected, and internal. Use access modifiers as security levels to determine who can access the method. For example, a public modifier means that any other code can access the method. A private modifier means that only the class itself can access the method. Methods like functions can not only take in values, but return values back to the code that called them. The value the method returns has a type that restricts what the value can be. Let's examine that next. The return type specifies the data type of the value returned by the method. For example, if the method returns a name, the return type would be string. If it returns a whole number, the return type would be int. If the method does not return a value, then the return type is void. Every method must also have a name. Typically, a method name provides some information about what the method does. Next, let's explore how the method's name functions when defining a method. A method name is the identifier used to name a method in programming. It is a unique label that allows developers to refer to and invoke the specific method within the code. Developers should follow the best practice of naming methods in a way that describes what they do. For example, a method named capitalized first name is much more descriptive than method 001. Now let's explore the parameters that methods use to receive data. Parameters are the input values the method accepts. They are variables passed into the method to provide it with data, and they are enclosed in parentheses after the method name. Finally, let's explore member variables that store the state or properties of an object. Member variables are variables that are associated with an object or class. Methods use or modify these member variables to manage and interact with an object's data. Now that you understand the structure of methods, let's explore how the concepts apply to declaring a basic method in C#. The structure of a method declaration in C# includes access modifiers, return type, method name, and parameters. For example, the addNumbers method has this basic structure. Let's break down the method addNumbers into its parts. The keyword public is the access modifier, meaning that any other code can access the method. The keyword int is the return type, meaning that the method returns an integer value. Next, we include the method name. In this case, the method name is addNumbers. The next part of the structure is its parameters. If the method has multiple parameters, they are separated by commas. In the example, we specify that the method takes two integer parameters, a and b. We'll add the member variables next. Both are integer data types, and we use the names member a and member b for these variables. We'll initialize them to the value of the input parameters a and b respectively. Finally, we add the method's body, which contains the code defining the work the method performs. Here, we write the statements that define the method's behavior. In our example, the method adds the values of the two member variables and returns the result. Let's apply these concepts to a real-world example. We'll create a method called calculateDiscount to compute the discount on a product. Let's explore how to implement it in C# by breaking down the syntax step by step. First, we define the access modifier. In our example, the keyword public will make the method accessible from any other class. Then we include the method's return type. In this example, it will return a double representing the discount amount. The next step is naming the method. As we mentioned, we'll name it calculateDiscount. Now we include the method parameters. In our case, the method will take two parameters that accept the type double, original price and discount rate. A double type is a number that includes decimal places. Next, we'll add two member variables. The member origPrice is a double variable initialized with the value of original price. The member variable discRate is also a double initialized with the value of discount rate. Finally, we define the behavior of the method in its body. In this example, the method will multiply origPrice by discRate and return the result. This calculateDiscount method has all the components a method should have. It has an access modifier, a descriptive name, a return type, input parameters, and it does the work on those parameters to return a value. This is a basic template for any method you can write in C#. In this video, you learned about the syntax and structure of methods in C#. By mastering these basics, you can create your own methods and perform various application tasks. Imagine trying to build a piece of furniture without any instructions. You'd have to figure out each step on your own every single time, which would be frustrating and slow. Methods in programming are like useful instruction guides. They break down tasks into simple, reusable steps that make complex problems much easier to work on. In this video, we will describe practical use cases for methods in C#. Some common use cases of methods include performing calculations, handling events, and manipulating data. Let's examine each of these and explore a few examples. Methods are often used to perform calculations like adding numbers, computing averages, or solving equations. By using methods, developers can create a block of code once to perform the calculation and reuse it where it's needed.
For example, the method add takes two integer parameters a and b and returns their sum. Methods can be written to handle events like button clicks or mouse movements, providing interactivity in applications. Think of this as pressing a button on a remote control and triggering a specific action. For instance, we can create a method called button click to handle interactions with the application's user interface. When a user clicks a button in the application, the code inside the method button click is executed. In this example, the method will print button click to the console. Now let's examine how methods are used to manipulate data. Developers use methods to sort arrays, modify strings, and process collections. For example, the method sortList sorts the array of input parameter and returns the sorted list. Let's explore some real-world examples of methods in action and how to implement them in C# by breaking down the syntax step by step. In an e-commerce application, a method can calculate the total price of items in a shopping cart. First, we include the method structure with all its elements. We define the method as public with a decimal return type. The method accepts a list of prices in the shopping cart as the input parameter. Next, in the method's body, we define and initialize a variable named total to accumulate the sum of all the prices in the list. Now we include a for loop to iterate over each price in the prices list. Inside the loop, each price is added to the variable named total to accumulate the sum of all the prices. After the loop has processed all the prices, the method returns the total, which now contains the sum of all the values in the prices list. Methods are well suited for processing data. Next, we'll explore an example of how to use a C# method to handle events. In a game, methods handle events like player movements or actions, enhancing the gaming experience. We define the method onPlayerMove as private, which means it can only be accessed within its class, and it does not have a return value. This method will be triggered when the player changes position in the game. We pass in data in the parameter e, which uses an event_args data type. The event_args data type is what C# uses to capture information about events. Next, the method's body accepts a variable called sender, which has the generic type object. We assign sender to a variable called avatar, which has the player type. When we assign sender to the avatar variable, we tell C# that sender is the player type. Now we include an if statement to check if the assignment was successful by verifying that the avatar variable is not null. In that case, the method proceeds with updating the player's position. Finally, we print the player's position to the console using the position value in the parameter e, the event passed to the method. This information can help debug or provide feedback within the game. For the final example, we'll explore an example of using a method to process data. In a weather application, a method processes and displays weather data, providing valuable information to the users. Let's define the structure for this method. The displayWeatherData method is a public void method, meaning it can be accessed from any class and does not return a value. Also, the method takes a list of weather data objects as input to process and display weather information. Now we include a for loop to iterate over each item in the data list. The variable weather represents the current weather data object in each iteration. In each iteration of the loop, the code processes the weather data by formatting it into a readable string called report. To generate the report string, we take advantage of the properties of the weather data class. For this example, we'll print the date and temperature. Finally, we display the formatted report string in the console. In this video, you learned some practical use cases for methods in C#. We explored how methods perform calculations, handle events, and manipulate data with real-world examples. Using methods effectively allows you to write more organized and efficient code in your applications. When working on a project like managing product discounts, repeating the same code for each calculation can quickly become difficult to update and manage. Wouldn't it be great if you could package those tasks into a single reusable block of code that you could call whenever you need to? That's how methods work in programming. Understanding how to call methods within a program makes your code more efficient, less likely to have errors, and easier to manage. In this video, we will explain how to call methods within a program and how to pass arguments to methods using input parameters.
A method is a block of code designed to perform a specific task. In object-oriented programming, it is a function associated with an object. It operates on the data contained within the object. Methods can accept data in the form of arguments. Arguments are the values or data you pass into a method or function when you call it. The method can use the data and arguments to perform its operations. Before you can call a method, it must be defined in your program. A method definition includes two key components, the method header and the method body. First, the method header specifies its name, return type, and parameters. The method name can be anything you choose, but developers usually name methods in a way that describes what they do. The return type of the method can be any valid C# return type or an object that you define somewhere else in your code. Second, the method body contains the code that runs when the method is called. A method's body can be very complex or very simple, but it's the part of the method that does all the work. You can even call other methods from a method body. With the method defined, you now can call the method so it can do work for you. Let's review how that's done. To call a method, write the method's name followed by parentheses. If the method requires parameters, you will pass the arguments within the parentheses. If a method has a return type, declare a variable with the same return type as the method and assign it to the method. The variable will be filled with whatever the method returns. The method's body must return a value of the same type you declared in the method's header, or an error will occur. Now let's explore how this definition comes to life in an example. We'll create a greet user method that prints hello user to the console, and then call the method to execute it. First, we'll define the method header as public void greet user. The void keyword indicates that the method does not return a value to the caller. Then we'll create the method body, which prints the message to the console. To call the method, we write its name followed by a pair of parentheses. Since there are no parameters, the parentheses remain empty. This line of code tells the program to execute the code within the method. In this example, invoking greet user will print hello user to the console. Now that we've covered defining and calling methods, let's explore how to make them more dynamic by passing arguments. We'll go through each step of defining and calling a method, but this time we'll include parameters in the method's header and arguments in the code that calls it. Let's define a method called addNumbers that takes two integers as parameters and returns their sum. The first step is to define the method header as public int addNumbers, including the integers parameters a and b. Then we define the method body, which returns the result of adding a and b. With this structure, our method is ready to perform calculations. Finally, we'll call the method by writing its name and passing the arguments 5 and 10. Since the method returns an integer value, we assign the result to a variable of the same type. This tells the program to execute the code within the method and store the result in the variable result. In this example, after invoking the method, the variable result will contain the integer 15. In this video, you learned how to call methods within a program. These skills are crucial for writing clean, efficient, and reusable code. Mastering them will equip you to confidently work on more complex programming tasks. Have you ever wondered how a calculator app instantly shows results? It's all thanks to method return values, a concept we're about to master. This skill enhances your program's functionality and enables you to create more dynamic and efficient solutions. Mastering how methods return values and how to use them is a key skill that will take your programming to the next level. In this video, we will explain how methods return values and how to use them. The return type of a method specifies the data type of the value the method will return after execution. A method can return any type that's valid in the programming language you're using. In languages like C#, you can even use custom objects that you create as the return type. The return type is specified in the method definition. Let's explore the two return types and how they can be used in your code. A method with a void return type does not return any value. It simply performs an action. For example, the method printMessage prints a message to the console but does not return a value.
Methods with return types other than void return a value that can be used by the code that called the method. For example, the method getNumber returns an integer. When invoking a non-void method, you can assign its value to a variable of the same type, or use it directly to evaluate conditions or perform operations. For example, we can declare a variable called number with the int data type and assign it to the result of the getNumber method, which also has an int return type. Return types define the type of value that the method returns. It doesn't define the value itself. This is done in the method's body code using a return keyword statement. Let's examine that next. A return statement is used within the method's body to return a value to the caller. This is how you send data back to the part of the program that called the method. After your method's body has performed the work it needs to, the return statement ends the method execution and returns a value. The value the method returns needs to be of the same type you define in the method's definition. For example, the line of code return 42 ends the getNumber method and sends the value 42 back to the caller. Now let's apply these concepts to a real-world scenario. Suppose you're working for a company which specializes in customizable jewelry. You need to create a method that returns the price of a customized jewelry based on the options the user selects. First, we define the calculatePrice method. This method takes 3 parameters, material, size, and a Boolean variable to determine whether we're including engraving. The return type is a double, indicating that the method will return a double value due to the price calculation. You then write the method's body. The method performs the calculation by starting with a base price of $50 and then adding additional costs based on the selected materials like gold or silver, the size of the piece, and any optional engraving features chosen by the user. The method's body returns a double value indicating the final price. To call the method, the website collects the customization options and uses the customer's selections as input parameters for the method. In this example, the customer specified gold for the material, medium for the size, and true for engraving. These values are then passed as arguments to the calculatePrice method. The method stores the final price in the price variable. You can then use the price variable and other code to display the price to the customer or store the value for later use. In this video, we learned the essential concepts of how methods return values and how you can effectively use them in your programs. You'll be well equipped to write more dynamic and efficient code by mastering these return types. Understanding how to call methods effectively is crucial for any developer. It's not just about knowing the syntax. It's about using methods to solve real-world problems and create efficient, functional code. Whether you're displaying a welcome message, calculating sums, or validating user inputs, these tasks all depend on calling methods correctly and purposefully. In this video, we will call methods to perform specific tasks within a program. Recall that a method is a function associated with an object in object-oriented programming that operates on the object's data. They accept arguments which are data passed into the method. Now let's explore some common scenarios where developers use methods to get work done in applications. Suppose we're creating a desktop application in C# for a fictional company called Greenway. Greenway is a transportation company specializing in eco-friendly delivery solutions. The application will need a C# method to display a welcome message when a user logs into the application. Let's create a method called displayWelcomeMessage for this purpose. First, we define the method header as public void displayWelcomeMessage. We then include the method body, which displays the text "Welcome to Greenway" in a message box when the user logs into the application. To call the method, write its name followed by a pair of parentheses. Since there are no parameters, the parentheses remain empty. This tells the program to execute the code within the method showing the welcome message to the user. Next, we'll add a method to calculate the sum of two numbers the user enters. We'll create a method called calculateSum for this purpose. Let's break down the syntax step by step. As in the previous example, we define the method header as public int calculateSum and include two integer parameters, a and b.
In the method body, we return the sum of the input parameters. To call this method, we assign its result to a variable of the same type and then print the sum to the console. In this example, the console will display the sum is 15. Next, we'll use a method to validate whether a user is old enough to access certain features. We'll create a method called isUserOldEnough to validate the user's age and display an appropriate message to let the user know if they're old enough. Let's explore how to implement it in C# by breaking down the syntax step by step. First, we define the method. We use a public access modifier and a bool return type to indicate whether the method returns a true or a false value. It will take the user's age as input and an integer argument we'll name age. In the method body, we'll use an if-else statement to evaluate whether the age argument value passed into the method is 18 or above. If it is, we will return true from the method, otherwise we return false. Next, we write an if-else statement to check the result of the isUserOldEnough method call using the age the user entered as the argument. If-else statements check for true and false values. If the value in the parentheses is true, the code in the if portion of the code runs. If it's false, the else portion is executed. Since our method returns a Boolean value, we can check its return value right in the if-else statement. Finally, if the method's call result is true, it means that the user is old enough to access the content. We show the message access granted to the user. Otherwise, we show them access denied. In this video, you learned how to call methods to perform specific tasks within a program. We began by understanding the basic concepts of methods and parameters and applying these concepts to real-world scenarios. By mastering these techniques, you're now better equipped to write organized and reusable code, making your programs more efficient and easier to manage. In this step, you will learn how to define a simple method that performs a task and call it in a program. A method allows you to write reusable code blocks that you can call wherever needed. When you define a method, you are creating a reusable piece of code that you can call or use later in your program. Defining a method means you tell the program what the method will do, but it won't run the method until you call it. Think of it like writing a recipe. The recipe tells you what to do, but you won't start cooking until you decide to make the dish. When you call a method, it's like saying, now go follow the recipe. Since this method doesn't return any value, we will use the void keyword. Void means the method performs an action, but doesn't give anything back. Now we will extend our understanding by creating a method that accepts parameters. This is useful when the method needs specific values to perform its task. Parameters allow us to pass data into a method, making the method more flexible and reusable. When you define a method with a parameter, it acts like a placeholder for that value that will be passed in later. The argument is the actual value you pass when you call the method. Think of parameters as placeholders inside the method. The argument you pass when calling the method replaces the parameter. This makes the method reusable with different inputs. In this example, we're using string for the parameter because we want to pass in text, a name. And you can use different data types like int for numbers or bool for true false values to change how the method behaves. Next, let's create a method that returns a value. Methods can return values that you can use in the rest of your program. Here we'll write a method to calculate the sum of two numbers. The return keyword allows the method to give back a value to the code that called it. This means that after the method runs, it provides a result, like the sum of two numbers, that can be used elsewhere in the program. When you call the calculate sum method, it returns the sum of the two numbers you give it. The return value can be stored in a variable and used in other parts of the program, such as printing or performing further calculations. Without return, the method only performs an action without giving anything back. In this step, you will create a method that returns a bool value based on a condition. The method will check if a number is positive. A bool value is either true or false.
When a method returns a bool, the method is making a decision. Is this condition true or false? This is useful when combined with if statements, which also rely on true and false statements to make decisions in your program. For example, the method might check whether a number is positive and return true if it is or false if it is. In this final step, we'll create a practical program to validate the user inputs using methods. The program will ask for the user's age and check if they are old enough to drive. When the user enters their age, the input is received as text, a string. But since age is a number, we need to convert that text into an int, an integer, so that we can compare it against a number like 18. This is why we use int.parse. Once the age is converted, we can pass it to the isOldEnoughToDrive method to check if the person is 18 or older. The isOldEnoughToDrive method returns true or false based on the user's age, and we use this value in an if statement to display the correct message. In programming, creating flexible and reusable code is essential for efficient software development. Methods, which are blocks of code designed to perform specific tasks, play a crucial role in this process. Parameters allow us to pass information into methods, enabling them to perform tasks with varying inputs. This flexibility is a fundamental aspect of writing adaptable, maintainable, and efficient code. In this video, we will define what parameters are and their role in methods. Parameters are variables in a function or method definition that specify what inputs the function can accept. They act as placeholders for the value that will be passed to the method when it's called. For example, in the method calculateSum, int a, int b, a and b are parameters. Now let's explore the role of parameters in methods and how they enable methods to do work to manipulate data and return meaningful results. Parameters enable you to pass data into a method when it's called. This data can then be used to perform specific tasks or calculations. The primary role of parameters is to make methods more flexible and reusable. They allow the same method to work with different inputs and produce varying outputs depending on the values the developer or user provides. There are two main types of parameters in C# methods: value parameters and reference parameters. Let's explore each of these and how they function and how methods operate. Value parameters pass a copy of the argument's value to the method. Changes made to the parameter within the method do not affect the original argument's value. For example, void displayValue int num receives a copy of the num value. The original value of num from the calling code isn't impacted. Reference parameters are the other type of parameter. These parameters receive a reference to the original argument, allowing it to modify the argument's value in the code that passed it. This is done using the ref keyword in languages like C#. For example, void update value ref int num allows the method to update the original num value. Now let's explore some real-world examples of how parameters are used in methods, starting with an example that includes a method with a value parameter. Suppose we create a method called printMessage that takes a value parameter input. We can call this method by passing in a string value, welcome customer, and the method will receive a copy of that string. It can then modify it without impacting the original value from the calling code. In this example of a method with a reference parameter, the double value method takes a number by referencing it and doubles it. Notice that the method return type is void and we don't use the return keyword in the method body. But the argument passed into the number parameter will still be updated in the code that called it. Suppose we declare a variable called myNumber and assign it the value of 5. If we pass it to the double value method, the variable myNumber will be updated from 5 to 10. This change will also be reflected in the code that called it. When this code is run, the console will display 10. In this video, you learn what parameters are and their roles and methods. We discussed the difference between value and reference parameters, understanding how each type serves a specific purpose in managing data within methods. By mastering the use of parameters, you're equipped to write more adaptable, efficient, and maintainable code. which is a fundamental skill for any programmer aiming to build robust software solutions. Think about the last time you used a search bar in your favorite app. Perhaps you used it to find a recipe or check the weather. Have you ever wondered how your input transforms into the exact information you want? The secret lies in how that data is passed into methods behind the scenes. This core programming concept makes your interactions with apps smooth and responsive. In this video, we will describe how to pass data into methods using parameters. Let's start by reviewing the structure of a method. Recall that a method is a function associated with an object that operates on the data within the object. Parameters, which are variables listed in the method's definition, serve as placeholders for the values that will be passed when the method is called. These values, called arguments, are the data inputs that the method uses to perform its operations. When a method is called, the arguments must match the number and type of the parameters defined in the method. Arguments and parameters enable methods to do meaningful work by providing the method with data. In order to receive arguments, the method has to be declared with parameters so it can accept the arguments being passed into it. We add parameters within the parentheses of the method declaration and declare the parameters with data types so we know what type of data the method will accept. Let's explore a real-world implementation of this structure. Suppose we want to create a method that displays a welcome message to a user when they log into a website. First, we define the method and specify the parameters it will accept. The method greetUser receives the user's name in the parameter username and displays the greeting hello plus the user's name that was passed in. Notice that the username parameter is declared as a string data type. This means the method will only accept string data as arguments. Next, we call the method greetUser and pass the required arguments, in this case the user's name. To greet a user named Alice, call the method and pass the user's name as string data in the parentheses. Finally, the method executes its code using the parameter we passed in. In our example, the method shows a message box with hello Alice as the message. Now let's build on this foundation by passing in more than one parameter to our method. Methods can accept multiple parameters by adding them to the method definition and separating them with commas. For example, we'll extend the greetUser method by including a parameter that displays the days since the user was last logged in. We add a new parameter called lastLogin with an int data type. We separate this parameter from our existing username with a comma between them. Next, we'll update the method body to show the user a message box with the original hello message. We'll also add an additional line that says it's been plus last login plus days since you last logged in. This method will use the value of the parameter last login when it constructs the message. Finally, we call the method and pass in both arguments. In addition to passing Alice as the username argument, we'll pass in the integer value 2 for the last login argument. The user gets a message that reads, "Hello Alice, it's been 2 days since you last logged in." In addition to passing in arguments and displaying them, parameters can be manipulated within methods to perform various tasks. To demonstrate how this is done, let's create a method called joinStrings that combines or concatenates two strings we pass in as arguments and returns the result. In our method declaration, we add two string parameters, first name and last name, and use the string keyword to define the return type of the method. The method's body will return the concatenation of the first name and last name values, adding a space between them. We'll call the method by creating a new string variable called fullName and assign the result of join strings to it. We'll pass in Alice as the first name and Martinez as the last name argument. Next, we'll add a line of code to write the value of the fullName variable to the console. Finally, when we call the method, it concatenates the strings we pass in and prints the full name value, Alice Martinez, to the console. In this video, you learned how to pass data into methods effectively using parameters and arguments. You explored the syntax of defining and calling methods with both single and multiple parameters, and saw how different data types ensure that our methods receive expected inputs. By understanding these concepts, you now have the tools to create more dynamic and flexible code that can work with various inputs and perform specific tasks efficiently. This foundational knowledge is crucial for writing organized, maintainable, and reusable code in any programming language. Imagine you're writing a function that processes user data, but it can only work with one specific user profile at a time. What if you needed this function to work with different user profiles without rewriting the code each time? This is where parameters come in. Parameters give your methods the flexibility to work with a wide range of inputs, making your code more powerful and adaptable. In this video, we will use parameters to enhance method functionality. Let's explore how parameters are used with methods to create a powerful software solution. For example, consider a financial application that uses a method to inform users about the balance on their checking account. First, the method showBalance accepts a parameter called balanceAmount that receives data about the user's account balance. Since it's storing financial data that may have precise decimal places, we'll declare this parameter as a decimal type. We declare the method with a void return type since the method doesn't return a value. Next, we add the method body, which displays a message box with the text "your balance is," followed by the value of the balanceAmount parameter. Finally, we'll call the showBalance method and pass in the numerical value of $2,000.50 as the argument. The method will display the message "your balance is $2,000.50. By using a parameter with this method, we can pass in any value for balanceAmount, and the method will display the amount. We wrote the method once, but we can use it to display different amounts at different times. Next, let's expand the use of parameters by exploring a method that performs an operation on a list of values that we pass into it. We'll create a new method for this financial app that totals the user's expenditures called showTotalExpenditures. First, we declare the method as void and add a parameter called expenditures. We declare this parameter as a decimal array. Arrays are used to store lists of items so that it can hold more than one value. Next, in the method's body, we'll declare a variable called total to hold the calculated total and initialize it here to the value of 0. Then we create a for loop that goes through each value we passed into the expenditures parameter. Each time the loop loads an item in the list, it adds it to the total variable. When the loop reaches the end of the items in expenditures, it shows the user a message box with the message, "Your total expenditures for the day are," along with the value in the total variable. Finally, to call the method, we define a variable called expenses as a decimal array. We'll initialize it with 4 numeric items representing the user's expenditures: $15.25, $8.50, $12.99, and $5.75. Then we call the showTotalExpenditures method, passing in the expenses array as an argument. The method will produce the message, "Your total expenditures for the day are $42.49. Finally, let's consider a more complex scenario where we'll use a method to calculate monthly loan payments. We'll call this method calculateLoanPayment. The method calculates the monthly payment for a loan using the loan principal, interest rate, and loan term. First, we'll declare the method with 3 parameters. We'll declare the principal and interest rate parameters as double data types since they'll hold numerical data with the decimal point. We'll declare the variable term in years as int since that will be a whole number. Next, in the method's body, we'll calculate the monthly interest rate in a double variable called monthly rate. We'll set this variable equal to the value in the interest rate parameter divided by 12. We'll also create an integer variable called term in months that stores the value of the parameter term in years multiplied by 12. This will store the total number of months of the loan. Now we'll create the code so the method will return the monthly payment figure. For this example, we'll not go into the specifics of the formula calculating the principal. But it is important to note that the method uses the values of the parameters and the monthly rate in term and month variables we calculated to perform a complex calculation and return a simple result for the monthly payment. Finally, we'll call this method passing in arguments for each parameter. For example, when this method is called with a loan principal of $10,000, an annual interest rate of 5%, and a term of 5 years, the monthly payment calculated is approximately $188.71.
In this video, you learned how parameters are used to enhance the functionality of methods. With parameters, we can create methods that adapt to different situations, work with various inputs, and overcome complex tasks. Whether it's something simple like greeting a user, or more complicated like processing an order or calculating loan payments, parameters allow us to design versatile and reusable code. Imagine creating complex programs with ease where each part of your code works together seamlessly. This isn't just a programmer's dream, it's a reality you can achieve by mastering the art of combining functions and methods in a single program. From enhancing code readability to boosting efficiency, the benefits of this approach are truly transformative for developers at every level. In this video, we will combine functions and methods in a single program, focusing on program design and the benefits of a modular approach. Combining functions and methods in a single program is a powerful technique that can significantly improve your coding efficiency and program structure. Let's explore how to design a program that integrates multiple functions and methods effectively. First, when designing a program that integrates multiple functions and methods, start by breaking your program into smaller, manageable tasks. Think of the goals your application needs to help users achieve. Then, work on isolating the individual tasks it will take to help the user accomplish those goals. Each task can be represented by a function or method, making your code more organized and easier to understand. Let's consider a simple banking application as an example. We might divide the app's tasks into tasks like checking account balances, depositing money, withdrawing money, and calculating interest. Each of these can be a separate function or method in our program. Next, consider the relationship between these tasks. Some functions may need to call others, while methods might operate on shared data. By planning these interactions, you create a roadmap for your program structure. In our banking app example, the withdrawal function might need to call the balance checking function to ensure sufficient funds. When a customer attempts to withdraw money, the program will first check the current balance, compare it to the withdrawal amount, and only proceed with the withdrawal if there are sufficient funds in the account. This demonstrates how one function, withdraw, can rely on another, check balance, to perform its task. Remember to keep your functions and methods focused on single tasks. This principle, known as the single responsibility principle, makes your code more modular and easier to maintain. The single responsibility principle states that a class, function, or module should have only one reason to change, which means it should only be responsible for one specific functionality or task. When these items have only one well-defined purpose or task, they're easy to understand, maintain, and test. By designing your software using the single responsibility principle, it becomes modular. Taking a modular approach to combining functions and methods in your application can make your code easier to maintain and reuse. This is called modularity. Modularity is the practice of dividing a program into separate, self-contained units or modules, each responsible for a specific piece of functionality. Let's explore the benefits of modular code. First, modular code is more readable. By breaking your program into distinct functions and methods, you create natural divisions in your code. This makes it easier for you and other developers to understand and navigate the program structure. In our banking app, having separate methods for each operation, deposit, withdrawal, check balance, makes the overall structure of the program more clear. A new developer joining the project could quickly understand what each part of the program does without needing to decipher complex code. Another benefit is that modularity enhances code reusability. When you have well-defined functions and methods, you can easily reuse them in different parts of your program or even in other projects. This saves time and reduces the amount of duplication in your code. For instance, the interest calculation method in our banking app could be reused in multiple contexts, for savings accounts, loans, or even in a completely separate investment tracking application. By keeping this functionality in its own method, we make it easy to move this feature to other programs or expand its use within the same program. Lastly, a modular approach facilitates easier testing and debugging. You can test each function or method independently, making it simpler to isolate and fix issues in your code. In the banking program, we could easily test the withdrawal functionality independently. We could set up a test where we create an account with a known balance, attempt a withdrawal, and then verify that the balance has been correctly updated. If there's an issue with withdrawals, we can focus our debugging efforts on this specific function without having to worry about the rest of the program. In this video, you learned how to combine functions and methods in a single program, focusing on program design and the benefits of a modular approach. Remember, the key is to think modularly. Create clear relationships between your functions and methods, and always keep reusability and testing in mind. Have you ever spent a long time assembling something only to realize you made a small mistake at the beginning? You feel a deep frustration as you realize you have to disassemble it and start all over. Similarly, writing applications properly from the beginning can save you hours of rework. Properly using functions and methods is one way to avoid creating small mistakes that can lead to big problems. In this video, we'll develop programs that use functions and methods to accomplish specific goals. Functions and methods are code blocks that allow you to break down complex problems into smaller reusable pieces. We use functions in JavaScript and methods in C#. Let's explore how to use these tools, starting with functions. A function is a reusable block of code designed to perform a specific task. This helps organize code when solving problems that involve repeatable tasks. Now let's investigate an example of how to use a JavaScript function to perform the same task with different inputs. This JavaScript code declares a function named calculateTotalPrice. It accepts one parameter, item prices, which is a list of prices. We initialize the total variable to 0, which will hold the sum of all the item prices. We then use a for loop to get each price in the item prices array. Inside the loop, each price is added to the total variable. Once the loop finishes, the total sum is returned as the output of the function. This function is useful in scenarios like summing product prices in a cart on an e-commerce website. Now that we have the function defined, let's examine how we call it to calculate a list of values. We'll assign the variable total price to the function calculateTotalPrice. Total price will store the value that the function returns. By assigning the function to the variable total price, JavaScript will call the calculateTotalPrice when it reaches this line of code. When we call the calculateTotalPrice function, we pass in a list of numbers, in this case 10, 20, and 30, representing item prices. The console.log function prints the total price to the console. This presents you with the output. This example simulates calculating the total cost of products in a shopping cart. Now that we've seen how functions work in JavaScript, let's move on to methods. Methods are similar to functions, but they are part of a class in C#. This structure makes it easier to work with objects in object-oriented code. We'll look at an example of a method that calculates a discount. Methods are similar to functions in that they are reusable blocks of code that perform specific tasks. Methods differ from functions because they are used in objects in object-oriented programming. They can use components of the object, such as other methods or the object's data when working on a task. Let's examine how you can use a method to complete a repeatable task in C#. First, we declare a product class, which will contain the method. Inside the class, we define the calculateDiscount method. It takes two parameters, price and discount rate. Finally, it returns the discounted price. This method could be used in an online store to apply discounts to products. The method calculates the discount by multiplying the price by the discount rate and subtracting the result from the original price. Now we need to call the method to apply the discount. In the method call, we pass in the price and the discount rate as parameters. First, we create an instance of the product class using the code newProduct. Then we call the calculateDiscount method on the product object, passing in 100 as the price and 0.2 as the discount rate. The method returns the discounted price, which is stored in the discounted price variable. Finally, the console.writeLine function prints the discounted price to the console. This simulates calculating and displaying the price of a product after a discount is applied.
In this video, you learned how to use functions for repetitive tasks and implement methods for handling specific operations within an application. By applying these techniques, we can create modular, reusable, and maintainable code that not only solves immediate challenges, but also sets a strong foundation for future development. When learning to code, you'll often encounter various programming concepts like functions, methods, loops, and conditionals, each powerful on its own. But the real challenge exists in understanding how to combine these elements to create a complete working program. It's common to have these tools at your disposal, but you need a clear strategy to integrate them effectively. In this video, we will develop a comprehensive program that integrates all the concepts you've learned so far. Developing a comprehensive program involves 3 phases: project planning, implementation, and final integration and testing of every aspect of the program. By following a structured approach, you can create a program that's not only functional, but also efficient and maintainable. Let's now explore each of these phases, starting with project planning. Start by defining the scope of your project. Ask yourself questions like, what problem is your program solving? What inputs will it manage, and what outputs will it generate? Clearly outlining the purpose and objectives of your program will help you stay focused during development. For example, if you're creating a simple calculator application, your scope would include working with basic arithmetic operations. Next, once you have a clear understanding of the project scope, identify the core functions your program will need. These are the building blocks of your program. For instance, in a calculator program, you might have functions for addition, subtraction, multiplication, and division. Each function should be designed to perform one specific task. This makes your code modular and reusable. The next step in your project planning is to integrate and consolidate features. In this step, you will assess what your program needs to accomplish and identify areas where functions and methods can be integrated or reused. For example, if multiple areas of your application require user authentication, your plan should include creating a single method for all authentication tasks rather than using multiple methods. This approach reduces the risk of errors and simplifies maintenance in the future. Finally, outline how the program will flow from start to finish. Consider the order in which functions will be called, how data will be passed between them, and where loops and conditionals will be necessary. For example, if your program needs to repeatedly ask for user input, a loop will be essential. Draw a flowchart or write pseudocode to visualize the logic before coding. Now that your planning is complete, it's time to move on to implementation. Here's where you'll bring your plan to life, applying all the concepts you've learned along the way. Recall that core functions we identified during planning, these are the building blocks of your program. First, you'll code each function and test them individually to make sure they work as expected. For instance, in a calculator program, you might start by writing the addition function and verifying its accuracy. For instance, in a calculator program, you might start by writing the addition function and verifying its accuracy before moving on to the next function. Next, once your core functions work, integrate them into the main program flow to perform more complex operations. For example, after implementing the basic arithmetic functions, you might integrate them to handle a full calculation based on user input. After the functions are integrated, use loops to manage repetitive tasks, such as continuously asking for user input until a valid response is given. Apply conditionals to make decisions within your program, like choosing which arithmetic functions to call based on user input. Test these elements thoroughly to ensure they interact correctly. Now that the functions are integrated and loops and conditionals have been applied, test each part of your program rigorously for bugs, logical errors, and edge cases. Debugging ensures your program works reliably under different conditions. Use print statements or debugging tools to trace and fix issues. Finally, with all components in place, the last step is to perform a full test in the complete system. This is where you validate that everything works together seamlessly. After careful planning, implementing, and testing each component individually, it's time to bring everything together in a final integration test. This helps you know that all parts of your program, functions, loops, and conditionals, work harmoniously to achieve the intended outcome. Make any adjustments and don't be afraid to modify your code as needed for better performance or readability. In this video, we explored the essential steps to develop a comprehensive program that integrates all the concepts you've learned. By carefully planning your project, identifying and implementing core functions, and ensuring the smooth integration of loops, conditionals, and methods, you've gained the knowledge to create well-structured and effective programs. This structured approach will empower you to confidently address complex programming challenges in your future projects. Methods in C# are like building blocks for solving problems. They allow us to break down a problem into smaller parts that are easier to manage. A method performs a specific task when called. We define methods using keywords. Public, this means the method can be accessed from anywhere in your code. Static, you can call this method directly from the main method without needing to create an object. Void, this means the method doesn't return any value. Its only job is to perform the task we give it. After defining the method, you must call it to execute the code inside. Defining and calling a method are two separate steps. Defining tells the program what the method does, and calling tells it when to execute. Methods become even more powerful when they take parameters. Parameters act as placeholders for data that we want to pass into the method. When we call the method, we pass arguments, which are the actual values that replace the parameters. This allows us to reuse the same method for different inputs, making the method flexible and reusable. For example, we will create a method that takes a name as input and prints a personalized greeting. Some methods can give back a result when they're finished. This is called a return value. To send a value back, we use the return keyword. This result can be stored in a variable or used directly in the program. Return values make methods more useful because they allow us to calculate something or get a result from the method and use it elsewhere in our program. For example, we will create a method that adds two numbers together and returns the sum. Methods can also return true or false values, which are called Boolean values. Boolean values are useful for decision making as they allow us to check if a condition is met and perform an action based on the result. We will write a method that checks if a number is positive. The method will return true if the number is greater than 0 and false if it's 0 or less. We will then use this method in an if-else statement to print whether the number is positive. In most countries, the legal driving age is 18. We will create a method that takes the user's age as input and checks whether they are old enough to drive. When the user enters their age, the input is received as a string, which is text. However, we need to use the age as a number, so we must convert it from a string to an integer using int.parse. This allows us to compare the age to 18. Next, we'll write a method called isOldEnoughToDrive that checks if the user's age is greater than or equal to 18. This method will return true if the user is old enough and false otherwise. Inside the main method, we will use an if-else statement to tell the user whether they are allowed to drive based on the result returned by isOldEnoughToDrive.
Functions and methods are crucial for creating well-structured, maintainable code. Integrating them effectively enables you to solve complex problems and develop efficient solutions. We began by examining the role of functions in programming, focusing on how they help structure and organize code. We also covered the fundamentals of creating and integrating functions seamlessly into your programs. Then we investigated different methods in C#, analyzing their syntax and diverse use cases to understand how they can improve your programming skills. Next, we analyzed how to call methods effectively, including understanding their return values and applying practical examples to real-world programming challenges. Then, we explored how to utilize parameters and methods, emphasizing efficient data transfer and their practical applications to improve method performance. Lastly, we examined how to integrate functions and methods into program development to address complex issues and build robust, efficient solutions. Congratulations! You have completed functions, methods, and scope. You've been exploring the world of programming, learning new concepts like variables, loops, and methods. But you might be wondering, how do I actually use all of this every day as a developer? Think of it like building a puzzle. Each piece, whether it's declaring a variable or managing logic within a control structure, plays an important role. When combined, these skills help you solve problems, create new features, optimize your code, and ensure your applications run smoothly. In this video, we will apply data types, variables, control structures, loops, and methods in integrated coding exercises. Let's review a piece of C# code and explore how these concepts are used together. Let's start with the data type we'll use in our methods. Our first line of code is public string calculate pass fail int student score. Here we're declaring student score as an integer or int. Recall that int is used when we need to store whole numbers. In this example, it will hold the student score. We also declare the return type as string, which will hold text values like pass and fail. Next, let's review the variables in the code. In the calculate pass fail and calculate grade methods, the parameter student score is used to represent the student score. Inside the print pass fail with grades method, we also use variables like pass fail result and grade to store the output from two methods before printing them. Now let's examine the method calculate pass fail. A method is a block of code that performs a specific task, in this example, determining if the student passed or failed based on their score. It takes the student's score as a parameter. Inside the method, we have a control structure, a simple if statement. If the score is greater than or equal to 60, the method returns pass. If it's less than 60, the method returns fail. Control structures like this allow our code to make decisions based on conditions. Next, we have a switch statement. We'll use this to determine the grade range of the student. By dividing the student score by 10, we can check if the score is in the 60 to 69 range, 70 to 79, and so on. This is another type of control structure, giving us more flexibility to handle different cases. Depending on the value, it returns a grade from A to F. Next, we use a loop. Here's a simple loop that runs 5 times, printing the result of our calculate pass fail method for different scores. Loops allow us to run a block of code multiple times, which is useful when you want to repeat certain tasks. The loop calls our method and prints the result for each iteration, displaying whether the student passed or failed. This demonstrates how we can combine methods and loops to process data efficiently. Let's explore the entire code from start to finish. We start by declaring and assigning a variable for the student's score. We have a method, calculate pass fail, to check if the score is a pass or a fail. Then we have a method, calculate grade, that uses a switch statement to handle different score ranges. Finally, we have a method, print pass fail with grades, which uses the loop to print out the results. This entire process shows how variables, data types, methods, control structures, and loops work together to solve a problem. If we run this code, the result will be the method's output for different scores based on our loop. The result prints the score, the result, pass or fail, and the grade, depending on the student's score. In this video, you learned how to apply data types, variables, control structures, loops, and methods together in a C# program. We examined the code line by line, demonstrating each concept in action. Keep practicing these key concepts and you'll get more comfortable combining them in your own programs. Imagine this. You're running a small grocery store. The aisles are filled with customers, but behind the scenes, chaos is brewing. You're trying to manage your inventory with pen and paper, and it's a nightmare. Items are missing, restocks are late, and pricing errors are costing you money. What if there's a way to solve these problems with some lines of code? Coding isn't just about writing lines of code, it's about solving real-world problems. In this video, we will solve real-world problems using a combination of learned coding concepts. Real-world problems often require a blend of different coding concepts, including loops, conditionals, and methods, to create effective and efficient solutions. No matter what coding methods you use to solve a problem, you'll always approach each problem using 4 key steps. Step 1, break down the problem. Step 2, identify coding concepts. Step 3, structure your code. And step 4, implement and test. By following this approach, you'll transform a complex problem into a series of straightforward tasks, making coding both effective and manageable. Let's use an example to illustrate this process. Imagine a small grocery store struggling with manual inventory management that needs an inventory system. Your challenge is to solve this problem by breaking it down using the right coding concepts, structuring your code effectively, and implementing and testing it thoroughly. Let's get started. The first step in solving any complex problem is to break it down into smaller, more manageable tasks. This means identifying the key functions or actions the system needs to perform and isolating them into individual components. By breaking the problem into smaller parts, you make it easier to focus on and solve each piece without getting overwhelmed by the complexity of the entire system. For the grocery store inventory system, you'll break the problem down into 2 main areas of functionality. First, you need to add new items by entering details like the item name, price, and quantity. Next, you need the ability to update items by modifying existing products. Once you've broken down the problem, the next step is to match each functionality with the appropriate coding concepts and tools. This involves choosing the right programming constructs like loops, conditionals, and methods that will help you implement each task. Identifying the right coding concepts ensures that your solution is functional, optimized, and easy to maintain. For the grocery store inventory system, you'll want to use the following. First, you'll need methods for adding and updating items. Next, you'll use if-else statements to validate inputs and ensure new items aren't duplicates. Finally, you'll use loops to search through the inventory when updating items. After identifying the necessary coding concepts, you'll plan how to organize your code. In this step, you should create a flowchart or write pseudocode to outline the sequence of operations. By structuring your code in advance, you make the coding process smoother and reduce the chances of running into logic errors. For the grocery store inventory system, you'll want to create a flowchart that outlines the steps for adding items to the inventory. Here's how you might build a flowchart. First, start with begin add item. Next, you include a task to input item details. This task prompts the user to enter the item name, category, price, and quantity. Then you'll have a decision to validate input. If the input is valid, you'll have the system move on to the next step. If the input is invalid, you'll have the system display an error message and go back to the input item's details. After that, you'll have a decision to check for duplicates. If a duplicate is found, you'll have the system display a message that the item already exists and start the process over at begin add item. If no duplicate is found, the system will proceed to the next step. Now you include a task to add item to inventory by storing the item details in the inventory list. Once that's done, you'll have a task to display a confirmation message that the item was successfully added. Finally, you'll end the add item process. This flowchart helps you visualize the sequence of operations and ensures each step is clearly defined before you start coding. Now that you've structured your code, it's time to move on to the final step, implementing your solution by writing the code and then testing it thoroughly. Implementing and testing your code ensures that your solution is not only functional, but also reliable. Let's break down how you might implement the grocery store inventory system. You'll start by developing a method to add new items to the inventory. The method checks if the item already exists in the inventory to prevent duplicates. If it does not exist, it adds the item to the list and confirms the addition. Next, you'll develop a method to modify existing items in the inventory. This method finds the item in the list to ensure it can be updated. Then it modifies the item as needed and confirms the update. Finally, you'll execute the program to test its functionality and verify how it works. When you run the code the first time you try to add apples,
The program should add it to the inventory and display a message saying, "Item added successfully." But the second time you try to add apples, the program will check for duplicates and find that apples is already in the inventory and display a message saying, "Item already exists in the inventory." This structured approach worked for solving the grocery store problem, and it can be applied to any coding challenge you work on. By breaking down complex problems, identifying the right coding concepts, structuring your code, and implementing effective solutions, you can tackle a wide range of real-world issues. In this video, you solved a real-world problem using a combination of learned coding concepts. Solving real-world problems with code requires more than just knowing individual concepts. It's about combining them in a way that addresses the challenge. We applied problem decomposition to break down problems, used top-down problem solving to identify coding concepts, structured our code with flowcharts, and implemented our solution using tools like if-else statements and functions. If you continue to practice and refine these skills, you'll become more confident in solving real-world challenges.
Clean, efficient, and maintainable code ensures that your programs run smoothly and makes it easier to debug, extend, and collaborate with others. By adhering to best practices, developers can produce code that stands the test of time, adapts to new requirements, and minimizes errors. In this video, we'll review and refine code based on best practices and peer feedback. I'll demonstrate these concepts using an example project in C#. We'll cover common pitfalls, coding best practices, and how peer feedback can enhance your code. Let's get started. We will begin by examining some basic code that determines if a student passes or fails based on a test score. Here's the code we have right now. First, we declare a public method called calculatePassFail that takes an integer called s. The function uses an if-else statement to check the score and then print pass to the console if the grade is greater than or equal to 60. Else it will print fail to the console. Although this code might seem accurate, developers must avoid a few common coding pitfalls. The first pitfall is unclear methods or variable names. Notice here that we have a variable called s. Recall that there are specific naming conventions for C#, such as using descriptive names and camel case for variables. At first glance, it isn't clear what s represents. This lack of clarity can make it hard to understand the code. Another pitfall is creating long functions that do too many things. In programming, this is referred to as the single responsibility principle. This principle states that a component should only be responsible for one specific task or function. In our example, the calculatePassFail method is not only determining if the score is a pass or fail, but also directly printing the results to the console. This means the function has two responsibilities: calculating the result and managing the output. Why is this not great? Because it makes the function harder to maintain. If you ever need to change how the result is displayed, say to write to a file instead of printing to the console, you'd have to modify this function, which should only be concerned with determining pass or fail. Finally, the third pitfall is the absence of clear comments that accurately describe your code. Without comments, it's difficult to understand the purpose of the code, especially for someone else or even for yourself after a few months. Now let's fix these pitfalls using some best practices. Best practices help you write clean, efficient, and maintainable code. First, let's use meaningful names. I'm going to change the variable s to student score. This way, it's immediately clear what the variable represents, making the code easier to understand for anyone reading it. Next, apply the practice of keeping functions short and focused. I'm going to break the calculatePassFail method into two smaller, more focused functions. First, I'll change the calculatePassFail method so it only determines if the score is a pass or fail. I'll change the if-else statement so that now if the student score is greater than or equal to 60, it will return pass, else it will return fail. Then I'll move the printing logic to a separate method called printPassFail that takes an integer variable called student score. I'll take the method's result as a string and then write the output to the console. Now our code follows best practices. calculatePassFail focuses on determining the result, while print pass-fail creates the display. This makes it easier to modify, debug, or reuse parts of our code in the future. Finally, it's best practice to add some clear comments to my code. Here I'm adding a comment that explains what the calculate pass-fail method does. Check if the student scores 60 or higher and return pass or fail. I'll also add comments in the print pass-fail method to explain what it does. Right inside the open bracket, I'll add call calculate pass-fail to determine if the student passed or failed, and before the console.write, I'll add print the pass-fail result to the console. Notice comments are preceded by a double slash to indicate to the computer that they aren't code to be executed. By following these best practices, our code is now clearer and more readable. It's easier to debug, maintain, and understand, whether by us or by someone else in the future. Now let's discuss peer feedback. Having others review your code is a great way to learn and make improvements. Notice here that I have some code that calculates a student's letter grade based on their test scores. The code includes a function called calculateGrade that takes an integer called student score. The function uses an if-else statement to check the score and return the grade A, B, C, D, or F. The code has been peer-reviewed in GitHub, and I have some comments to review. Notice one of the comments suggests to use a switch statement instead of multiple if-else statements for better readability and easier maintenance. Let's incorporate that feedback into our code. I'll start by replacing the if-else chain with a switch statement. First, I'll move the return keyword to the beginning of the line, followed by the variable name student score. Next, I'll call the switch statement by typing switch, and then I'll open a new set of curly braces to define the switch cases. Inside the braces, I'll specify each condition starting with scores greater than or equal to 90, using the arrow symbol, which is an equal sign and a greater than sign together, pointing to the letter A in single quotes. I'll repeat this pattern for the other ranges. Greater than or equal to 80 points to B, greater than or equal to 70 points to C, and greater than or equal to 60 points to D. Finally, I'll handle any score that does not match these conditions by using an underscore to represent all other cases and having it point to F. By using a switch statement, the code becomes more readable and easier to understand. Each condition is clearly outlined, which makes it simpler to follow compared to the original if-else chain. And there we have it. I've improved my code by applying best practices to some common pitfalls and incorporating peer feedback. Remember, writing good code is not just about making it work. It's about making it understandable, maintainable, and efficient. In this video, we reviewed and refined code based on best practices and peer feedback. These approaches help us make your code clearer, easier to maintain, and more adaptable for future changes.
Have you ever wondered why some applications run smoothly while others crash or behave unpredictably? The difference often comes down to one crucial step in the development process: debugging. In this video, we will explain the process and importance of debugging in programming. Let's begin by defining debugging. Debugging is the process of identifying and resolving errors or bugs in a computer program. Debugging is a methodical process that developers use to ensure their code works as intended. It involves examining error messages, reproducing and isolating the error, and analyzing and fixing the issue. Let's explore each of these in more detail. Debugging involves understanding the error messages your program generates and using them as clues to find the source of the problem. These clues are valuable because they point towards the section of code that's misbehaving. But interpreting these clues correctly is where the real challenge lies. Let's examine a real-life error message. The error message starts with null reference exception, which means the code tried to use an object that hasn't been initialized. It's null. Understanding this message is key because it tells you exactly what went wrong. Your program tried to use something that wasn't there. The next part, object reference not set to an instance of an object, tells us that something expected an object but found nothing. Finally, it shows where the error occurred. At program.calculateGrade, student, in program CS line 15. This means that the error happened inside the calculate grade function in the program.cs file on line 15. To fix this, check line 15 and ensure any objects like student are properly initialized. Once you've located the source of the error, you can begin the process of correcting it. As you might have noticed, these messages often provide crucial details, like the type of error, the line of code where the error occurred, or a stack trace showing the sequence of function calls leading to the error. Use this information as your first clue to identify where things might be going wrong. Once you have this initial information, the following steps are to reproduce the error consistently and then isolate it to a specific part of your code. Reproducing errors means consistently recreating the issue in your code. This helps confirm the problem isn't random and makes it easier to identify the cause. After reproducing the error, isolate the problem using debugging tools such as breakpoints, watches, and print statements. After reproducing and isolating the error, the next step is to analyze and fix the issue. Start by carefully examining the code around the error to understand what's causing the problem. Try to find common mistakes like incorrect logic, unexpected input, or improper data handling. Once you identify the potential cause, make changes to correct the error. Test your code to verify if the problem is resolved. This process may require several attempts as you refine your solution and ensure it fully addresses the issue. To help with the debugging process, programmers often use specialized tools like debuggers to step through their code line by line, inspect variables, and understand the execution flow. Tools like Chrome DevTools, Visual Studio Debugger, and PyCharm's Debugger are popular choices for this purpose. Using the right tools can help you debug faster and catch more errors, but it also helps you know if common errors that occur in code and how to manage them. Common errors are mistakes that cause the program to produce incorrect or unexpected results, even though the code may run without crashing. Common errors can include errors in logic, syntax, and runtime. Let's break down these common errors and learn how to identify and manage each one. Logic errors occur when the program runs but produces incorrect results. For example, a calculation might yield the wrong number because of a formula error, or a loop might iterate one time too many due to an off by one error. Logic errors are hard to spot because they don't stop the program from running, but can lead to incorrect or unexpected outcomes. Review your code against any flowcharts you might have created to spot logic errors. Also, double-check your algorithms and ensure your logic aligns with the desired outcome. You can also use test cases to validate that your code produces the correct results in all scenarios. Another common error is syntax errors. These happen when the code violates the rules of programming language, like missing a semicolon or a typo in a variable name. The compiler or interpreter usually catches these errors before the program runs, making them easier to fix. To work with syntax errors, carefully read the error messages. These typically indicate the line number and nature of the error, making it straightforward to correct. Finally, you might encounter runtime errors. These errors occur during the program's execution. They're often due to unexpected conditions such as trying to divide by zero or accessing an element in an array that doesn't exist. These errors can cause the program to crash or behave unpredictably. Runtime errors can be more challenging because they only occur under certain conditions during the execution of your program. To spot runtime errors, thoroughly test your code, especially edge cases, and manage expectations. This way your program can manage unexpected situations without crashing. Debugging is more than fixing code. It's also an opportunity to learn from errors and improve your coding skills. Each error you encounter is an opportunity to better understand your code and write more robust programs. In this video, you learned about the process and importance of debugging in programming. You also learned about common types of errors and how to work with them. Debugging is an essential skill in programming. It enables developers to identify and fix errors that could otherwise compromise the functionality and reliability of their applications. Imagine you're a developer working on a new feature for an app. You've written hundreds of lines of code, but when you run it, something isn't right. The app crashes or the results aren't what you expected. You wouldn't rewrite the whole thing or hope for the best. Instead, you would systematically debug, combing through the code step by step to find exactly where things went wrong. In this video, we will apply various debugging techniques to identify logical errors in your code. Debugging is the process of identifying and resolving errors or bugs in a computer program. Debugging is an essential skill for any developer. Developers must figure out where the code isn't behaving as expected and fix it so the entire program runs smoothly. There are several ways to debug your code, each with its own strengths. You can use techniques like watches, logging, print statements, and breakpoints to catch and fix logical errors. Let's start by exploring watches, a tool for tracking variables in real time. A watch is a feature that helps you track the value of specific variables while your code is running. It's a feature integrated into software development tools like debuggers or integrated developer environments. Recall that an integrated development environment, or IDE, is a tool that streamlines the development process by combining code editing, compiling, and debugging into one place. When you set a watch on a variable, you can see its current value and how that value changes step by step as the program executes. Imagine your app calculates a shopping cart total. Using your IDE, you can watch on the variable's total price. During testing, you notice that it suddenly changes to 0 when you add a specific item. This could mean there's an error in how prices are added for the item, like missing a value or an incorrect format. While setting a watch helps you pinpoint when something goes wrong with a specific variable, logging provides a broader perspective on how your program is behaving. Logging records real-time data about what's happening as your program runs. You can add log statements in your code at critical points where you want to track information. When the program runs, details are stored in files or databases. By strategically placing log statements in your code, you can gain insights into how your code behaves at runtime, which can be especially useful if you're tracing errors in complex systems. For example, imagine you're debugging a function that calculates shipping costs based on total order weight. You use logging to track the weight of each item. The log shows an unexpected jump in weight when a particular item is processed, revealing it's recorded in grams instead of kilograms. This helps you quickly find and fix the unit conversion error. While logs can be stored, directed to files, and analyzed to provide a detailed record over time, print statements offer a more immediate and straightforward approach for quick debugging during development. A print statement is a command that outputs text or data to a console or terminal window. You use print statements to output the value of variables or the flow of execution directly to the console. Print statements can help you trace the logic of your code by displaying messages at key points. Imagine you're debugging a function that calculates a discount for customers based on their purchase history. You can add a print statement to display the discount percentage. The output shows that the discount is always 0, revealing that the condition to calculate the discount is never met. This helps you identify and fix the faulty logic in the discount calculation. Print statements offer quick insights, but breakpoints are a powerful tool for isolating issues more precisely when you need to pause and examine your code in greater detail. Breakpoints allow you to pause your code at specific lines to examine the program's state in detail. Think of them as a checkpoint within your code. You can set a breakpoint in the IDE and run the code in debug mode. When your program reaches the line with a breakpoint, it stops running. You can inspect variables, step through the code line by line, and see exactly where things go wrong. This method is highly effective for isolating complex bugs that aren't immediately visible. Imagine you're debugging a function that loops through user data to calculate their total spend. You set a breakpoint at the start of the loop. As you step through, you notice that the loop is exiting early because a condition is incorrectly met. Using these techniques together is like having a well-equipped toolkit. Combining them can help you trace errors back to their source. For example, you might start with logging to get an overview, use print statements to narrow down the problem, and then set breakpoints for a more detailed inspection. Each tool provides valuable information, helping you piece together the puzzle. Let's explore how these techniques can be used together in a real-world debugging scenario. Imagine you're working on a function that calculates the total price of items in a shopping cart, but it's not returning the right total. You set a watch in the variable that tracks the total price, add a print statement to check if the function is being called, log the values added, and set a breakpoint at the final calculation. Suddenly you find a small rounding error that's causing the incorrect total. That's how these techniques come together to help you find and fix bugs. Debugging isn't just about fixing errors, it's about understanding how your code works step by step and building confidence in your ability to solve problems. In this video, you learned how to apply various debugging techniques, including watches, logging, print statements, and breakpoints, to help you identify and trace logical errors in your code. Debugging is a vital skill that every programmer needs to master. By applying debugging techniques, you can efficiently identify and resolve logical errors, leading to cleaner, more reliable code. Imagine having a skilled Copilot next to you during a long road trip. Someone who not only helps you navigate, but also spots potential hazards before you even notice them, suggests shortcuts, and ensures you reach your destination faster. That's what Microsoft Copilot offers to developers. An AI-powered assistant designed to guide you through your coding journey, making the process smoother, quicker, and less error-prone. In this video, we will explain the features and capabilities of Microsoft Copilot. Microsoft Copilot is a tool powered by artificial intelligence that assists developers in writing and debugging code. Microsoft Copilot can streamline your coding process and improve productivities in many ways. It offers several key features that developers find invaluable, including code generation, real-time code suggestions, automatic error detection, and code optimization. Let's begin with code generation. Now that we've introduced the idea of Copilot streamlining your work, let's explore how it helps with the first step of any project, building the foundation. When starting a new project or prototype, you often need to build a basic structure quickly. Instead of creating every line from scratch, Copilot can automatically generate the foundational code. This allows you to focus on the creative aspects of your project and save time on routine tasks. After Copilot helps you set up your initial code structure, it's time to go further in the actual coding. This is where Copilot's real-time suggestions come into play, helping you build out your code more efficiently. When writing code, it's easy to get caught up in the solving of problems and overlook optimization opportunities. Copilot can suggest code in real time, saving you time and reducing potential errors. These immediate recommendations help you write cleaner code without breaking your flow. This can be especially helpful when you're working with complex algorithms or trying to enhance performance. Not only does Copilot help you as you write code, but it also helps you to avoid potential mistakes. As you code, Copilot continuously scans your work to detect potential errors, such as syntax mistakes or logical flaws, and highlights them. This integration of suggestions and error detection allows you to address problems as soon as they appear, minimizing disruptions and ensuring your code is as clean and efficient as possible. Once Copilot has helped you spot and fix errors, its work doesn't stop there. The final step is code optimization. Copilot analyzes your code to identify areas where you can make improvements, like eliminating redundant code or finding more efficient ways to perform tasks. This helps you maintain a high-quality code base that is easier to manage and scale over time. From generating code to making real-time suggestions, detecting errors, and optimizing your final product, Copilot is there every step of the way. By leveraging these features, Microsoft Copilot enhances every stage of development, helping you code more efficiently. In this video, you learned about Microsoft Copilot's features and capabilities, showing how it can assist in writing, debugging, and improving your code. By integrating these capabilities into your workflow, you can enhance productivity, reduce errors, and focus more on building and innovating.
Microsoft Copilot uses artificial intelligence to analyze code in real time, highlighting issues and offering solutions that can save hours of manual debugging. This powerful tool helps streamline the development process, allowing you to focus on writing clean, functional code. In this video, we will demonstrate how to use Microsoft Copilot for debugging and logical error detection. I've already set up my development environment and installed the Copilot extension. Before exploring how Copilot can help us debug, let's add some code and examine it. To begin, I add an array named numbers that contains the values 1, 2, 3, 4, and 5. This array holds a series of integers. Below that, I've declared an integer variable named sum and initialized it to 0. This variable will store the sum of the values in the numbers array. Next, I've written a for loop that is supposed to iterate through each element in the numbers array and add it to the sum. Finally, after the loop, there's a line that prints the result of sum using console.writeLine. This outputs the total sum of the numbers to the console. However, in the Problems tab, I can see that there are some issues, and the program currently will not work as expected. This is where Copilot can help. To use Copilot to help me debug these issues, I'll click on the first issue, which states, "The type or namespace integer could not be found." Notice when I do this, there's a yellow light bulb that replaces the red X symbol. Selecting the yellow light bulb gives me a few options. I can generate class integer and convert top-level statements. I can also have the option to fix using Copilot or explain using Copilot. I want to understand the error, so I'm going to first choose to explain with Copilot. This will open the Copilot chat interface. In the chat, Copilot explains that integer is not a valid type in C#. When I scroll down, Copilot also offers suggestions to fix the error. It tells me to replace integer with int. Now that I understand the error, I'd like to use Copilot to fix it for me. So I select the yellow light bulb again and choose Fix using Copilot. Notice that a Copilot suggestion box appears at the top of the screen. It uses the command /fix to describe the error, explaining that the type integer should be replaced with int. Copilot generates new code in line with the file, providing a suggested fix right where the issue occurs. You can choose to either accept or discard the suggestion directly from the box. Let's go ahead and accept this suggestion by clicking on it. The updated code now reflects Copilot's suggestion, and the errors are corrected. Notice in the Problems tab, there are now no new issues with the code in the file. In this video, we demonstrated how to use Microsoft Copilot for debugging logical errors, and explored how Copilot analyzes your code, offering smart solutions that can save hours of manual debugging. What if you could streamline your debugging process with an AI tool that spots errors and suggests solutions in real time? Integrating Microsoft Copilot directly into your workflow makes debugging faster and smarter. It can help you quickly identify and fix issues so you can spend more time writing great code and less time tracking down bugs. In this video, we'll integrate Microsoft Copilot into the debugging process for practical coding tasks. The debugging process involves a few key steps. First, we examine the error messages. Then we reproduce and isolate the error, and then we analyze and fix the issue. Let's get started. I already have some code with bugs in a project file here in Visual Studio Code, and GitHub Copilot is installed and ready to assist us. Here's the code we'll be working with. It's a simple C# program that calculates the sum of an array of numbers. However, there's a logic error preventing the correct sum from being calculated. First, let's examine the code and try to find the error. In the main method, we initialize an array called numbers with 5 values, 1, 2, 3, 4, and 5. Then we call the calculateSum function, which is supposed to sum the numbers in the array and return the result. The function starts with the for keyword, which creates a loop. Inside the loop, we initialize a variable I, which represents the position of elements in the numbers array. The loop condition checks if I is less than or equal to the total number of elements in the array. This means the loop will continue running even when I equals the length of the array. Each time the loop runs, the function adds the value at the current position in the array to a running total called sum. Once the loop finishes, the function returns the final value of sum, which is the sum of all the elements the loop processed. However, arrays start counting from 0, so the first element is at position 0, and the last element is at position numbers.length minus 1. When the loop tries to access the position equal to the numbers.length, it's trying to reach beyond the end of the array. Notice the debugger shows an error message in line,
with the message, index was outside the bounds of the array. And it highlights that line 20 of the code is causing the issue. Our next step is to reproduce and isolate the error. I'll set a breakpoint at line 20 so we can step through the code and isolate the exact cause of the issue. Even though we know from the error message that line 20 is where the issue occurs, we still need to isolate the exact problem. Breakpoints allow us to pause the code at a specific line to examine variables in program flow. Then I'll run the debugger again. Notice it stops at line 20 where I placed my breakpoint. As I step through the code, I can observe how each part is executed. Notice that the values of sum and I change as I step through the loop. When I reaches 5 and sum equals 15, that's when the error message appears. This tells me that the error happens at this specific point in the loop when the code tries to run for the 5th time. Now that we've isolated the issue, we need to analyze and fix it. This is where you can integrate Copilot into your debugging workflow. I'm going to highlight the entire loop from lines 18 through 23. Then I'll select the yellow sparkle icon and select Modify using Copilot. Notice a dialog box appears where I can chat with Copilot and give it commands. I want to understand more about what the index outside the bounds of the array error means, so I'll type the command /explain and the error is in this for loop and select enter. Copilot explains that it's allowing the loop to run one step too far beyond the valid elements of the array. This makes sense based on what we've noticed in the debugging process. Next, let's have Copilot suggest a fix by using the /fix command. I'll type /fix in the dialog box and select Edit Code. Copilot will generate a solution based on its understanding of the problem. Notice that Copilot rewrites my code directly in the editor. It changes the code I less than or equal to numbers.length to I less than numbers.length. This seems correct, so I'll go ahead and apply it to the code by selecting Accept. Now I'm going to run the debugger again to verify the fix. Notice this time the program runs successfully without errors. We also get the expected value of 15 in the debug console. Copilot has helped us efficiently resolve the issue. By integrating GitHub Copilot into your debugging workflow, you can save time analyzing and fixing issues. Now it's your turn to try debugging with Copilot and breakpoints in Visual Studio Code.
The key to successful software development lies in careful planning and design. With a solid project plan, you can ensure that your code is organized, efficient, and ready to work on complex tasks. In this video, we will plan and design a comprehensive code project. Planning and designing a coding project involves defining project requirements, setting objectives, and creating a design outline that includes key coding concepts. Let's explore these steps using an example. You want to build a task management app to help your coworkers keep track of their tasks. First, begin by defining project requirements. Recall that a project's requirements are the outcomes that must be met and the tasks that must be completed to ensure its success and completion on time. Project requirements come in two main categories: functional and non-functional. Functional requirements define what the app needs to do, the essential functions that make the app work. They answer questions like, what should the app accomplish? The functional requirements for our task management app are straightforward. The app must allow users to add, review, and complete tasks. These are the basic actions that make the app useful. Non-functional requirements cover how the app should perform. These are aspects like usability, performance, and security. They ensure the app is not just functional, but also reliable and enjoyable to use. The non-functional requirements for the task app focus on usability and performance. The app should have an interface that's intuitive and that allows users to create, edit, and delete tasks with no more than 3 selections. The app also should be able to load the task list within 2 seconds and be able to handle up to 10,000 tasks without performance degradation.
With our requirements in place, the next step is to set clear project objectives. Recall that objectives are specific results that a person or process aims to achieve within a time frame. For our app, these might include building the code base for adding, reviewing, and completing tasks within 3 months, implementing data integration for task storage within 4 months, and completing testing and debugging, resolving 95% of critical bugs before beta release. These objectives are measurable. We can always check if the app is meeting them as we build. Clear objectives provide direction and help maintain project timelines. They ensure everyone involved knows exactly what needs to be accomplished. With well-defined objectives, we can allocate resources like time, effort, and budget more effectively, making the entire process smoother. Now let's move on to creating a design outline. This is where we transform our requirements and objectives into a plan for how the app will function. A design outline acts as a step-by-step guide for building the app. To design our task management app, we'll break the project into smaller, manageable modules and plan coding components we will use to implement them. For our task app, we need a module for viewing tasks, and this module will provide a simple interface for users to review their task lists anytime. Then we need a module for adding tasks. This module focuses on a straightforward way to input new tasks. Finally, we need a module for marking tasks as complete. This module will provide checkbox interface elements that can be selected. This outline helps us examine the app's structure and ensures we haven't missed any key features. Now let's plan out the coding components we'll use to implement the modules. To implement the modules, we need to use variables, methods, if-else statements, and loops. Since variables store information, first we should outline where we will need to keep data throughout the project. For example, in our to-do list app, we need a string variable for each task. Each time the user adds a task, it is stored in an array or a list of variables. Next, we should design the methods. These will enable us to group related tasks into one reusable unit of code. In the to-do list app, we should have a method for each module, including view task, add task, and mark task complete. Next, we'll plan out where the decisions in our app happen. We'll use if-else statements to handle different scenarios based on conditions. For instance, we'll plan to use an if-else statement to check if the user has entered a task. If the input field is empty, we'll display a message asking the user to enter a task. Otherwise, we'll display a message to add the task to the list. Finally, we must determine if any of our modules must repeat code based on conditions. We'll identify where it's essential to repeat actions and plan to use loops to handle those situations. In the to-do list app, we'll use a loop to display all the added tasks, showing them on the screen each time the user opens the app. In this video, you learned how to plan and design a comprehensive code project. By carefully planning and designing each aspect of our task management app, from defining requirements and objectives to creating a design, we ensure that the app will be user-friendly, efficient, and ready for development.
Now that we've planned the task management app, it's time to build it using C# and Visual Studio Code. In this video, we'll implement the planned project using Learn Coding Concepts. I'll take you through the code line by line, explaining how it works, so you can understand the logic behind each step. As you recall, the app will allow users to add tasks, mark them as completed, and view them. Let's begin building. First, I'll define a class called Task Manager. This is where I'll store all the logic for managing tasks. Now I've declared two static lists, one named Tasks to store the task descriptions, and another named Task Status to track whether each task is completed. The list string will hold strings of the actual task descriptions, while list bool will hold Boolean values with false representing pending tasks and true representing completed tasks. The next step is to handle user interaction through a menu. I'll build a main method that continuously prompts the user to select an action. The main method is the entry point of the application. In this case, it has a static modifier, meaning it belongs to the class itself, not instances of the class. The method returns void, indicating it doesn't return any value. It takes an array of strings as parameters, which allows users to pass arguments when the program starts. Inside the method, I create a while loop to continuously show the menu to the user until they choose to exit. The menu gives 4 options: add task, mark task as completed, view tasks, and exit. I use a console.writeLine function for each of these 4 options. I use a console.readLine function to capture the user's input and store it in a string variable named choice. I use a switch statement to handle each menu choice. The switch statement includes 4 cases and a default case, all based on the user's choice. In case 1, I call the appropriate method addTask to add a task. In case 2, I call the method completeTask to mark a task as completed. In case 3, I call the method viewTasks to display the task list. Case 4 uses return to exit from the program. And the default case is used if the input is invalid and will print an error message and show the menu again. Now let's implement the functionality to add tasks. I create an add task method and first prompt the user to add a task description using console.writeLine with a message asking the user to enter task description. The description is then read from the user's input via console.readLine and stored in the task variable, which is of type string. I add this task to the task list using tasks.add with passing task parameter to the method. I also add false to the task status list because the new task is not initially completed. Finally, I print a confirmation message to inform the user that the task was successfully added. Now that I can add tasks, let's mark them as completed. To do this, I create a complete task method using an if-else statement to first check if there are any tasks in the task list. I use the list count property for this. I compare the count of tasks to 0 using double equal signs. If the list is empty, I print a message saying no tasks available to complete and exit the method with a return statement. Next, I ask the user to enter the number of tasks they want to mark as completed. The input is captured using the console.readLine function, which waits for the user to type something and press enter. Once the input is captured, I try to convert it to an integer using int.tryparse. This checks if the input is a valid number. I then check if the task number is valid by making sure it's greater than 0 and less than or equal to the total number of tasks in the list. This is done with the condition task number is greater than 0 and task number is less than or equal to tasks.count. If the number falls within that range, I proceed to mark the corresponding task as completed. To do this, I access the task status array and update the task at the position task number -1 to true. This indicates that the task has been completed. I then display a confirmation message that says task number marked as completed, where the task's description is shown as a part of the message. If the input is invalid, either because it's not a number or the number is outside the range of tasks, I print an error message that says invalid task number. This ensures the user knows they need to enter a valid task number. Let's move on to the method that allows the user to view a list of tasks. I'll create a viewTasks method that first checks if there are any tasks to display by checking the tasks.count. If no tasks are available, it prints no tasks available and exits the method. If tasks exist, I use a for loop to iterate through the task list and print each task along with its status. The loop runs from 0 to tasks.count -1, and for each task I receive the status from the task status list. If the status is true, I display completed. Otherwise, I display pending. I then use the console.writeLine to print the task number, description, and status. The task number is shown as I+1 to make the numbering user-friendly. Now that I've implemented the core features of our task management app, we have a working tool for adding, viewing, and completing tasks. The more you work with real-world examples like this, the better you'll get at understanding C# and applying coding concepts to your projects.
Congratulations on completing the Foundations of Coding Full Stack course. Throughout this course, you have built a solid foundation in full stack development, from planning projects and understanding logical structures, to mastering control flows and creating efficient, reusable code. Equipped with these skills, you are now prepared to tackle real-world challenges and continue growing as a full stack developer in an ever-evolving field. We began this course by exploring the fundamental principles of full stack development and the essential responsibilities of full stack engineers. You learned about the differences between front-end and back-end development, discovered the key technologies and tools used in full stack development, and the basics of Git and GitHub for version control, establishing a solid foundation for effective full stack development. Next, we delved into logical processes and their importance in programming. You used deductive reasoning, deconstructed complex problems, and practiced both top-down and bottom-up approaches, including creating pseudocode for various scenarios. Then we focused on algorithm structures such as if-then statements and binary logic. You created flowcharts to outline logical steps, recognized key data types, and learned how to declare variables in C# while developing a basic algorithm. After that, we defined basic control structures such as if-else statements and switch cases to understand how they manage decision-making. We then covered loops like for, while, and do while, and their role in handling repetitive tasks. Finally, you practiced combining these elements through various coding exercises. Next, we explored how to use functions to build reusable code blocks and examine methods in C#, focusing on their definition, syntax, and practical applications. You learned how to call methods and manage parameters for efficient data transfer. Finally, we developed basic programs that utilize functions and methods to solve various problems. You combine the concepts, techniques, and skills gained throughout this course to create a code project that incorporated essential elements like if-else statements, loops, conditionals, functions, and variables. As you progress, remember that the skills you've gained are just the start. Full stack development constantly evolves, so keep refining your techniques, stay updated with new trends, and focus on creating accessible, efficient web applications. Your journey in development has only just begun.